We can remind everyone to mute during the presentation, please.
Sure. Can you actually just mute them en masse or something too?
Yeah, and then Hans, you can unmute.
Should we wait a couple minutes or?
Wait, maybe one more minute.
Yeah, I wouldn't wait too much longer. I think people will just sort of shuffle in as they come.
It looks like we have people joining though. The participants are going up in numbers, so.
Right, yeah.
Okay.
Yeah,
Nice.
I see Letty and Xinghua have joined. Morning.
And we have our first 3 speakers, so that's at least, maybe Hannah's here too. Maybe we have our first 4, but yeah, I think we're in good shape.
So this is Tony Craig. I'm on the phone line, but I'm having trouble joining via Zoom for some reason. I don't know if others are having any problems. It sounds like people are joining via Zoom successfully.
Tony, I think the only thing is you had to go through a re-registration process and then accept the code of conduct terms.
Yep.
Then that
Yeah,
will.
I did all of that. I got an email with all the information on it from Todd. So, you know, I'll keep trying. It sounds like it's working for others, so I'll just keep trying.
Yeah, it is working. Glad you could be here, though.
We'll see if I actually make it.
Is a situation where the password's not working?
That's correct. It says yeah, incorrect password or something. There's 2 passcodes on here. I've tried both of them. One of them is anyway.
One of them specific to the phone and the other one's for the web, but
that's right.
I the same email. That's what I logged in with.
Yeah. Make sure too, if you're cutting and pasting the password, that you don't get extra spaces in there. That sometimes happens.
Yep.
Yeah, that's
I tried all those things. So
okay.
And okay, well, I'll keep trying.
Well, I think we probably should get started. And so, Hansi, were you planning to do the welcome?
Sure, I'd be happy to welcome. So, hello everyone, welcome. Happy to see you at yet another Zoom meeting. Actually, I'm excited because this time there's actually people's faces rather than just little blank postage stamps. So that's always kind of exciting. So we just have a few sort of little announcements and talking points that we want to get through before we start like the meat of the discussion here, which will be all of your fabulous science. So to begin, we want to advertise some available model output data sets. And so these can be used for all of your fun research adventures. and they're just waiting to be used. So please use them. So, so far, the ones to announce are, first of all, a series of season-to-season hindcasts with the CESM2. So these were run by the Earth System Predictability Working Group, and they actually contacted us and said, y'all like CICE predictability. Do you want to do something with these? And so there's actually an amazing amount of CICE output available. The details are written here. Weekly starts, let's see, 45-day long runs and 11 ensemble members, and from 1999 to 2019. So if you are interested in this output, please get in touch with us, and we will make sure that you get a hold of it. Okay. And then the second thing is the CSM high res runs. So first of all, there's a couple things here. They are some of them were contributed to high res MIP. So we have a couple of sets of runs associated with that. And in addition, there's a whole bunch of extra stuff. So we have like a long pre-industrial control in this super high res sort of configuration, which is a 1/4 degree atmosphere land and 0.1 degree ocean and ice. We have an 1850 to 2100 historical and RCP 8.5 transient, no ensemble members, unfortunately, ensemble member of 1. And then an 80-year CO2 ramping run, as well as 4 ocean ice forced runs done using the surface forcing of the JRA 55, optimized for such ocean forcing experiments. And then once again, in terms of high-res MIP, there are additional 130-year 1950s control runs, which sounds pretty fascinating. And then a 1950 to 2050 AMIP style run. So lots of things available here. And then just to let you know what's coming up soon. So by the late summer, what should be available to everybody are the CSM2 large ensemble runs. So that should be a great resource for folks. And then also what will be available are CSM2 runs with CMIP5 forcing. So you can really get a sense of to what extent differences between CSM1 and CSM2 are due to the forcing and what extent they're due to actual differences in the models. And I believe there's 3 ensemble members here. I think that is right.
There's actually 7.
7. Oh my gosh. Okay.
Awesome.
Even better. 7. Okay, good. And then CSM2 tuned ice runs, which Jen K will be talking about today. Those should generally be available to the community by late summer. So anyway, we're excited to hear about what she has to tell us about those runs. And then I want to tell y'all that it is time to use your computing resources that you have requested. It is time to burn some CPU hours, okay? Metaphorically, of course. So if you have requested resources, and remember, I know it feels like, you know, a decade ago, but this was just last September that we all requested them. So please get in contact with us so that you can start using them if you haven't already. And for help on this, contact our one and only fabulous Dave Bailey. He will help you with all of the details there. And then if you didn't request resources, like, please let us know, because we usually end up having too many resources because people end up sort of canceling their experiments, deciding to do something else, et cetera, et cetera. They found out someone else already did the experiment that they wanted to do. So in that case, we end up having some extra resources, and we would really like to just use all of our resources. So get in touch with us. Even if you didn't ask us, get in touch with us and we'll see what we can do to hook you up. Okay. So the types of topics that are supported under our current resources include prediction, polar prediction, particularly CICE, integrating models and observations, wind CICE interactions, the response of the polar regions to external forcings of all different varieties, as well as some resources for Antarctic CICE and Southern Ocean process work. So, and now I'm going to hand it over to Dave so that he can tell us some amazing things that are going on with CICE 6.
Yeah, so thanks, Hansi. Now, if you don't use your resources, I'm going to use them. So, you know, please do sign up and let me know if you need help with that. But basically, I've been working on bringing in the new CICE consortium model, CICE 6, into the CESM framework. And so one of the first steps in this process is to make sure that the climate of CICE 6 is similar enough to CICE 5 when in a fully coupled configuration. So I've run about 50 years of CSM2 with both CICE 5 and CICE 6. And I'm going to be validating the climate between these two simulations. And I may actually extend to 100 years just to make sure that we can statistically have some confidence in the climate between these runs. Both of these runs use this new CMIPS new OPSI driver, thanks to Mariana Vertenstein for doing the bulk of that coding there. So CICE 6 will only be available using this new driver in the code. And so, you know, you can, again, talk to me more about this later on. Preliminary analysis at least suggests that the runs do have a very similar climate, even though they're, you know, they have the same physics, the same constants as best as I have been able to do. But there are bug fixes, other answer changes in the code that are just going to make them have different answers. My next steps in the next 6 to 12 months, I'm going to get CICE 6 into a CSM beta tag so that it'll be the default CICE component when you check out that CSM beta tag. I'm going to be working on a new CGrid staggering implementation. This is for coupling to MOM6, which runs by default on this CGrid. A big thing that is going to be a challenge for us is this new coupling of heat, freshwater, and salt, because MOM6 uses these natural boundary conditions. So, you know, POP used to use the virtual salt flux, was a constant volume. And so MOM6 has opened up a world of possibilities, but also a number of complexities with doing this. And then I want to start using some new physics that's available in CICE 6. We want to test this out to determine what we're going to use as our default CICE component for CESM3. And so testing the landfast ice parameterization of Jean-Francois Lemieux and others, as well as the new flow size distribution from Letty Roach and others. So back to you.
Awesome. Thank you, Dave. Yeah. Dave is very busy, as you can see. Okay, so here's the overview of our program today. So we actually were really pleasantly surprised that so many folks wanted to share their research at this meeting, and we have been able to accommodate everybody, so that's lovely. So this morning, the talks will generally focus on Antarctic climate, some pan-polar studies, so those that are spanning both hemispheres, as well as some synergies between observations and models. We're very fortunate to have several amazing folks from Mosaic here who will be sharing their findings from their time on the ice last year. Stuck in an icebreaker in the Central Arctic. I think that's correct. And then in the afternoon, the focus will be completely on Arctic climate, various processes, polar amplification, CICE predictability, dynamics, winds, et cetera, et cetera. So, and then in both morning and afternoon, we'll have sort of some time and space for discussions to really get a sense of where our polar climate research is going, where we can collaborate, and yeah, where we can sort of work together. So I think that this is now time to hand it over to our first speaker, unless Dave and Marika have something else to say.
No, I'm good.
No, yeah, just welcome everyone. So,
yeah, welcome.
Yep.
Yay. Okay, great. So I'm going to hand it over to our first speaker. So I'm going to stop sharing my screen. How do I stop? Oh, stop share. That's it. Yeah. Yes, I'm not super fast with Zoom, apparently. Okay, so our first speaker is Ray Chemke, who's coming to us from the Weizmann Institute of Science. And he will be talking about using multiple large ensembles to elucidate the discrepancy between the 1979 to 2019 modeled and observed Antarctic sea ice trends. So welcome, Ray, and we're really thankful to you. You are in such a different time zone that it is amazing that you are even here. So very happy to have you here. Thank you.
Thanks. Yeah, so I'm going to talk about the recent discrepancy between model and observed Antarctic sea ice. Specifically, I'm going to look at the role of internal variability versus force response in models and what's causing this discrepancy. And this work was done with Lorenzo Polvani, Columbia University. Sorry. And I'm going to start with looking at the time evolution of Antarctic sea ice extent from 79 to 2019 over March, April, May. This is the black line. And we see this, that between, for example, 79 to 2015, we see this surprising increase in Antarctic sea ice extent. Blue line showing us just a linear regression over this period. And previous studies show that models fail to capture this increase. So on bottom left, I'm showing the sea ice extent trends from 79 to 2015 across different CMIP5 models. So each gray bar is for a different CMIP5 model. Multimodal mean is in green, and the observed trend is in black. And we see that indeed most models do not capture this surprising increase. But over recent years, we see looking back on the black line, a time evolution, we see this kind of large reduction in sea ice extent, and one might wonder maybe now models are capable of capturing the sea ice extent trend. So in panel B, I'm showing the trends over the entire period, and even though the observed trend is significantly reduced, still most models do not capture the observed trend. So this discrepancy is still happening, and here we're trying to understand if this discrepancy between the models and observation is due to biases in the model's force response, or maybe it's because when we're looking at the CMIP5 ensemble, we're not adequately simulating the internal variability of the system. And one reason why we suspect that internal variability could cause this discrepancy is because previous studies have suggested that the increase in Antarctic sea ice in observation might just be due to internal variability, not part of the force response to external forcing. So just two examples of these studies. On the left is taken from Fan et al., showing time evolution over the Southern Ocean of different metrics. So the upper one is sea ice extent. Note that they flip the y-axis, so it's going down, meaning that it's increasing. Then we have sea surface temperature, zonal wind, sea level pressure, and surface air temperature, all of them showing this kind of multi-decadal variability, which might suggest that sea ice extent also is part of this kind of long-term variability. On the right is taken from Polvani and Smith 2013. We see all 27-year trends from pre-industrial control run of different CMIP models in red and blue, and the vertical solid black line showing us the observed trend, 7-year trend. And we see that it's well within the pre-industrial run, and thus, since it's only made of internal variability, it suggests that this trend is just maybe part of internal variability. So to see whether this discrepancy between models and observation is due to internal variability or force response, we're using large ensemble. Using large ensemble in this kind of question is quite straightforward because unlike the variability or the variance across the models in CMIP5 ensembles across a large ensemble is only due to internal variability. And averaging, of course, the members in each ensemble isolate the force signal. So we can actually have these two components and see what's causing this discrepancy. And we use here 5 different large ensembles. And before comparing those ensembles to observation, first we want to see if they will capture the climatology of sea ice extent. So I'm showing here the sea ice extent climatology defined as the average between 79 to 2019 as a function of month across the different ensembles. So each ensemble has a different color, and observation are in black. And we see that 3 ensembles are doing an okay job capturing the climatology. This is the NCAR ensemble, the Australian one, and Canadian one, while the MPI and GFDL one are less capturing the climatology of Antarctic sea ice extent. So for this talk, I'm going to focus on the 3 ensembles that are doing an okay job capturing the climatology. Right, so let's see how these ensembles, if they're able to capture the observed trend. The answer is, I can tell you it's no. So I'm showing here the PDF of 41-year trends across members of each ensemble. So on the left is CSM, middle is the Canadian one, and right the Australian one. the mean of each ensemble is the green line, and the observed trend, 41-year trend, is in the solid black line. And you see that none of the ensembles are able to capture the observed trend, suggesting that internal variability could not explain this discrepancy between models and observations. Now, before concluding that, we want to make sure that first, the ensembles are large enough to simulate at least the internal variability. And second, that they are actually simulating well the variability of CICE. So to see if the ensembles are sufficiently large to capture the variability, we compare those PDF in each ensemble to all 41-year trends from a PI run, because in a pre-industrial run, we have thousands of members. So we can see if we're adding more members, is this changing our PDF, or is it enabling us capturing the observed trend? So the orange PDFs that you see here are the PDF from a PI run, all 41 years from each PI run, and it's shifted, instead of being around 0, around the forced signal in each ensemble. So we can have a easier comparison. And you can see that even if we add many more members, we still do not capture the observed trend, suggesting that, before that, at the top left corner of each panel, I'm showing the ratio between 1-star deviation from a PI run and 1-star deviation from the actual ensembles. And we see that it's very close to unity, suggesting that adding more members does not help us to capture the observed trend. And it seems that the ensembles are sufficiently large to capture the simulated variability at least. And second, we want to see whether the ensembles are capturing the observed variability. So for that, we just detrended the time series of observation in each member in the ensemble, and we look at standard deviation of this time series as a simple metric for internal variability. And I'm showing the PDF of that below, and you see that both CSM and the Australian ensemble captured the observation, which you see in the brown line. In the Canadian one, it's at the edge of the ensemble. So overall, it seems that 2 of the 3 ensembles do capture the variability of the observed variability, and all ensembles are sufficiently large to capture the variability. So our conclusion is that this discrepancy between models and observation is not likely to stem from internal variability, but it seems to come from biases in the model's force response. So next, we want to understand better what's causing this bias in the model's force response. And here we're going to focus on ocean coupling. And for that, we built a hierarchy of ocean locking experiments using CSM. It's run over the 20th and 21st century. So there's 3 hierarchies in this kind of suit. The first one, we use the full CSM large ensemble, the 40 member from Jen's work, which has the full physics ocean. It has active thermodynamic and dynamic coupling. Then we did another ensemble of 20 members with all components similar to the large ensemble CSM, except for the ocean component. We'll replace it with a slab ocean model, and we fix the ocean heat flux convergence in that slab ocean with PI values. So in that configuration, changes in CICE could not be affected by changes in ocean heat flux convergence. So taking the difference in the CICE trends between the full physics, the fully coupled model, and the one with fixed ocean heat flux convergence allow us to isolate the role of dynamic coupling. Then we need another ensemble of 20 members where we fix the ocean temperature. So there is inactive thermodynamic and dynamic coupling. And then we can take the difference between the fully coupled model and the fixed ocean temperature and isolate the role of oceanic feedbacks. And also take the difference between the fixed ocean heat flux convergence and the fixed ocean temperature and isolate the role of thermodynamic coupling. So let's see the contribution of each of these ocean coupling components in the force response in CSM. So I'm showing here again the CICE extent trends. Red is CSM. This is what we saw before in the fully coupled. The gray is the contribution from ocean coupling. And we see that most of this force signal is coming from ocean feedbacks. And decomposing these ocean feedbacks to thermodynamic coupling in green and dynamic coupling in blue, we see that most of the force signal is coming from thermodynamic coupling, while changes in ocean heat flux convergence acts to reduce this CICE loss by approximately 26%. This might suggest that the discrepancy, the bias in the force response, it could be from thermodynamic coupling, since it plays such an important role in melting the forced signal. So to examine that, we looked at the recent trends between 1979 to 2019 of surface heat fluxes. This is only the ocean atmosphere part, ocean atmosphere coupling part in this green line. across the different ensembles. Those are the colors here, and in 3 different reanalyses. Those are the horizontal gray lines. And you see that while all models actually showing increase in surface heat fluxes, meaning warming of the Southern Ocean, reanalysis actually showing a cooling, suggesting that we do see some, we say, discrepancy in thermodynamic coupling, which might suggest why we get such strong melting in the models. And last slide, I just want to show you that having model biases in high latitude does not only affect high latitude climate, but mid latitude climate as well, because since models do not adequately simulate the cooling, for example, of the Southern Ocean, they're actually not simulating well the meridian temperature gradient, and as a result, they're not simulating well the recent changes in eddy heat fluxes at mid latitudes. So the plot that you see here showing us eddy heat flux trends over recent decades, the red bar showing us the different members in CSM, and the green line showing us the trends from 3 different reanalyses. And we see this discrepancy that while the CSM showing us a weakening of eddy heat fluxes at mid latitudes, reanalysis actually show a strengthening. And we were able to show that this discrepancy is coming from the fact that models are not adequately simulating the cooling over the Southern Ocean, and as a result, the meridian temperature gradient. So I'll just conclude and say that looking at the recent discrepancy between observed and model Antarctic sea ice trends, it seems that this discrepancy is due to biases in the model's force response, and it's coming from, might become from thermodynamic coupling. And we saw just another example of how these model biases in polar region can affect also mid-latitude climate. Thank you.
Thanks so much, Ray. That was awesome. We would love to take questions for Ray. So feel free to either to speak or to put a question in the chat.
So this is Marika. I had a quick question. So the observed trends in the Antarctic are very regional, and there's actually compensating regional trends that lead to this small increase, right? So do you think there's value in looking more at the regionality of the trends in the climate models to try and get a sense of what they might be doing incorrectly in their forced response and maybe in their internal variability as well?
Yes, I guess yes, but I would say that it's not really compensating. Most regions actually show an increase aside from one region, I guess. I mean, that's my understanding at least, but it's still interesting to look regional and see in which region this appears, or at least this biases appears in the force signal.
I have a question. So this is Qinghua. So I just want to say to add Blanchard just had a paper published this year, early this year. He added observer wind in the model in the CESM to see how this Antarctic CICE simulation improved. So he found a lot of improvement by adding observer wind in the model. So yeah, so I think so maybe relate to your talk. So have you checked? Have you think how to link your study with the wind variability in Antarctica?
No, I actually haven't. It's one step forward would be to look, for us, was to look at these thermodynamic coupling processes. Part of them are affected by the winds, of course, like latent heat fluxes and sensible heat fluxes, and see how these which component in thermodynamic coupling is responsible for that, but we haven't looked at winds.
Okay, thank you.
Jen has dropped the link for that paper in the chat.
Yes, excellent.
Hi, Ray. Very nice talk. So this is Widow. I have a small question. So I'm just wondering, you look at the temperature impact for the bias of the Antarctic sea ice. Just wondering, how about salinity? Will salinity also affect?
So where did I look at temperature? Sorry, I missed you.
Oh, so you conduct experiment to check the sea surface temperature and also the heat flux convergence. So that's the thermal part. I'm just wondering, how about the highland parts? Will the ocean salinity also contribute to the bias?
No, it could be. We checked only one thing. It also could be that, there are biases or discrepancy in many different parts of the model. It's not necessarily coming from only one thing, but yes, actually, we should look at salinity as well.
Thank you very much.
I just have a quick question, just clarifying the final slide where you showed the V prime T prime discrepancy. Yeah. So, sorry, this is I haven't read this paper. Can you tell me, are you talking about the atmospheric eddies or the ocean eddies? Sorry, that's not obvious
sorry,
to me.
No, those are atmospheric eddy heat fluxes.
Okay, thank you. So I think then what I would say, is that then if the atmospheric heat fluxes by eddies are increasing, usually that means that the ocean ones are decreasing, right? Usually it tends to be sort of flipped, like kind of compensated. And so that I think would be consistent with less ocean heat delivery and therefore, like CICE expansion or something, just sort of in a sort of hand wavy way. So yeah, that's really cool. Thank you. That was helpful. I was also wondering too, so that is just the eddy heat fluxes. What about moisture? I bet moisture is also increasing, right? V prime, Q prime?
Yes, but there are actually CSM at least doing quite well capturing the eddy moisture fluxes over recent decades. So I would say that it's not affected by the discrepancy that we have over.
Okay, thank you so much, Ray. Any other questions for Ray? All right. Of course, you know how to contact Ray, so hopefully it's okay if I just advertise that you should contact him for further questions if you have it. Yeah, great. Thank you so much. And now I'd like to introduce our next speaker. I know we're running a little bit long. My apologies for this. So the next speaker is Alice Duvivier from NCAR. And she is going to be talking about the coupled impacts of sea ice thermodynamics on Antarctic, due to Antarctic coastal ice production. So take it away, Alice.
Okay, thanks. Can everyone hear and see okay?
Yep.
Okay, I see thumbs up. All right, so as many of you know, one of the big changes in CESM2 compared to CESM1 is that we changed the sea ice thermodynamics from the Bits and Lipscomb 1999 thermodynamics to a mushy layer where we have prognostic salinity and we wanted to basically see what some of the coupled impacts might be of this change in thermodynamics on the system. So let's see if this will advance. Okay. So I wanted to point out that the reason we're focusing on the coast is that we have these polynyas that form along the coast. You can see this is from observations wherever there are colors. It's regions of high ice production, and they're important for both the physical system and the ecosystem. So these polynyas are basically sea ice factories. They produce sea ice. The sea ice gets blown further north, and those polynyas continue to produce sea ice throughout the Antarctic winter. They're also in the location where Antarctic bottom water constituents of the ocean water are formed, and so they're important for the ocean circulation. And they're also a habitat for marine animals and phytoplankton. And the mechanism for most of these coastal polynyas is basically you get downslope winds coming off the Antarctic continent. It blows ice away from the coast. You get some area of open water, some really cold air blowing over that water. You're going to get ice forming. And when you have this open water, that's called a polynya. Some of the work that we've already done with CESM2 has shown that there are differences compared to CESM1. So this is from a paper that Hansi put together last year. What I want to point out here, these are just June, I've only pulled June, and we're looking at sea ice production in centimeters per day, and these brighter colors means more. What we see is in CESM2, this top row, the frazzle ice formation or formation in open water is much higher along the coast. See these really bright colors when compared to CESM 1. Here we have some, but not very much. But I want to point out too that this is not an apples to apples comparison, because CESM 1 and CESM 2 have many more differences beyond just thermodynamics. And so what we're looking for is a more apples to apples comparison, showing what the differences in these thermodynamics on the coupling basically due to the whole system. And so what I'm using in this experiment is 50-year pre-industrial control runs with CESM2 that Dave ran and published on. And here's the information about his paper. And he'd done some initial work looking at some of the differences you see between the mushy thermodynamics and the bits and Lipscomb thermodynamics. So one thing you can see here is that there's more snow ice growth of sea ice when you have the mushy layer thermodynamics, and the snow depth on sea ice is much less. So the purpose of this study is to understand the regional, seasonal, and coastal impacts of the sea ice thermodynamics on the coupled system. And so we'll really focus on the coast, and I've broken things down into regions as well, because as Marika pointed out in the comments for the last talk, things can be really different by region. So what I'm showing here is just the winter, and by winter I mean April to September, so the whole kind of ice growth season. This is looking in the bits and Lipscomb thermodynamics experiment. This is the average sea ice concentration, or fraction, I guess, in this case. And you can see that, as you'd expect, in the winter, we have high ice fractions pretty much everywhere. When we look at the difference between the mushy and the mushy and the bits and Lipscomb thermodynamics, we get that the differences are very small and pretty much not statistically significant anywhere around the coast. So if you just did a climatology of the winter ice differences, you would see, well, they're not that different. I also want to point out that I've divided up the Antarctic into these regions. So I'm just going to point this out because this will be on a lot of the other figures, and I want to make sure that this is clear. But we have a Weddell Sea region here, an Indian Ocean sector here, a Pacific Ocean sector here, the Ross Sea sector here, and the Amundsen-Bellinghausen sector here. And so what I've done in this figure here on the right now is look at the regional ice area. This is just April, May, June, but it's very similar for July, August, September, between the bits and Lipscomb, which is the dark color, and the mushy layer thermodynamics, which is the lighter color. This is the total ice area over the whole Ross region here, a time series over the 50 years. And basically the takeaway from this is that there aren't significant differences in the ice area in pretty much any region. The only exception is here in the Indian Ocean sector. You can see there's this period where the mushy thermodynamics led to lower total ice areas for a bit, but it was not consistent throughout the whole period. So I just want to point out that in general, if you just looked at the ice area, you would think, okay, these two runs are not all that different. But when we start looking at the mass budget and what's causing the ice to have the state that it is, we do see that there are significant differences in the ice growth terms specifically. So this, again, I pointed out, this is the Ross Coast. So in almost all of these figures, I start with the Ross Coast and then I work my way around clockwise to the Pacific. So it'll always be Ross, Amundsen-Bellinghausen Sea, Weddell, Indian, Pacific. All right, so in all the regions, what we're seeing here is differences in the mass budget terms, and this is mushy layer minus bits and Lipscomb. And I want to point out that you see this dark blue line. That means that the Frazel ice growth, or the open water ice growth, is larger in the mushy layer thermodynamics experiment in all of the regions compared to the bits and Lipscomb. And similarly, the snow ice growth is also larger, though it's not as big of an increase in the snow ice growth. That's this green line. Sorry about the not colorblind friendly. I've kind of run out of options when you have too many terms. And then in contrast, the congelation ice growth, which is this like purple line, has decreased in all of the runs. So even though the ice state is fairly similar, we're kind of, when you actually look at the processes that are going on to form ice, those actually are different between the two. One thing I want to point out too that I find a little peculiar is that there's more bottom melt basically between all of in the mushy layer thermodynamics, even in the winter. And that doesn't exactly make sense to me because you're not usually melting a lot of ice in the winter, but it does suggest that the ocean temperatures might be a little bit different. One thing that we're looking at, and we still don't really understand this, and so if anyone on this call has insight, that would be very much appreciated. But when we look at the correlation between the frazzle and congelation growth, we find that that it's negative in both the bits and Lipscomb, that's this top row, and the mushy thermodynamics, and this is in CESM2, basically throughout the whole winter season. And to us, this doesn't quite make sense. Our thought of how the processes would be going on here is that you might get frazzle growth, and then that would lead to an increase in congelation growth, maybe in subsequent months. So if anyone has any brilliant ideas about what's going on here, we would like to talk more. We have some ideas. I'll talk about those in a minute. One thing I do want to point out is that here I'm showing the relationship between the frazzle ice growth and the mixed layer depth. And what we find is that the frazzle ice growth leads, if there's an increase in frazzle ice growth, it leads to shallower mixed layers in subsequent months. And that's true for both the bits and Lipscomb and the mushy thermodynamics. But you can see that the relationship is a lot stronger in like the Ross and the Bellinghausen Amundsen Sea than it is in the Pacific or the Indian regions. Those sectors, the relationship is pretty much non-existent. I want to point out that there's an opposite relationship for congelation growth, which, given the anti-correlation between those two terms, is not unexpected. When we look at some of the ocean state differences, what we see here is if I look at, again, this is winter, so April through September average mixed layer depth, and then I take the difference, the mushy thermodynamics leads to shallower mixed layers. So the red is negative. I know that's a little confusing. But there are shallower mixed layers in many regions. It's not consistent everywhere. You can see here there's in the kind of Indian and then Eastern Weddell regions, there's pretty much no large difference. But in some regions, there are certainly big changes in the mixed layer depth. And so this implies there is a big impact on the ocean. When we look at the ocean temperatures, you can see too, this is the 200-meter ocean temperature between these two experiments. Again, this is kind of confusing. I didn't notice it until this morning, but the red means colder. The 200-meter ocean temperatures are colder here in the mushy experiments than they were in bits and Lipscomb, though that's not true everywhere else. This is, again, pretty regionally specific to the Amundsen-Bellinghausen Sea. And what I wanted to point out was I said I was going to talk about atmospheric impacts as well, and then we realized, whoops, one of the runs, no atmospheric data were kept except for the last 2 years. So we're rerunning these right now. They are pre-industrial experiments. They've run 50 years so far. They were done just yesterday. So I didn't show all the data in this presentation. We are thinking we might extend them out to 100 years to increase the statistics, the robustness of the statistics. And I want to point out that one of the other things we added is daily atmosphere ocean biogeochemistry and CICE data. And so one of the things we're planning to look at that I'll talk about in a moment is the different timescales and processes going on those timescales and how those differ. And even though I'm focusing on the Antarctic, there's also Arctic data. And so people on this call who are looking, who might be interested in having daily output and understanding the difference in thermodynamics in the Arctic, you could use this data set as well. So as I said, this is still very much in progress. We're very interested in a conversation, but some of our outstanding questions are to look over a range of timescales. So weekly, you could imagine if a cyclone goes by, causes a polynya, what would the sequence of different dominant processes be during that event, monthly and then seasonal as well. And the other thing that I've done a little bit with, but not a whole lot so far, is using the CESM2 large ensemble to investigate changes in the polynyas over time. I'm interested in the coupled impacts on the atmosphere and the ocean, and I want to know if the mechanisms are changing over time. And one of the reasons this is really important is to understand the biology in the region for people who are basically needing to manage these regions and try to protect and preserve biology and ecosystems. So that's the end of my science talk. I also wanted to just briefly point out that a friend of mine is a professor of fine arts at University of Connecticut, and she specializes in art science work. And she and I started talking last December, and she got funded through UConn to do animated short with music and all of that is going to focus on the changes in ecosystems and physical landscapes in the Arctic. So she'll be doing all of the art stuff, but I have agreed to help with being a scientific subject matter expert. And if anyone on this call is interested in talking to her, as she kind of comes up with her concept of how and what she wants to animate, that would be fantastic. She's thinking about looking at everything from microscopic processes. So I'm thinking like, brine drainage and sea ice and biogeochemistry, to the macroscopic processes like, changes in sea ice area or storms or whatever. And it'd be great to have more than just me on this project. It'll be displayed at the MCAR Mesa Lab and of course on like YouTube and all of that stuff too when it's done. And that's the end of my talk. I'm gonna stop sharing because I can't see people and hands and stuff like that. Okay.
Thanks so much, Alice. Yeah, so let's open up the questions for Alice.
Hi, this is Letty. Thanks for that talk, Alice. I just wondered if you could speak a little bit more about the mechanism between the salinity evolving model and the mixed layer depth, the impact on mixed layer depth.
Yeah, so we think that one of the things that we think might be going on is with the salinity evolving model, we have changes in the freshwater, or I guess I should say the salt fluxes from the ice into the ocean, and that would affect the ocean mixing and how deep the mixed layers are. As I mentioned, when I realized that we'd need to rerun with different model experiments, some of these things I put on hold because I was like, well, I'm gonna have to redo them with the updated experiments anyway. So I haven't looked at the salt fluxes to the ocean in this experiment, but that's on the list of things to do. And I think that will be really relevant for understanding, those changes in mixed layer depth.
And as a follow-up, my understanding is that CSM maybe overestimates the mixed layer depth in the sea ice region. Do you think that's right? And so is this kind of acting in a way that's good compared to observations?
I'm not sure where the echo is coming from. I will say that most of my work looking at the mixed layer depth has almost always been north of the sea ice edge comparing to observations, because there are not a lot of observations of mixed layer depth. Once you get into the sea ice, basically Argo floats have a hard time in there. I think I saw Keith Lindsay was on this call, and he might be better suited to talk about the mixed layer depths or the Antarctic bottom water formation in CESM2. My understanding was it was pretty biased. And this sort of experiment, I'm looking at the pre-industrial control, so it's kind of just trying to understand what the differences are in the system and not as much a direct comparison to observations. But yeah, I don't know if Keith wants to chime in or not. He's probably hiding.
Hi, Alice. Yes, deep water formation is pretty bad in CESM2 and the coupled by 1. Keith Moore at UC Irvine is done some analysis that attributes it to a fresh salinity bias. I'm not sure if he's compared that to previous generations of CESM, but that's one of the indications of something that's playing a role. But we don't know why we have a freshwater bias, but we certainly do have too weak ventilation into the bottom water.
Well, thank you for the questions. If anyone else has any other thoughts about the frazzle or the congelation growth and stuff like that, I'd be happy to talk more offline. But otherwise, I think things are a little behind, so I don't want to delay us any further.
Thank you so much, Alice. Appreciate it. Okay, so let's move on to our next talk. by Jen Kay from the University of Colorado, and she will be talking about the influence of sea ice mean state on climate change and variability in the CESM2. So take it away, Jen.
Does the slide look okay?
Looks awesome.
Great. So good morning, everyone. I'm going to talk about some work that we've been doing looking at the CESM2 and the influence of the sea ice mean state on both the polar climate and also the climate more generally. And this is work that many of you on the call are actually co-authors on. And for those who are not, there will be an opportunity to look at these simulations. They were really done with the Polar Climate Working Group resources and therefore are a resource for you. So yeah, getting right into it. For those who are not as familiar with the CESM2 CAM6 Arctic sea ice, there were some issues that have been noted both in the CESM2 description paper and also in more sea ice targeted analyses, namely that the sea ice in the Arctic is a lot thinner than it was in the previous version of CESM1, and that also it's quite biased in the late summer. So you can see here basically the observations showing a lot more sea ice. So the observations here are in red and CESM2 with CAM6 is in black. This bias where there's insufficient late summer sea ice can be traced basically to this thin ice issue here. So both in the extent and then also in the thickness, some indications that the model is too thin. And this has implications for projections, for the amount of area in the present day state. And this has been noted in a paper by Patricia, who's on the call. But basically, yeah, there's some substantial impacts. And this is just a feature that you all should know about with the CESM2 CAM6. So for us, this was really important because obviously many of us look at the Arctic sea ice and are concerned about things like Arctic amplification, and the timing of sea ice loss is very important to that. So we talked about what to do to address that. And basically what we ended up doing is what I'll call a street tune. And basically the idea here is that we're just going to take the CESM2, we're going to make some small modifications to it, and hopefully improve the sea ice mean state, and in particular, be able to better replicate the late summer sea ice observations that we have. And just remember the context here that this is not something that was likely to go into a released version of the model, just because we were having all these troubles with sea ice expansion and shutting down the North Atlantic circulation. And so there was very little interest in expanding the sea ice. So what we did is made two modifications. Both of these modifications reduced the summer melt. And these modifications were made globally. No other tuning or modifications were made. So that was kind of neat. What we then have is the ability to try to compare these new simulations with tuned ice, which we'll just refer to as CESM2 tuned ice, with the CESM2. And here in this talk and in the paper we're writing, what we're comparing back to for CESM2 is not only the CMIP6 pre-industrial control run, but also the CESM2 large ensemble, which is not publicly available yet. And so I'll discuss some sea ice results from that here, but that's not publicly available and will likely be available in the summer, as noted by Hansi at the beginning. But what's neat for this comparison is that the first 50 ensemble members of the CESM2 large ensemble have the exact same everything except for these two melt parameters as the CESM2 tuned ice. And so we can compare these two ensembles, one with 4 members and one with 50, to try to assess what the impact of this kind of reduced summer melt is on the system. So we started by looking at the pre-industrial control run. This was a good sort of sanity check that, you know, both of these models are kind of not going off the rails. The CMIP6 CESM2 control run here is in black, and our tuned ice run is in blue. And you can see that with less summer sea ice melt, we do end up with a climate that's a little bit cooler in the global mean. But that the top of atmosphere energy imbalance is still really small, and this simulation is stable over multiple decades, centuries. So that's great. So that now we can start to look at the sea ice in these two pre-industrial control runs. And on the left here, I just have the Arctic. So we can see on the top the volume. So the tuned ice volume in blue is larger than the CESM2 default. So suggesting that this reduction in summer melting is, you know, increasing the amount of sea ice year round. And then also we can see that the late summer in particular, we have more extent and area in the CESM2 tuned ice experiments. So this is promising. Although this is the pre-industrial control run, we'll see this also, this phenomenology when we look at the present day. Although this talk is in the Antarctic section, I only have one Antarctic slide here, and maybe that's an advertisement for others who want to look at these simulations in the Antarctic. There is an increase in the Antarctic sea ice volume as well, and in the sea ice cover, which is less seasonal, just likely due to the geography differences between the Arctic and the Antarctic. We'll see from the comparisons later that the Arctic, there's really evidence for these reduced summer melt tuning parameter changes to have a good impact towards observations. And I would say the evidence for that is less clear in the Antarctic. We can also look at the spatial pattern. So here, looking at the September sea ice concentration and the March sea ice thickness for the Arctic. And so we can see, you know, in the late summer, we're getting a lot more September sea ice concentration along the margins, makes sense. And that the March sea ice thickness here, you know, it's about a ½ meter, sometimes even more than that, thicker. This is definitely interesting and has potential to impact the transition to an ice-free Arctic as we start to ramp up the forcing. So we're going to move on to the transient evolution and really ask, you know, how does this sea ice tuning, how does it affect the climate change and variability? And here again, this CESM2 large ensemble provides a really nice framework for comparison. We know there's a lot of internal climate variability, and with a large ensemble, we can really start to see, are there really substantial differences between the two? So again, the focus here is on the Arctic. So similar to the pre-industrial control, and maybe I'll go through these quickly because I already hinted at this result, but there's, in the present day, there's more sea ice volume in the tuned ice experiment. And then here on the right-hand side, this is kind of like our money figure, our nature figure, yay, it worked. We're getting a lot closer to the observed area and extent with these tuned ice parameter changes. If we look at what this looks like, again, on the top for September sea ice concentration and the bottom for March sea ice thickness, we can again see, you know, more late summer extent, more cover with the tuned ice, and also this thicker March sea ice at the beginning of the melt season. And we can see how that evolves through time, which is kind of, we can see here in the C and G panels here, this is for the 2030 to 2049 period. And we can see basically that there are much smaller differences in the March sea ice thickness by this time period. But there's still differences in the late summer sea ice extent. So I think this is just showing the impact of these changes on the summer melt. But somehow by the next March, those differences have not been remembered. And I think this is hinting at this transition to a seasonally ice-free Arctic. And then on the right-hand side, we can see basically that transition has fully happened. So by 2050 to 2069, there's very little difference between these two simulations, both in their March sea ice thickness and their September concentration or extent. The only differences are in the Canadian archipelago, where this is kind of the last remnants of where sea ice lives in a transition to a warmer climate. So now comes the fun of using the large ensemble. So here, this is from the CESM2 large ensemble, all 50 members that used in this study, and then the observations on top. And I know all of us are used to large ensembles more and more now, but I think it always is worth repeating that all we can expect from a model is that one ensemble member, the observations, lies within the spread of our model ensemble. And in this case, we can see that basically that's really not the case here. The observations are almost always on the upper end of the CESM2 large ensemble. And so even if we started adding 40 more members than what we had for CMIP 6 and in the analysis done in Patricia's paper, that's not helping us resolve this mean state bias. And if we look at the tuned ice, again, another one of these kind of nature money figures, yay, it worked, right? I mean, the observations are right in the middle of the tuned ice members. There's only 4 of them here, but you can definitely see hints that this looks more appropriate. And then we also looked at trends. So here I'm just, again, plotting the range that you get from the CESM2 simulations. And then the observations are just one line because there's only one realization of them. And we can see for the most part, actually, it's interesting that the range of trends between the tuned ice and the CESM2 large ensemble, they overlap, which really shows you that the internal variability is really large, and it's pretty hard to tell the difference between these two. The only exception here is this period where we have 20-year trends ending in, for example, 2010, where the ice loss appears to be a little bit less in the CESM2 tuned ice than in the CESM2 large ensemble. And I think this is due to a feature of the CMIP 6 forcing, which Patricia will talk about. But basically, the CESM2 tuned ice with its thicker ice is a little bit less sensitive to these kind of changes in the forcing that are happening here. And interestingly, the observations are largely consistent with both of these ensembles in terms of trend, just really showing you it's hard to use observations, and in particular 20-year trends, to constrain model simulations. There's a lot of variability. So continuing along this theme of there's a lot of variability, it's really hard to tell the difference between these two once you start to get a lot of ensemble members. Here, we'll just look at some standard CICE comparison metrics. This is the CICE sensitivity, which is defined as the change in extent per ton of atmospheric CO2, or the change in extent per degree global mean surface warming. And you can see in this bar whiskers is the CESM2 large ensemble, so really large range. And then we have the 4 ensemble members from the tuned ice. They are, for the most part, within the range of the CESM2 large ensemble. And then the 1 observations here in the dashed line. And so we can see, yeah, there are some changes, but it's really hard with so much variability in these metrics to use the observations as a constraint and to actually be very confident that we are seeing changes from CESM2 large ensemble to CESM2 tuned ice. One thing where we are more confident that we're starting to see a difference in these two is in the transition to a seasonally ice-free Arctic. Here, the CESM2 large ensemble has a huge range of this metric. This is in part to these CMIP 6 forcing issues and the thin ice in CESM2, which cause it to go ice-free, like last year or the year before. So totally unrealistic. We are not at ice-free conditions yet. But the CESM2 tuned ice goes ice-free later than the CESM2. And if you do some bootstrapping, you find it's really unlikely that you would end up with these members that are going ice-free so late. So we can say with a fair amount of confidence that having the thicker ice does delay the transition to a seasonally ice-free Arctic Ocean. But there's still a lot of variability in this metric. So then again, leveraging the large ensemble and trying to see what we can say about the real differences between these. So now instead of comparing to the observations, I'm really trying to ask just, are these two ensembles different? Obviously they have different ensemble sizes. So what I've done is for the CESM2 large ensemble, I've just bootstrapped that to end up with a range that's basically what you could get from randomly sampling 4 ensemble members out of the 50. And then I can compare that to the CESM2 tuned ice experiments, which do have 4 ensemble members. And so what we can see is that the CESM2 tuned ice does indeed have more sea ice than the CESM2 large ensemble. It's outside of the bounds of the internal variability. And that's also true for the March sea ice volume. We can also look at trends here on the bottom. So again, this kind of weaker sea ice trends, weaker sea ice loss in the tuned ice experiments around these this period with the anomaly in the CMIP6 forcing. I think that's due to this kind of thicker ice and it being a little bit more resilient. And then at some point in time, we have to lose that extra ice in the tuned ice experiment. And that happens here later in the simulation. So that's why we start to see these larger trends out here. So yeah, some differences, but I mean, for a lot of these records, you can see that, you know, for example, in the current time period, these two are basically indistinguishable if you use the bootstrapping to try to really statistically assess the trends and the trend differences. The variability is also different. We know the variability in sea ice is highly tied to the mean state. So here I'm just looking at the standard deviation in the September sea ice extent in these 2 experiments, again, using the bootstrapping method. And we can see the variability is actually less in the present day period with the thicker ice, and that transition to more variability and then the decline to no variability as you have no more ice happens later in the CESM2 tuned ice. So I'm not going to dwell on the non-Arctic impacts for 2 reasons. One, as I said, for the Antarctic, the changes are not necessarily favorable towards the observations. And so there's some interesting differences, but they're not kind of what the focus of this work will be. And then for the non-Arctic and Antarctic areas, so the extrapolar regions, the changes are actually really small. So the impact of this sea ice tuning is really small. And here I just show that in terms of the global surface air temperature anomaly and its evolution. You can basically see that the blue and the gray are right on top of each other. It is worth pointing out that the CESM2 tuned ice is cooler and it stays cooler. So there is a difference in the mean state, but it's again not affecting sort of the transient change. So I'll just summarize here. We're still seeing this issue of basically a thin ice bias in the CESM2 with CAM6. And we did these experiments, tuned ice, to try to remedy that. And we're seeing some really great changes in the Arctic that really lead us closer to observations. And that's really affecting the transition to an ice-free Arctic in the CESM2. It's happening later, and the associated warming is also happening later. But interestingly, we're seeing the trends are really, it's a lot harder to tell what's going on with them. And I think that's just because there's so much internal variability in something, even like a 20-year trend. The non-polar climate impacts are pretty small, which is, I think, an interesting result and a nice one in the context of model development, because you might be scared to try to apply these tuning parameters if you start to screw up the climate in the non-polar regions, and we're seeing that that's not the case here. So suggestions are very welcome. The simulations are, contact me if you're really excited about analyzing them, but they'll be available officially after the paper is submitted. So with that, I'm going to stop, and sorry, I think I've gone a little bit long, but there's so many fun results here, and yeah, I'll stop.
Thank you so much, Jen. Awesome. So Jen can take questions now. And one thing that I would like to say is that there is a question here in the chat from Jiangzhu, who asks how much this tuned ice impacts the ECS.
That's a great question. And actually, I'm going to turn it over to Marika or Dave, because they did some experiments to look at this, again, as a part of this, like, kind of vetting this configuration potentially to use within the CESM2 framework.
Yeah, my recollection from those is that it didn't have a very big impact on the equilibrium climate sensitivity. In 1%, I think it was, Dave, I can't remember if you did doubled CO2 runs or quadrupled CO2 runs, but it was in one of those configurations and it didn't have a big impact.
Right. I did do the 4 times CO2, which was sort of what we had done to assess equilibrium climate sensitivity in the core model. And yeah, there's very little change with that. So as Jen highlights, I think that these tend to be more localized to the Arctic, and the global implications are quite small.
Thank you.
I believe, yeah, right. Using the hand function. Awesome. Yes, please.
Jen, I'm wondering whether the changes you made with the CICE affected the atmospheric circulation at all within the Arctic, things like pressure patterns or wind speeds and the like?
Yeah, so I did look at that, just way too many figures to show on a talk like this. I would say the impacts within the Arctic, there are some, they're consistent with sort of the impacts of, more sea ice, reducing the transfer of heat from the surface ocean to the lower atmosphere, and that affecting the circulation in the fall in particular. There's no impact at all in the summer. So it's very consistent with kind of this idea that, in order to have an impact on the Arctic atmosphere from changing sea ice, you need to actually have transfer of heat from the surface up into the atmosphere. And that was happening, with this thicker ice. There was less of that in the fall, but nothing in the mid-latitudes. I mean, I did all of the statistical significance testing, and I think that that's pretty consistent with other work that's really tried to assess the influence on the mid-latitudes using a couple of models.
Nice, thanks.
I see Dave has a question here, Dave Bonin.
Yeah, hey Jen. I wanted to know, did you examine like the formation of North Atlantic deep water and the differences between these two simulations, or like large scale overturning?
I did not, but there's actually, stay tuned, because I shared these simulations with someone who, whose name I'm forgetting right now, but he works in South Korea, and he's looking at his name is on the first slide. Anyways, he's looking at that exact question in these simulations.
Cool.
Because they're curious about how the timing to an ice-free Arctic affects the North Atlantic overturning weakening. And so yeah, if there's some connection between the sea ice timing and that timing. But that's not something I've looked at.
Okay, thanks.
Okay, there is one more question in the chat for Jen, but in the interest of time, Jen, would you be able to answer that in the chat? Is that okay?
Sure thing. Yeah.
Awesome. Thank you so much.
Be in touch if you have questions. There's kind of a lot there, and I hope that you'll use these simulations. I know Dave has already said that there's interest within the CESM project to use them, but I think that they might be of interest to this group, especially.
Great. Thank you, Jen. Okay, so let us move on to the final talk before break. So this will be Hannah Director from the Colorado School of Mines, and she will be talking about subgrid scale sea ice leads in CESM.
Okay, can everybody see that?
Yep.
Great. Okay, so thanks for the introduction. I'm a postdoc at the Colorado School of Mines, and I'm excited to talk to you today about sea ice leads, and in particular, what kinds of features of sea ice leads are going to be subgrid scale if we're looking at a lower resolution model. So this is work in collaboration with Doug Nitschke, Marika Holland, and Cecilia Bitz. And I'm grateful to NSF for funding this work through the Math Sciences postdoc program. So what we have here is a high resolution output from CESM. This is in a control run, and this is just a 15-day snapshot of daily sea ice concentration data. And I want to draw your attention to these long, skinny areas where you're seeing low concentration. And those are what we consider leads. So the National Snow and Ice Data Center defines this as narrow linear cracks in the ice. And so we can see this in the high resolution model output. Unfortunately, if you go into a lower resolution model, you don't see these features. And so what today's talk is going to get at is kind of early stage work to start to think about how we can understand this lead behavior in the high resolution model and potentially opening pathways to correct some of the errors that we see with that. So the first thing to understand leads is to actually be able to identify them in data. And there's been a fair bit of work in this regard, particularly in terms of deformation data. And so these methods have looked at linear kinematic features. And so that includes leads, but it also includes pressure ridges. And so the two aren't necessarily distinguished, but both leads and pressure ridges show this same long, narrow structure like this. And there's been some algorithms developed to detect LKFs, and they've been focused on deformation data. So how do you take deformation data and how do you extract the leads from them? And the algorithm that most people are using right now is Hutter et al. 2019. And you can see the output of this on the right of the screen. This is a figure from their paper. And so you can see these kinds of structures. This is for a single time point that are long and narrow, but we don't necessarily know if those are leads or pressure ridges. So what I've been working on is developing an algorithm to find the leads specifically and to find the aspects of the leads that are subgrid scale. So the idea of this method is we're going to identify what aspects of the leads would be subgrid scale if we were looking at a lower resolution model. And this algorithm is also going to differ from that of Hutter et al. In that we're not going to use the deformation data. We're going to use the ice concentration data alone to try to find the leads. And so this kind of motivating using a different approach is a couple of things. One, we're really focused on what would be subgrid scale. So this will allow us to isolate what aspects of the leads are not being seen in a low resolution model. It's also potentially useful to build our lead finding algorithm using just the sea ice concentration data. And one reason for this is the potential to turn around and then simulate the sea ice leads, and particularly in concert with a model that's running with other features. And that's because it's easier to modify the concentration distribution in something like CICE than it is in, to modify deformation. And then lastly, looking in this way, it's easier to separate leads from pressure ridges. So if you look at the output of the Hutter et al. Algorithm, it'll tell you where the LKFs are. It won't necessarily tell you if they're a lead or a pressure ridge or some combination where they're connected. So most of the work I've been doing is developing an algorithm to isolate the leads, but this is why we want to do this. So the basic idea is we want to identify the features of the leads that wouldn't be able to be seen in a low resolution model. So we start with a high resolution model output, and we look at every grid box and we average it with its neighbors such that it's now at the resolution of a typical low resolution model. And so when you do this, then you get this, smooth concentration field, and you can see right away that you're missing some of the small scale features. You're not seeing any of those narrow cracks. And then we can look at the difference between the high resolution output and this smooth field. And you can see that the differences show up in the edge of the ice. And we have the areas where it's lower and higher. And you can see that in the colors. And if you zoom in a little bit on a particular section, you can see that these features do show this like LKF-like structure in that they're long and narrow. And you have some areas that are leads where you've got this negative difference. And some areas which are pressure ridges where you have this positive difference. And then so once you have this difference file, we can then look at isolating the individual leads. So we can identify sets of contiguous grid boxes that have these negative differences. And then each one of them, we can trace a path through it. So we pull out a set of grid boxes that are connected and have this negative difference. And then we can fit a curve through those. And so what this curve gives us is basically the center of the lead. And it can be a curved path through it. There's some things you need to work out in terms of branching and in terms of, is this two leads that are really close together, or is it one lead, and how do you make those determinations? But the gist of it is that the algorithm comes through and you can run the whole output and see where the leads are in a relatively defined way of how you're looking at the leads. And so you can zoom in again and kind of see the features more clearly. And you can see they align with where these differences are. And then finally, what this method allows us to do is we know where the center of the lead is. So then we can look along perpendicular to this center of the lead and look at how the width of the behavior is. So we can look at, do we have just a negative difference where there's a lead, or is there maybe some, as we move outward, is there some of the ice being pushed up on the sides? And how is the width and behavior of this? So that's kind of what the method allows us to do. And so the way we're going to use this data is to analyze leads under a range of different settings. And so this is ongoing work, so I don't have a ton of results at this point, but we can look by having an efficient algorithm to extract these leads, we can look at what the lead patterns look like under different scenarios, what's going on in the Arctic, what's going on in Antarctica, how are things behaving in the current time point versus how are they behaving in the future. And we can also look at seasonality. Similarly, we can look at the individual features of the leads and how they're potentially varying under these different settings. So what's the distribution of the lengths of the leads? What kind of branching do you have? So sometimes you have one lead that branches off into another. And how do these widths behave? And particularly, are you seeing these leads on one place, and then as you move farther out, do you see a pressure ridge? And then finally, we can look at the conditions which precede or a lead formation. So do we see, leads forming in thin ice? Do we see leads forming with particular atmospheric or oceanic conditions? And so the goal of having all this information is that there's some potential that we could simulate these differences in leads from the high versus the low resolution data. So if you understand all of these factors that are related to what's giving you lead behavior that you can't see in a lower resolution model, then you can kind of flip this algorithm around and generate leads that reflect what you would expect to see. And so the big picture goal of this would be eventually then to try to use this information to improve low resolution parameterizations, in particular, potentially using them stochastically because we know this behavior isn't going to be reflected at the lower resolution. So thank you for listening, and I'm happy to take any questions.
Thank you so much, Hannah. That was great. Letty has a question for Hannah, which she has put in the chat. She asks, how expensive is this method? How much data do you think is practical to process?
So at the current time to run, so it takes a max of about a minute on one core to run this algorithm for either the Arctic or Antarctica. It's often lower because sometimes of the year there's very few leads. And so those months, the algorithm will go through in like 5 minutes or so. So I've run about 500, but I think it's very plausible. And I think we're thinking about running thousands, if not 10,000 cases. And so, there are cases where it's going to take a minute to run through it, but there's lots of cases where it's also going to take a few seconds because there aren't very many leads.
So, Hannah, I had a question. Do you think it would be practical to apply this to observed data, like ISAT-2 data, and would that help you get some insight on what biases might be even in the high resolution model?
Yeah, so I think this would be very plausible to run in, relatively high resolution observational data. Nothing about the algorithm is specific to it being a, being model output. There is some distinction between, are you looking at differences between high resolution and low resolution data, or are you looking at observations? But the algorithm has been written as, generally as possible so that hopefully we can apply it to a large amount of data. Yeah.
Awesome. Thank you so much, Hannah. There are actually a couple of more comments and questions for you in the chat, but I'm going to say, let's go ahead and break until 11:05 Boulder time. So let's give ourselves 10 minutes for whatever we need to do. And come back here. And I'd like to point out too that if the speakers who have already gone, would you be able to send your talk slides to Elizabeth Faircloth so that she can post them? That would be great if you could do that. So anything else I need to say before we go to break, Marika and Dave?
I don't think so. So 10 minutes. Do what you need to do.
Awesome. See you soon. Thank you so much, all of our morning speakers. You're excellent.
Hey, Marika. Oh.
Yeah.
Just wanted to let you know that I don't think that I can send you my slides to post.
Yep. No, that's fine. I think, we can, so maybe if other speakers are online and they have slides that they don't feel comfortable sharing or they're not allowed to share for various reasons, that's fine. We will just post your abstract in that case. So, but if you're able to share your slides, we'd love to get them and post them. So yeah, thanks, Jen. And others.
Jen, is it possible that you could even remove a couple of the CSM2 large ensemble slides and just post the rest of the presentation?
I could do that. I mean, the pre-industrial control stuff is all released and out.
Okay. Yeah.
I think that'd be helpful, especially since there were some questions about the maps and yeah. Okay.
So Matthew, I don't know if you've been on all morning, but we are running a bit behind. So
yeah, I'm here. I've been paying attention.
okay, sounds good. You're not on a treadmill like CICE is.
I'm not. Although I keep thinking what a great idea that is. I just
Right.
Okay, should we get started?
I think that sounds good.
Awesome. Great. Okay, so we are now moving into talking about our amazing colleagues who have done some observations in the Arctic this past year. So I'm going to turn it over to Matthew Shoup, followed, I think, closely by David Clemens Seawall. And they are going to tell us about both atmospheric and CICE observations in the Arctic from Mosaic. And I guess go ahead and post questions in the chat, but I think they're going to be going continuously through. So we'll just let them do that. And then we'll kind of take a barrage of questions at the end. All right, great. Thank you.
All right, sorry, I'm just get my screen up here. Does that look good to you all?
Looks great.
All right, let's need to adjust something for myself here. All right. Well, thanks everybody for having me. I'm Matt Shoup, University of Colorado in NOAA here in Boulder. And I'll just provide a kind of brief overview of the atmosphere observations during Mosaic, the multidisciplinary drifting observatory for the study of Arctic climate. And I hope that most of you know something about this. I'm not going to provide a whole lot of background, but let's see here. Oh boy. Something's not working. Oh, there we go. All right. So my one slide on the plan was to take the RV Polar Stern, the German icebreaker from the Alfred Wegener Institute, and go drive it up into the Arctic sea ice in the fall and park it in the sea ice, and then set up a whole array of observations on the ship, around the ship, in a network extending out about 50 kilometers in each direction. And then over the course of the ensuing year, this is going from September 2019 to September 2020, drift with the transpolar drift across the central Arctic out towards the Fram Strait. Over the course of the year, have a number of different resupply vessels come and go, bringing food, fuel, swapping crew, etc. And the plan was to have some aircraft flights and missions along the way as well. So that was the concept going in. And some of it actually worked out this way, pretty amazingly. So just very briefly, here's an actual map of the actual drift that happened, and you see a nice picture in the background there of polar stern installed in the ice. So this figure shows the actual drift. You see the dotted red line heading out from Norway and installing on the 4th of October was the kind of start of the drift in the ice pack. I've put on here for reference a couple of ice edge boundaries. You can see the September sea ice minimum during the Mosaic year, and you can see the actual edge of the March maximum as well, just for reference. And these solid lines are the drift of the polar stern across the transpolar drift along its trajectory. Each of the different colors are different legs of our operations. We planned on 6 legs. We ended up with 5 legs. And the drift happened much faster than we thought. We used data from the previous 12 years, kind of observations from satellite to kind of project where the drift would happen, how fast it would happen, where the ship would go. And none of those 12 years of data suggested that we would go as fast as we actually did. That's, of course, due to the large-scale circulation, the very high Arctic Oscillation Index that occurred in early 2020, anomalous winds, and a lot more. So that's a whole nother story. Very interesting one, but nonetheless, the ship drifted way faster than we anticipated. And so well before the end of our year there, by the end of July, we had actually reached the ice edge. And in order to continue for our full year, we had to reposition the ship, take it back up near the North Pole, and capture the end of the melt season and into the freeze-up transition. So that's kind of the general concept for the whole drift. One note is that in between the green and blue legs, which is between legs 3 and 4, we actually had to take the ship out of the ice to facilitate the rotation of people. And this is due to the COVID situation and our inability to use some of the vessels that we had planned to use. And so we actually had an interruption of some measurements at a really important time. This is right at the melt onset. Fortunately, we did have a number of measurements that were left in place, making kind of autonomous measurements. But yeah, we had to take the ship out for approximately a month to facilitate that rotation. So we kind of followed the trajectory we anticipated, but there were a lot of challenges along the way. And the ice was very dynamic. We moved very rapidly, and we had some interruptions along the way, including things like cancellation of some planned aircraft missions. So a challenge, but nonetheless, we were very successful, I think, in collecting some really fantastic data. And I'll just give you an insight here into some of the atmospheric measurements that were made there. To start out, here's just our general schematic of the Arctic atmospheric system and the kinds of things that we wanted to look at, the kinds of processes we wanted to examine. And there are a bunch of related puzzle pieces, or questions that we had that motivated our science. And I'm not going to go into these here. You can look at the slides if you want later. Generally, though, we're very much interested in how atmospheric processes drive and impact the vertical and lateral exchanges in the Arctic system. So this is the movement of energy, momentum, gases, particles, moisture. How do things move around in this coupled system? And that's really what motivated our design here. So now I'm going to go through and just kind of show you some of the types of observations. And I'll start with where within the Mosaic constellation was the atmosphere team making measurements. And here's just some nice pictures. We had a lot of measurements that were made on board of the ship itself. Many containers. We had a whole DOE armed facility on board. We were launching balloons from on board. So lots of measurements were on board the ship, and therefore they were kind of robust to all the ice dynamics that challenged operations out on the ice itself. We also had a lot of measurements out on the ice. So there's some pictures of some folks making flux chamber measurements that go around and make measurements at different places on the ice. We had permanent installations on the ice. Met City, for example, had lots of kind of quasi-permanent installations about 500 meters away from the ship to make undisturbed measurements. There was a balloon town where we launched tethered balloons for profiling the atmosphere. These were all kinds of activities nearby the ship within a few hundred meters. Additionally, somewhat more distributed, we flew a number of unmanned aircraft, and you'll hear from CICE about some of that, providing some spatial context. We had a distributed network, and that's the kind of bullseye map you see here. The ship, the Polar Stern, is at the star in the middle, and you can see these circles emanating out to, the outer circle is 40 kilometers spatial distance from the ship. And all these different shapes and colors are different sites in our distributed network, with lots of different kind of buoy and semi-autonomous measurements. And the atmosphere team also made some measurements, especially at the L sites in this distributed network. And then we also did have some aircraft operations towards the end of Mosaic. Unfortunately, the aircraft was unable to actually reach the Mosaic installation because it had moved further north by that time. So I'm going to go through some of the different kind of areas of the measurements. The first here is profiling the atmospheric structure. You see some nice pictures here of some of the different approaches we took: towers, tethered balloons, other kinds of balloons, LIDARs for looking at temperature, moisture structure in the atmosphere. Here's just a nice example of one of those things. This is relative humidity from a LIDAR continuously over time. So this really allows kind of the first long-term continuous profiling of the humidity profile in the Central Arctic, which really gives this nice insight into air masses and their evolution. We had a 4 times daily radiosonde program. Occasionally we launched even more than that. That's, again, a fantastic data set that we've never really had. That many radiosondes over a whole year in the Central Arctic. So that's going to be a huge opportunity for looking at the impact of those radiosondes on assimilation and many other applications. We had very detailed near-surface boundary layer observations from towers, from fiber optics, to look at the near-surface stratification of the boundary layer. And we had hundreds of hours of tethered balloon and unmanned aircraft profiles, again, providing unique insight into boundary layer structure, aerosols, and a lot of other properties in the lower atmosphere. Continuing with profiling of the atmosphere, but looking here at dynamics, we had the most comprehensive wind program to ever be assembled in the Central Arctic, with 9 different complementary perspectives. We're talking Doppler LIDARs, Doppler radars, SODARs, tethered balloons, all kinds of platforms for looking at winds. And it's actually a really interesting story to look at things like low-level jets and the interaction between the atmosphere and the surface. So again, a very comprehensive approach here. Gases and gas exchange. We made the most precise gas flux measurements ever made in the Central Arctic to enable the detection of very small fluxes of CO2, methane, ozone, DMS. These, of course, are linked in with lots of biogeochemical processes, ecosystem research. And one of the important things, of course, is that these fluxes are very small, but we were able to actually measure those small fluxes. Aerosols and their precursors. I can't even name all the firsts here. We had a very extensive suite of aerosol measurements from a number of different contributors. And there were so many firsts, especially wintertime observations where there's never been anything so sophisticated in the Central Arctic sea ice before. These measurements are providing substantial insight into things like new particle formation and the origin of particles. How much of an aerosol source is there locally within the ice pack, especially as the ice pack is changing and exposing more open water, versus the influx of particles coming with kind of longer range advection? So that's a really great question that will really have great data to look at from a number of different perspectives. Cloud properties and processes. Again, the most extensive suite ever assembled for looking at Central Arctic cloud properties. This is in large part due to the ARM mobile facility on board, which has a huge suite of measurements, but also other collaborators like the Tropos Institute from Germany. We're already deriving cloud products that will be available. And we see clear fingerprints of, for example, strong cloud impacts on the surface energy budget and other perturbations there. And there's lots of cloud modeling projects that are starting to spin up. Just a nice example, looking into the data, these kind of 4 strips here are the first leg of mosaic. So this is the kind of fall into winter transition. And these are observations from a cloud radar. So vertical extent of clouds over time for the whole leg. And I've kind of highlighted a bunch of different things. We see all kinds of cloud structures, mixed phase clouds, low level clouds, storms. We can see snow events, all kinds of different things happening in the cloud field that will be interesting to dive into in the context of our analyses. Precipitation, again, many perspectives on snowfall. And this, of course, is really important for things like linking to moisture in the atmosphere and cloud processes, but also then making the link to snow on the surface, which we all know is an evolving and really important theme going forward. We'll hear a little bit more about that, I'm sure, in the next presentation. But we're measuring with radars, with gauges for looking at mass, for looking at fall speeds of particles, for looking at habits of particles, blowing snow, all kinds of aspects of the snow that will be really important in linking the atmosphere and the surface. And the surface energy and momentum fluxes. We had continuous heat and momentum transfer. Even when the polar stern had to leave, we were able to keep one of our flux sleds that we built in Boulder out there to monitor the energy budget transitions as we moved into the spring melt transition. Again, new insights into how clouds are impacting the energy budgets. We're able to link things like the winds in the atmosphere to ice motion through momentum transfer. And some of these data were used in kind of near real-time model evaluation, which I'll show here. This is work from Amy Solomon, where we're taking a lot of the measurements from some of our stations. Here's just an example of distributions of net long wave radiative flux at the surface compared to, this is a model that we run over at NOAA to look at how those compare. Of course, we can look at time series of different parameters. This is near surface temperature gradient and evaluating how a few different models, coupled models are representing that. And then importantly, we're looking at process relationships. So here's the relationship between the net long wave radiation at the surface and the near surface temperature gradient between 2 meters and the surface to look at relationships in the data here, the observational data in these kind of gray spots, but then a bunch of different models and how they handle these kinds of process relationships. So this is another use of these great atmospheric observations. So just to summarize here, we had a lot of unique successes out there. There's a fantastic data set for understanding the Arctic atmosphere and it coupling to the rest of the Arctic system. I think we know based on the utility of the Shiba data set from more than 20 years ago, I think we know that this mosaic data set will really be groundbreaking. It will really be a foundation for all kinds of work in understanding the system and improving models. We have really the most comprehensive atmospheric observations that have ever been made in the Central Arctic, with more than 200 instruments operated, capturing as many as 20 distinct cyclones that came through. A lot of the measurements were on board the ship, so that enabled them to have continuity in spite of things like ship, the ice dynamics and ship movements. We did have a few aircraft flights that can be linked via trajectories to the observations made out at the ship. I showed some near real-time model evaluation. We're also developing what are called merged observatory data files. This is a project that's been very closely linked with the Polar Prediction Project and YAP to pull in observations. We're starting in the atmosphere, but we will also want to include the ice and ocean into a kind of consistent format for comparison with operational models. And so those data files, we expect to have some ready here pretty soon, at least the early versions of those, which would be very useful for comparing with a number of different model simulations. And the mosaic data in general are starting to become available through Pangea, through the ARM archive, through the Arctic Data Center in the US and other sources. So we're very active at getting our data already to get out there in publications and archives for people to use. Please feel free to contact me if you are interested in engaging with data. I know we have a number of mosaic investigators here on the call, but we really do want to encourage broad use of the data. You know, there are some subtleties of the data policy that we have to work through, but my goal is to really ensure that this community and other modeling communities can really harness this great observational data set. So with that, thank you.
Thank you so much, Matthew. And now we will move on to Maddie Smith and David Clemens Seawall, who will continue presenting on Mosaic, and this time in terms of the CICE.
All righty. Can people hear me?
Yep.
Yeah, I can hear you.
Oh, your slides just disappeared though.
Thanks. Yeah, Maddie's actually gonna drive for the slides. So perfect. Thanks.
Okay.
Maddie.
Does this look right, or do these need to be swapped?
They look good. We're seeing like the slide shoot.
Okay.
You.
Cool. Yeah. So David and I are kind of presenting in tandem. So he's going to take over a little bit, and we're going to give kind of a whirlwind tour of some of the ice observations following on from that. So I'll let him.
Alrighty. Yeah. So thank you for having us here, and we'll just get started. Go ahead. Next slide, please. So Matt already gave a wonderful introduction to the Mosaic project, so I think we'll just skip straight through this one and the next one. And
I guess I did just want to mention here that if particular, I mean, Matt already talked about this a lot, but we did have a few interruptions in the data set, but we do still cover the annual cycle. And the other thing I think that is particularly relevant for the ice time series is that there was a lot of dynamics during Mosaic, which definitely interrupted some of our on ice work. But is also something that's kind of interesting in the observations. So.
Awesome, thanks. So, yeah, so this is the PROMISE project is a group of really observationalists and modelers between Dartmouth, CREL, NCAR, and UW. And so you can see all of our smiling faces here. We were very fortunate in that we had someone on the ice on Mosaic for every single leg. So that gave us a lot of continuity in our observations. And Maddie, can you go to the questions? And so the core of our project, where we're driving at three big questions, and all of these had been identified previously as areas of potential improvement in the CESM and other climate models. And so these questions are, what's the role of snow properties in controlling the mass balance and shortwave radiation budget? Then moving on into the summer, how is solar energy partitioned and what is its fate in the seasonal ice system? So this is expanding on research that was done on Shiba in many ways. And then finally, how is energy partitioned between the ice bottom and bottom melt and lateral melt? And how do these processes affect ice-ocean energy exchange? And so as Maddie said, I'm going to start in the first part of this talk and focus on our observations in the winter, and mostly question number 1. And then Maddie will take over and address 2 and 3. And so snow on sea ice, I think as everyone here likely knows, is really interesting and really important to the climate system because it has 2 competing effects on ice mass balance. Snow is an excellent thermal insulator, and so in the wintertime, it tends to impede ice growth. Meanwhile, snow also has a very high albedo, and so in the summer, the snow cover will protect the ice from surface melt. And so as the PROMISE team, we were focused on sort of 4 core measurements looking at the snow cover. First off, we were looking at where did snow redistribute and where did it accumulate through the terrestrial laser scanning data. We also looked at, as part of the snow budget, at snow loss into leads. We looked at the snow and ice mass balance through a stakes data set. And finally, we looked at the albedo of the snow. And so I'm going to talk mostly about the measurements that our group made, because that's our what we know well. But I just wanted to point out that I think as Matt kind of highlighted in his talk, one of the strengths of Mosaic is that there are a lot of coincident measurements that we'll be able to use to really understand this system better. So these are just listed some of the coincident measurements that were made with these data sets. Next slide, please. And so the terrestrial laser scanning is really the workhorse of our snow accumulation and redistribution data set. This is a technique that allows us to make maps of centimeter scale changes in the snow surface on areas of hundreds of meters. Next slide, please. And so one of the things that I think is really cool about this data set is that it lets us go from the bird's eye view that you might be used to looking at as a modeler and actually go down to the perspective of an observationalist looking at the surface. And so in this rendering, where I'm showing the sea ice topography, in this case colored by height, on an area about 200 by 300 meters. And the end of this animation, you're standing just 2 meters off the surface. So one of the things we think we'd like to share with anyone, especially in the modeling community, in addition to the data products, is looking at what does this environment look like from a human perspective. Here's just another example of this kind of visualization where now the colors are indicating the accumulation. And so on the left side of this ridge, you can see a large snowdrift that formed in a recent snowfall and redistribution event. Next slide, please. So in the interest of time, I'll sort of skip through this, but our preliminary results suggest that snow redistribution and accumulation in the winter is very heterogeneous, and much of the surface doesn't experience much, if any, change. Next slide, please. However, the areas that do experience a lot of change are in the vicinity of ridges. So ridges create a large difference in the snowpack, and we see a lot more snow accumulating on their lee sides than out in level ice areas. Next slide, please. Another aspect of the snow budget that currently has is an area of improvement in models is windblown snow loss into leads. And one of the challenges here is that there simply aren't a lot of data sets on snow being lost into leads. And so to address this, we collected ice cores, or transects of ice cores from leads that formed under a variety of conditions. And we used the stable water isotopes to look at how much snow was actually incorporated into that lead ice. Next slide, please. And so we don't have the data back yet from the lab, but just anecdotally, the kinds of things that I expect to see are that I think in most of the leads we saw, probably not that much snow ended up actually incorporated into the lead ice. So this upper left image is an example of a typical ice core, where the surface is on the left side of the image, or the upper surface is on the left side of the image. And here, there may be some snow in the upper 5-10 centimeters, but there's not much snow overall that got incorporated in the ice. However, we did have one very warm storm event where I think we did get a significant amount of snow getting entrained in the leads that formed during that event. And so this provides some kind of examples of end members for how snow may or may not be getting into leads. Next slide, please. Finally, I'll just close this section by talking a little bit about our mass balance measurements. These are point measurements of changes in ice and snow thickness. Next slide, please. And the real strength of this technique is that by measuring separately the bottom melt and the surface melt, we can get a closer look at the processes affecting ice melt, especially in the summer. Next slide, please. Well, just starting with the winter data, throughout the winter, we installed stakes on a variety of different ice types, and we saw growth across all of them. Next slide, please. And this is just a very preliminary look at this, but the patterns are largely what you'd expect. We see ice growth rates are highest in the winter when it's cold, and then as the spring goes on, they taper off. By the time we left the flow for the transition in May, ice growth rates across all ice types had dropped to zero. So with that, thank you very much for listening, and then Maddie will take it away to talk about the summer season.
Yeah, so David's, I think, set up really well the importance of the kind of feedbacks associated with snow throughout the winter and into the spring. And then a large part of our observations were also focused on the summer evolution, where snow also plays a big role in the kind of transition into melt and driving how that transition occurs. And then all of the albedo feedbacks that happen throughout the summer, where of course the open water formation, it drives a large albedo feedback that we think about a lot, but there's also lots of other kinds of feedbacks associated with the surface change, from the snow melting and initially reducing the albedo to the kind of formation and expansion of ponds, and also the ice kind of thinning. So we made a lot of our observations throughout the summer season focused on understanding these feedbacks in ways that are hopefully useful to improving representation in models. And so kind of building on the last slide that David showed, these are some results kind of looking at some of these point measurements of mass balance changes throughout the summer. And so again, these are preliminary, but throughout the summer, we were on a slightly different location than they were over the winter, just nearby, but we had some new stakes that were installed kind of relatively early in the summer in June. And so these were on a mix of second year and first year ice. And so one comparison I want to point out here is that the second year ice, which is the yellow, we did see it melt faster than the observations on level first year ice. And also something that's not necessarily shown in these results, but that we saw is that we did have substantial or more surface melt than bottom melt. So these measurements do kind of allow us to partition out the melting into these different processes. We also want to think about the partitioning of melting in addition to this kind of one-dimensional perspective, also in the kind of three-dimensional perspective and the role of lateral melting, which I think is particularly something that had been identified as something that could use improvement in the models, as it's based on, generally based on kind of old empirical relationships that we hope to connect to other physical drivers. And so to do this, I guess this is just a figure of making, or a photo of making some observations in Leeds, highlighting again that the ocean is very dark, so it can absorb more heat near the surface. And so we made observations a number of times throughout the summer at different kind of lead areas around the flow, where we saw these really thin layers of fresh water accumulating. And so the kind of observations that we're making were very much in the vein of some things that were done during Sheba. So this plot on the left is observations from Sheba, where they saw this thin, fresh layer that was relatively warm, kind of up, you can see it's up to 2 degrees, accumulating throughout the summer. And then when that mixed down, it really accelerates lateral melts as it's accumulating, and then the kind of the mixing in of that layer that kind of forms throughout the summer affects the partitioning of basal to lateral melts. Yeah, so these observations are really focused on understanding how the heat in the ocean is partitioned between the lateral and basal melting. So the plot on the right is just some kind of preliminary profiles from the observations that we made during Mosaic, which I think generally show a similar story to Sheba, but we hope to kind of connect to different atmospheric and kind of ocean conditions to get a better understanding of what's driving the partitioning. So you can see there's kind of this thin layer, order of a meter, with some heat accumulating near the surface. I also just wanted to mention that something we saw that was kind of an interesting feature related to mass balance evolution was accumulation of fresh water beneath the flow, which during the summer we're normally seeing melt, and that's normally what we're observing. But this accumulation of this fresh layer from presumably the draining of ponds beneath the flow actually led to the formation of these false bottoms. And this has been observed kind of sporadically in the Arctic previously, but we saw it a lot of places. So one thing we're thinking about exploring with this data of these false bottom formations is kind of to understand better the impact that this could have on the overall mass balance in the summer, where instead of seeing melting, you're actually seeing some ice formation. Oh, I guess I'll just quickly play this video. Oh, it's not working. For some reason, it's black. Never mind, we'll skip it. It's a nice video showing the false bottom underneath the ice, but seems to be bad. So we'll continue on in the interest of time. I also wanted to highlight that in the kind of broader picture of mass balance, that one of the big tasks on Mosaic was doing what we called mass balance transects. And so these were large kind of hikes around the different parts of the ice that we were on. So this is just a map with the kind of the route around the flow that we're measuring the ice thickness and then the surface features. So both the snow or surface scattering layer depth, and then during the summer, the pond depth. And so these are results from Melinda Webster, who was kind of leading this effort during the summer. And so this plot is showing you the depth of the surface features. So we can see the melt ponds in this kind of darker blue deepening throughout the summer as melt is increasing. And then I think another interesting feature here is that we can see the kind of melting of snow, which is these red dots, but this is capturing both the snow and then after the snow has melted, the depth of that surface scattering layer from the melting of the bare ice. And so you can kind of see the snow melting away, and then after it becomes primarily the surface scattering layer, it's a relatively constant thickness on that surface. So I think those are kind of useful to put understand the broader scale of mass balance changes throughout the summer, and potentially, hopefully will also be useful for kind of validating and improving some of the model parameterizations related to these surface evolutions. So yeah, thinking about the kind of covariance of these different features, and then and particularly how that relates to albedo, which is what I'm going to talk about next. And also because we had different ice types represented on the flow and different ice thicknesses, we can think about how these different features evolve over different kind of ice types and ice thicknesses. So one of our, as I've already mentioned, one of the big tasks during the summer is understanding the evolution of albedo. Albedo is a really sensitive tuning knob in the CICE component of climate models. And so, and the Shiba data, which I think Matt mentioned, has been kind of one of the primary data sets showing this kind of full scale seasonal evolution of albedo. And so we made surface-based measurements of albedo throughout the summer on lots of different ice types. I'm focusing particularly on the surface measurements, which are in contrast to the data sets that Hai is going to represent or present next, and that some of the things that Matt also mentioned. And the goal of these is to have a high coverage spatially and temporally, to both have kind of generality, but also describe specific processes. And so for this, we laid out survey lines that are sampled every 5 meters. So throughout the summer, where these exactly were kind of varied throughout the different legs, but we usually had at least a few hundred meters on different ice types represented. And we made 2 types of albedo measurements, both spectral and then broadband. So those are shown on the left and the right. And we usually made these together. And then the real benefit of these kind of on the ground optical measurements is that they can be directly related also to coincident physical property characterizations. So this includes properties about the mass balance, where we had these kind of transects of ice thickness and snow thickness changing along these lines. Also more detailed characterizations of the surface, like the effect of grain sizes and kind of the snow structure. And then also kind of some of the ice coring work, which wasn't always necessarily exactly coincident in space, but kind of helps us understand the changing of the ice structure and optical properties relative to albedo changes throughout the summer. And this is largely, of course, the value of Mosaic 2 is understanding the seasonal evolution, but also in the context of all of the other components of the system. Yeah, and this is just a quick another table summarizing the kind of observations that we made and also comparing them to Shiba. So our observations of albedo were split over these three legs, which basically is just to say that we, similar to Shiba, had observations from April to September, but they did have these sorts of gaps in mid-May to mid-June because of the changes in logistics with coronavirus, and then at the end of July to August when the flow reached the ice edge a little earlier than expected. But we had observations over all these legs of albedo. And I know I'm going close to time, so I'll go quicker. I guess I'm just kind of highlighting legs observations from kind of the middle of summer, since that's when I was on Mosaic. And the map is probably less important, but I just wanted to show an example of we have kind of imagery from lots of different platforms of these different areas. And so we can see the spatial kind of over these areas, the heterogeneity in the surface where we have ponds forming. And so then looking at the data, we can see how it evolves, how the albedo is evolving over space and time. So this plot is showing the albedo along this line, which is shown in this image, and then the colors progress with time. So you can see initially there's already variation with those ponds that have formed, and then you know, the differences in albedo change along those different surface types. a perhaps easier, more useful way to summarize this data set is looking at averaged albedos over these kind of line averaged albedos, so over a kind of space that represents a more ice averaged albedo. And so this is showing the mosaic data set, which is the blue lines, compared to the Shiba albedo time series. And so you can see again here that we do have some spatial or temporal gaps, but it also compares quite well overall to the temporal evolution and spatial variability that we saw during Shiba, so where we kind of capture much of these sort of 5 phases of albedo evolution that were identified in the Shiba data set. And then in addition to looking at time series, we also well characterized albedos of different surface covers and specifically how variable they are. So we looked at bare ice, which is when after the snow has melted and there's this formation of the surface scattering layer. And this is comparing observations on 2 ice types on mosaic, so first year ice and second year ice, and then also comparing those with Shiba, which is the red line. And overall, we see that they're remarkably similar. There's almost no difference between the first year and second year ice on mosaic. So the albedo of the bare ice is relatively steady. In comparison, pond albedos are highly variable. And I think this is a key target for model improvement. They generally represent quite conservatively or high in the models. And so this just kind of shows the range of pond albedos that we observe. So there's some really dark ponds and some really light ponds. And so yeah, we can use those to kind of calibrate model representations. I also just want to mention that we had a kind of unique surface cover, which was sediment laden ice, which has kind of been very sparsely observed with albedo measurements. And so we observed kind of the evolution of that surface type, which has particularly high surface ablation. So you can see these photos are from the same location a month apart, and you can see it's really melted away. And then we also see signals of that in the surface albedo, where you have this, or spectral albedo, where we have this kind of peak associated with the sediment. Okay, and then we also had lots of other measurements that kind of captured short-term variability focused on different processes that might be important to albedo. So kind of related to atmospheric drivers. During the early summer, we had a kind of small snow event where we saw that kind of increasing the albedo on the short term. And then late in the summer, or kind of during the freeze up period, after the surface was snow covered, we saw the albedo decreased from a rain on snow event. So those are kinds of these small scale or short-term variability that we've captured with these events that might be interesting to think about how they can be represented in models. And then we had we did an experiment removing the surface scattering layer, so we can see this shows the dark blue is initial, and then this brighter blue is after we shoveled off the surface scattering layer. So we can kind of characterize to what degree that changes the surface albedo. And then we also had some 24-hour cycles where we really saw the short-term variability, which is overall relatively low in this case because it was cloudy. So yeah, okay. And then, yeah, so I think, as David mentioned at the beginning, these observations were all really motivated by things that had been identified as needs in the climate models and where there are still big uncertainties associated in predictions for the Arctic. So we've kind of highlighted some of the things that we think or that we hope to target with these observations for improvements in the models. But of course, we'd love to hear more ideas of things that we can do with this data. And yeah, we hope that this data will be kind of useful for decades in the same way that the Shiba dataset was for improving and validating the models. Okay, that's it.
Great. Thank you so much, David and Maddie. We really appreciate it. So we're running quite late, unfortunately. So what we're going to do is we're just going to have folks put questions in the chat. And so, yeah, feel free, please, if you could sort of take a look at what's being chatted about there and answer those questions, that would be awesome. And then I'm just going to hand it over to Gijs de Boer, who will be talking about the observations of the surface and atmosphere from Mosaic. And then we can sort of roll into our discussion where we will kind of talk very sort of broadly about incorporating these amazing observations into our models and thereby improving them. Okay, please take it away, guys.
Yeah, thanks, Hansi. I'm trying to share my PowerPoint, and that's the one application I'm not seeing on the share window. So please give me 1 second. Oh, there it is. Got it. Start on slide 1. All right, are you able to see that okay?
Yep, that looks great.
Great, thank you. So I'm going to give a quick overview, and I'll try to keep it as short as possible since we are running late, of some of the observations that we collected during Mosaic using remotely piloted aircraft. And I want to thank both of the previous presenting groups for their really nice overview of everything that happened. I'm going to keep it a little bit more focused on these measurements. This work is a collaboration between a group of people that are listed here on the slide, but it's easier to look at faces, so we'll start there. The core of this team was operating from the University of Colorado, and that spanned a variety of different groups on campus, including CIRES, IRIS, and RECOV. IRIS and RECOV are both engineering-centered teams working within the Aerospace Engineering Department at CU. Additionally, during the drift, we had a lot of help from a variety of people, but specifically Yule Smale and Andy were really big help to us in terms of our operation. And so I want to make sure that we recognize that as part of our team here. We had a few different primary targets during Mosaic, largely focused on understanding subgrid scale variability. One of those is really specific to kind of capturing highly detailed observations throughout the atmospheric column and understanding whether today's modeling tools are able to capture some of the features resulting from the variability that maybe they don't resolve. Secondly, observing and understanding variability in the sea ice and the surface and its contribution to energy transfer. And this includes both thinking about things like leads as well as just the variability in melt pond coverage and surface albedo. And then finally, understanding the impact of coarse vertical resolution in the models on kind of proper representation of complex processes occurring in the Arctic boundary layer. And let's see if I can get the slides to advance. There we go. So as I mentioned, Matt and Maddie and everyone already gave a nice overview of what Mosaic is. This is a map of the drift occurring throughout the year. The legs are colored by kind of a strange sequence here, but legs 1 and 2 are in blue. 3 is this tan color, 4 is orange, and then new leg 5 is purple. And I say new leg because, as you might have picked up already, COVID resulted in some shuffling of how the legs were supposed to be carried out. We were originally supposed to take part in 3 legs, ranging from early March or so to end of August. The good news is that the time that we spent on the ice still covered that range of dates, but because of the shifts in the schedule, the legs 3 and 4, excuse me, there was a gap in between. So we missed a little bit of time in the middle there, but this provides a nice perspective on where we operated during this campaign. And I'll get into the details of these 2 platforms in a minute, but the Data Hawk, which is a fixed wing platform looking primarily at the atmosphere, is represented by the green dots. And then the Helix, which is a copter platform, was operated where these red dots are during leg 4. So a little bit more information on the platforms. This is a picture of the Data Hawk. It's a very small fixed wing aircraft, about 1 meter wingspan. It operates for about 40 minutes, and certainly the temperature does impact that a little bit. So earlier in the campaign, it was a little less than 40 minutes, and towards the end, we were hitting that 40-minute mark pretty consistently. It's equipped to measure a variety of things. We have a Vizsla sensor here on the tail, almost, that measures temperature, pressure, and humidity. It's very similar to what is used in radiosondes. Additionally, we have up and downward looking IR sensors. These give us information on, when we're flying across gradients on the surface, very useful for sampling over leads, for example, as well as when we're flying under clouds. And so if you have a broken cloud scene, this helps you understand when you're under a cloud or when you're not under a cloud. And then finally, we have this fine wire array here in this tube, and that measures at very high frequencies temperature and velocity to give us information on turbulence in the atmosphere. The primary objectives for the Data Hawk 2, obviously this platform sampled in the atmospheric boundary layer. We did a lot of flights between the surface and 1 kilometer or so. And it was really, again, primarily meant to help provide measurements to improve model representation of key processes and also advance our understanding of energy transfer between the surface and overlying atmosphere. So I'll give just a couple of slides of examples of the sorts of data we collected. These are the temperature profiles that we captured during the 2 legs that we were present. Again, you can see kind of the gap in the middle here between legs 3 and 4. There were certainly profiles that fell into this range. We just weren't there to measure them at that time. You see a lot of complex structure, a lot of strong inversions, particularly down near the surface, and some pretty significant warm air intrusions in the later part of the campaign, where we saw temperatures a couple hundred meters above the surface, almost extending to 15 Celsius, whereas the surface is kind of constrained to that near freezing point. Additionally, I mentioned that we were targeting leads. We didn't have a ton of leads to sample, but we did conduct some flights, and particularly Gina Yosef, who's on the call with us here, was out there conducting these flights, and the objective was to collect both horizontal transects at low altitude over the leads in the ice, as well as profiles on either side. And we're just starting to dive into these data, and we're very much in the middle of quality controlling the data and getting them ready for publication, but trying to understand kind of the impact in terms of transfer of energy from the lead into the atmosphere, what the net impact is on the temperature and humidity structure on either side of the lead. And so this is one area that we're starting to make some progress on. The other platform that we deployed during Mosaic was a hexacopter called the Helix. This is a system that's equipped with a few different instruments. Again, we had a pair of those Vaisala radiosonde-like sensors on the arms out here in these casings. These are protected from solar exposure and at the same time ventilated by the propeller wash coming down through the sensor housing. In addition to that, we have these equipped with two gimbals, one on top, one on the bottom. The bottom gimbal held both a Kippenzonen pyranometer as well as a multispectral camera. So we collect the imagery of the ice and at the same time measure the reflected broadband solar irradiance from the surface back up towards where the copter is. And then we also had a gimbaled pyranometer at the top to see what sort of incoming solar irradiance was present at any given time. And the primary objectives of this platform included providing measurements of surface albedo and sea ice and melt pond fractions over, again, leg 4. Originally, this was supposed to be legs 4 and 5, kind of from the pre-melt season through the summer. It turned out that we pretty much started sampling just after the start of the melt season with this platform because of the gap in the data set. But still collected some really neat data, and I'll jump into that a little bit here. This is an example of the sort of measurements that we collected from this platform. In the bottom left, there's a video of the camera imagery over time. And so you can see we're flying over the sea ice surface here. This is sped up. The time is in minutes, so you can see we're running this a little bit faster than real time. But along the way, we're capturing imagery as shown on the far right side across 5 different spectral channels, as well as albedo observations from the pyranometers on board. So we're working to put all these pieces together now, and Jonathan Hamilton and Radiance Calmer, I think Radiance is on the call, I'm not sure if Jonathan is, are spending a lot of time right now quality controlling the data and stitching all the imagery together for public consumption. Additionally, some of the flights were focused on collecting kind of detailed observations over specific surface types. And so this is one flight example where a few different surface types were targeted, including specific melt ponds, ridges. Maddie showed an example of some of the sediments of the dirty snow, as that's our technical term for it. And then things like cleaner snow, white snow, and the ocean near ice ocean surfaces. And another thing we were interested in targeting is trying to understand kind of the scale components here. And so this flight is one where we would be at a gradient or across a variety of surfaces. We do some sampling down near the surface to look at how much variability we see when we're flying at 2, 3, 4, 5 meters, very close to the surface. And then as you increase altitude, things start to kind of come together, right? You get more of a representative sample across the scale of what that sensor, which has a hemispheric field of view, is seeing. And so far, we're finding that in terms of albedo, things tend to converge around 30 meters from the surface, where we start to see kind of a uniform value. And we're working with a group from the Finnish Meteorological Institute. They've also conducted similar flights to try to nail down exactly what this looks like and to provide some context of scale of how the albedo is varying depending on how you're looking at it. So I just wanted to put one slide in here about engagement with modeling groups. It's been a while since I've been part of this meeting, maybe 2 or 3 years, I don't know, but it's really nice to be back here. And I think that there are some really unique opportunities to kind of engage and connect with the measurements that we're providing, but all of Mosaic. You saw the really nice observations that the other teams were just presenting, all the other groups were just presenting. But some ideas specifically on the UAS measurements, we're very much interested in trying to think about whether these observations could be leveraged to develop case studies to try to target specific phenomena of interest, whether that's evaluating boundary layer parameterizations or trying to understand whether cloud cover in the model does the same thing as cloud cover in the measured atmosphere, things like that. Additionally, working to both evaluate and help to develop existing parameterizations. We've had some nice discussions with the CICE team about, or nice discussions, one preliminary meeting, let's put it that way, with the CICE team about how these observations might be useful for some of the work that they're planning to do on updating the parameterizations in the CICE model. And additionally, getting back to the leads, we've had some nice discussions with a group at Utah to understand, try to link the UAS observations with their LES output and see whether they're seeing kind of similar scales and the impact of the leads as we measured over the course of the campaign. So I think, speaking broadly here, it would be really nice if people see opportunities for using these measurements, for engaging with these measurements, please reach out to me. I'm happy to try to develop those collaborations and partnerships. It'd be great to find as many uses as possible for the data that were collected. So quickly to summarize, the operations that I just gave an overview on represent some of the first successful extended deployment of small UAS in the high Arctic. People have flown limited numbers of flights here and there, either with research cruises or with aircraft that have transected large distances, but I don't know of any other campaigns that have allowed for these platforms to be deployed over several months of time to capture the variability and the evolution of the Arctic ice pack. The detailed data that we collected document the thermodynamic and kinematic state of the lower atmosphere during legs 3 and 4, as well as information on the surface and specifically surface albedo during leg 4. We're in the process of processing data and putting together our data sets so that they can be published at the Arctic Data Center. We're targeting a spring 2021 publication for that. Some of our initial studies have looked at the impact of small leads and also understanding relationships between kind of the boundary layer structure and other atmospheric parameters. And we'd be really happy to engage with anyone here at the meeting and beyond. So thanks for your attention.
Wonderful. Thank you, Guys. And thank you to all of these fabulous Mosaic folks who have come and shared their sort of their amazing work. And yeah, so there are tons of questions and comments on the group chat. This has just been going and going this entire time. So I think we can take some of the questions on there, though I think, you know what we should do? This is actually time for our discussion. So let us perhaps for this discussion very much focus on sort of the nexus between observations and our models. And then for the later discussion, we'll talk perhaps a little bit more. Oh, I'm sorry. Goodness. One of my colleagues mentioned to me how to that I have mispronounced a name. Okay, Guys, not yeah. Thank you, Guys de Boer. My apologies for that.
It's no problem. We could get a distribution of different representations of my name if we go through the call. Not the first time, not a problem.
Okay, thanks, guys. Yeah, so I think that let's go ahead and open it up to working group discussion on sort of this connection between models and observations, because there's a really wonderful discussion going on in chat, and I think we should just go ahead and bring that into sort of a regular discussion here, particularly because I don't know if the Mosaic folks are going to be here all day, so.
So I had one thing to bring forward that's kind of been going in the chat, and I think is also relevant to one of the points Heis made on one of his last slides about kind of case studies. I mean, it seems to me like the value, one of the huge benefits of the Mosaic data is all these measurements, right? And so I think And I think using them for model development, because they are just a single point in time, it's really about process, understanding process evolution. But to do that, you need to integrate all these different sets of data. And I know some things are being designed to do that in kind of an operational prediction context. But I wonder if there would be value in the CESM community, or the Polar Climate Working Group more specifically, thinking about case studies for model improvement that then we could feed back to the Mosaic team to see whether, I mean, or have these conversations with the Mosaic team to kind of design what those process-based case study sets of observations might look like.
Yeah, I have two comments to that. One is, yes, absolutely. A lot of the initial effort to develop data sets that are for model evaluation are through the collaboration with the Polar Prediction Project and YOP. And so that's a different model approach than CSM, but I think the concept is there. And I basically have a postdoc that's working on this, and a lot of it is a matter of scale and timing and some of the, the basic parameters. Once you already have the data, it's a matter of how you package it. And so if there was explicit guidance from this community about the way in which that packaging would be most effective, those are the kind of things that we can definitely take forward and work to adapt some of the data sets that we're developing, these kind of collaborative data sets that bring together many measurements. The other comment that I want to make is that we will be having a Mosaic meeting in Boulder, likely next year. We were thinking about trying to do it this fall already, but I think that's just not realistic at this point, but likely next year it will be in Boulder. And so, I mean, I'll be the local host for that. And we certainly want to very much focus on this engagement between modelers and observers. And by that time, we should have a really good handle on the observations and be really in a good position to have detailed discussions about how we can make progress on, really fostering this linkage that you're talking about. So I'd say those are kind of two things to think about now.
Yeah, that sounds
so I think
great.
Dave has sorry. Okay, I think Dave has a comment. He has his hand raised, so I wanted to give him a chance to speak.
Yeah, I wondered, Matt or Heise or any of you, do you know if the Polar Prediction Project or YOP is doing sort of a column model approach? I think that one of the best ways that we can do this to get this into the large scale models is to look at these process studies, as Marika highlights, and really look at just the column interactions first, and then we can think about ways of scaling it from that column up to a larger scale model or something like that.
Yeah, within YOP, I know Gunilla Svensson is kind of spearheading an effort to do some column perspective, and I know that she's interacted with a lot of you all before as well, so I think that there's some opportunities there. Another thing that I would have about this column perspective is, of course, Mosaic observations are great for that, right? We're at one location, and I say one in quotes because we have all these data together, but we also have this really interesting perspective on variability and heterogeneity. So that it's a richness that I think that we can, it's kind of a new approach to this single column thing, where often at an observatory, at least the ones I've been involved with, it really is just one perspective. And here we have more than just one perspective of this column that will, to me, lead to a richness in the potential there.
Sorry.
Can
yes.
I chime in for a second, Hansi? I was just going to say, I think that would be really interesting. I know that I put this in the message, but looking at that surface albedo that Heise showed, and then like you go up 30 meters and it's kind of converged to just being a single albedo is really interesting to me, because from a climate model perspective, we're looking at scales of like 25 to 100 kilometers, and the first model level is not right above the surface, it's higher up. And so just trying to understand the implications of like, okay, how does the heterogeneity, what's the distribution of heterogeneity, or how does that converge, I think would be really interesting. I need to think about it more, to think about how best to use some of that data, but it's really interesting and I think would be really useful.
So one thing that I'm seeing from a lot of the chats that are going on is this question, perhaps of how to think about, so Guy says, organize model evaluation and intercomparison efforts. And Jen K says, using Polar Climate Working Group computing resources to run case studies. So I guess I'm just wondering, how can we interface all of that together to actually make that happen? How would one run such case studies, for example?
I mean, I think we have the capability of running like our single column atmospheric model. We also have the capability of running the CICE as a single column, which does have heterogeneity because it has the 5 ice thickness categories and different surface types on different ice categories. So it has some measure of heterogeneity. And so I think we could think of experiments to run with our kind of subset of CESM modeling configurations that could tackle some of this. It almost seems to me like in order to do this, I mean, I think individuals might go away and do this. And, you know, as Maddie and David mentioned, there is this Promise project that I'm involved in with them. We're trying to do some of this, but I wonder as a group, as a working group, if there was enough interest, maybe we could have kind of a sub-team, you know, working with Mosaic investigators to brainstorm about some of these things. And something more than, you know, I know we're running over time. People want to get lunch and stuff before our afternoon, so we only probably have about 5 more minutes to discuss this, but we could have a longer conversation if people were interested in making some sort of subgroup.
Things that would be really useful there are identifying the conditions or events that would be the organizational themes around which we would do those kind of sensitivity studies or evaluations, right? Because there's so much data, there's the whole year, all kinds of different transitions happening. And so kind of focusing on a couple specific kind of thematic areas or time periods or events would be a big step, because then, you know, that helps to set up the model, of course, but it also helps the observers to think about how to package data in an appropriate way to enable that.
So a couple of comments here. You know, we do have those season to season predictability type experiments. And so Alice is wondering if those might be of use. And then Jen K says that 4 times daily radiosonde observations are great for setting up single column atmosphere models. So it seems like this is just perhaps a matter of getting people interfaced and talking to each other to make this happen. And perhaps writing a giant proposal for this or something of that nature.
Yeah, I mean, just a couple of the themes that I've heard people discussing that I think would make for maybe nice kind of case studies is boundary layer evolution and the role of the surface heterogeneity in that boundary layer evolution. So like the kind of lead measurements that Heis was talking about, I think, and the surface-based measurements that, you know, in terms of the heterogeneity in snow and sea ice conditions. The other thing I think is the heterogeneity in the snow and sea ice conditions and the role that that plays on sea ice mass budgets, et cetera. So I think those are 2 things that already people are working on, but maybe some concerted effort would be a nice path forward.
Yeah, Marika, I'll add to that and say, I think that one of the other things that stands out in my mind is some of these really strong gradients in the lower atmosphere, whether the model could actually sustain those or whether the parameterizations are just too aggressive at mixing things. When you have, for example, advection of warm air, and I realize in a single column framework, that's going to maybe be a little bit sensitive to how we'd handle it in advection terms. But trying to figure out whether a model framework could support, you know, 10 or 15 degrees of temperature gradient over a very narrow or very shallow layer, to the extent that we have resolution in the model to do that.
And I was gonna call out Hannah on this one too. I see that as a real way to bring this together too into the subgrid scale heterogeneity aspects, you know, to use Hannah's work to sort of produce that somewhat artificial model heterogeneity and then use that compared to the observations. So
Yeah, I think that was one of sort of the general sort of questions to talk about here as well, which is, for example, using various types of machine learning to design these types of subgrid scale parameterizations that could help incorporate these observations into our more coarsely resolved models. So okay, yeah, there's so much chat going on here. Daniel was wondering about connecting with folks at NOAA for model development. Oh my gosh, this is just going and going. Okay, it's just moving. Andrew Roberts says a focus for understanding the scale awareness of a column model. Yeah, and then, yeah, lots going on here. In here. Jen talks about, let's see, yeah, a focus on vertical stability and stratification. So it sounds like many people are interested in this. I think that perhaps maybe we should try to sort of get folks that are interested in this together, and perhaps we can start off with an email chain and go on to some other sort of platform as needed, and then that can be talked about more to actually get this going in terms of what might be necessary. Okay, so I think that it is probably a good time now for everyone to sort of maybe take a break for lunch. But of course, feel free to hang out here and chat for as long as you want. If you run on ideas rather than food, then please feel free to stay here. But if not, please go take a break, and then we will meet again in about 45 minutes for our afternoon session. We will be focusing predominantly on the Arctic. And in our final discussion, we'll hopefully even touch base again about all of this observational and modeling sort of synergy, and be able to speak more about Arctic and Antarctic studies. So thank you all so much for being here, and we'll break for a little while. Thanks.
And I will note, I just saved the chat so we can parse it later. Sorry if we missed your comments in the chat, but hopefully by going through the saved text version, we can get back to you and things like that. So, yeah.
And I'll just also add, we probably will send out an email after the meeting, seeing what members of the Polar Climate Working Group would like to be involved in a further discussion about integrating models and observations. If you aren't on the Polar Climate Working Group email list, please sign up for that so that you'll get those emails. Or you can also just email myself, Hansi, or Dave directly and say, I want to be involved in this discussion, and we'll make sure you're included. Thanks.
Wonderful. Okay. Sounds like a plan. Thank you all. See you soon.
Thanks, everyone.
Hey, Dave, how's it going?
Had to find the mute again. Good. So,
Saw you had your camera on. So, hey, Hansi.
Hello.
yeah. So, all right. So I will be presenting for Mark. Is that right?
Yeah, if that works, that would be great.
Yeah.
I think he was hoping to be available for questions.
Yeah. Yeah.
But
from his car, apparently.
From his car.
Yeah, from his car. Yeah. Huh. Well, that's bad when your home internet is worse than your cellular internet. I'm going to just quick try sharing this presentation just so that I see how it works. But okay, so I'm going to just do the presentation itself. Are you seeing just the presentation?
I'm not seeing anything.
Oh, that's weird. Why did, oh, never mind.
There it is.
Yep. Okay. And it's full screen?
Yep.
Okay. And then I'm just going to play a little bit of his voice to make sure that the volume's okay.
Hello, everyone. Today I'll...
Sounds great.
Good. All right.
Thank you.
I will stop sharing.
I could do that too, but it's always easier to introduce if someone else is the one fiddling with screens.
No, I totally agree with that. Yeah. So.
Yeah.
Marika, are you on any Slack groups? I know Dave is on a ton.
I'm on one main Slack group. So NCAR is also using Zulip.
Oh.
Which is kind of like Slack. So I'm on several Zulip groups.
Zulip. All right.
Zulip. I know, which just means I'm so cranky about these things. I've realized I've just got, it's like the one very obvious my age is showing sort of thing where I'm like, now I have to check my email, I have to check my Slack, I have to check my Zulip. But I appreciate that they're useful. I just.
Marika, I'm younger than you, and I'm a grump about this too. I'm like, maybe I'm just like old beyond my years. I was also thinking about eating, that I was sad we couldn't all eat as a working group.
Wise beyond your years.
Yeah.
Whatever.
Yeah, actually, and ironically, I'm older than Marika, but I kind of like them. The thing I like about Zulip maybe better is that it has just one stream with everything, which is the hard part I found about Slack is like, oh, there's a notification. Which group is it? You know, and I've got 10 different groups. And so it takes me a few minutes to figure out which one or the channel, right? But yeah. But in principle, I like them.
Yeah. I understand their usefulness. I'm just a grump.
Yeah, I guess I'm just wondering in terms of trying to get folks interfaced and talking to each other on a more regular basis. And I think that usually it's a little bit more possibly organized than email. So that's the only thing. I mean, maybe, I don't know. I don't know if we want to go to the place where, you know, we have a polar climate working group Slack and a channel for people that are doing model observation synergies or studies or cases or whatever. But anyway, that was just kind of an idea, like just one potential idea for how we might be able to do it.
Do a survey during the discussion and sort of see what tools that people use or something like that.
Yeah, one concern with Slack that I've heard raised is that you don't have an archive of it. And so unlike email, which you can go back to later, you know, if you kill the Slack, it's gone. And so I would definitely think about that in terms of long-term, because I still like Google things in my Polar Climate Working Group folder from like 2010.
Me too.
Yep. Wow. All right.
Well, I think we should get started because there's so many great ideas and so many interesting talks that I think we're going to have challenges with time in the afternoon as well. So we might as well just get started. So this afternoon, so for those of you just joining for the first time or rejoining, welcome to the Polar Climate Working Group. So I'm Marika Holland. I'm one of the co-chairs. Hansi Singh is another co-chair. Dave Bailey is our liaison. And we have a set of really great Arctic talks this afternoon. And then we'll end the day with some discussion on kind of research priorities and other ways to better collaborate and things of that nature. So without further ado, we're going to have speakers share their talks. And we're going to start with Raymond Selvold from Delft University. And I expect it's fairly late in the day for Raymond, so sorry about that. And he's going to be talking about the influence of Arctic sea ice loss on the Greenland ice sheet's surface mass budget. So Raymond, if you're able to share your screen and unmute, you can take it away.
So let's see here. Oh. Can people see and hear me?
Yes, looks great.
Yeah, that's great. Thanks. So I will present some work I have done on the influence of Arctic sea ice loss on the Greenland ice sheet surface mass balance, which is work I did together with Jan Lennartz and Miren Vizcaino. Oh. Yeah, so the motivation for this study is that the Greenland ice sheet has been losing mass since the 1990s. And here in the first figure, I showed in the red mass balance in red, the surface mass balance in orange, and the ice discharge to the ocean in blue. So this is from Van den Broek et al. And we can see that since the 1990s, the mass balance has really rapidly declined. And looking into the SMB and the surface mass balance and the discharge, we see that most of this decline in the mass balance is due to a decline in the surface mass balance. So the surface mass balance is defined as the accumulation of snow and rain that refreezes in the snow minus the meltwater that runs off into the ocean. So at the same time as this is happening with the surface mass balance declining and the mass balance of Greenland, the Arctic sea ice has also been declining fast, as seen in the second figure, where the purple line shows the observed loss of Arctic sea ice in winter. So then the question is, what is the impact of this Arctic sea ice loss on the Greenland ice sheet surface mass balance, and if there is an impact? So to study this, I analyzed some simulations that were part of the PAMIT project, and I used simulations from the Sea Community Earth System Model 2.1. And the reason for using this global climate model is that it includes an explicit and interactive simulation of the Greenland ice sheet surface mass balance. So simulations are run at 1 degree horizontal resolution. It has an active atmosphere and land component, which are initialized to 2000 conditions, and using prescribed sea ice and sea surface temperatures. And then I looked into 2 experiments. So one is using pre-industrial Arctic sea ice concentrations, and outside of the Arctic, it is using the average of 1979 to 2008 sea surface temperatures, and another experiment which uses future or +2 Kelvin compared to the pre-industrial state of Arctic sea ice concentrations, and also prescribed sea surface temperatures where the sea ice is reduced by more than 10%. And these sea ice concentrations comes from, and sea surface temperatures comes from the CMIP5 model ensemble. And here I have plotted this forcing that is in the model by taking the future minus the pre-industrial. So you can see that it has a year-round forcing of less sea ice and higher SSTs, and particularly during the summer. And each of these experiments consist of 100 one-year simulations. So they are run from April 1st to June 1st, and then to June 1st the year after. So it's really 14-month simulation, but the 2 first months are discarded as spin-up time. So it leaves 1 year simulation, and then it's run 100 times with different atmospheric initial conditions. So what we already know about the impact of Arctic sea ice loss is from observations. They suggest that there's a regional enhancement of 500 hectopascal geopotential heights, higher Arctic temperatures, increasing downwelling, long wave radiation to the Greenland ice sheet surface, and which gives more surface melt, but very little contribution from turbulent heat flux to the energy of melt, because of the Greenland ice sheet has very persistent katabatic winds flowing from high elevations to low elevations and out to the coast, which seems to be blocking the advection of warmer air masses over where Arctic sea ice loss happens into the ice sheet. There's also some regional climate modeling done, which suggests the increase of precipitation over the Greenland ice sheet, and some global climate modeling that also suggests more surface melt at the GRIS surface and more blocking frequencies. And these are done then with these modeling studies by perturbing using observed sea ice loss and looking into the melt rates from observations. So the novelty of this study here is really having an explicit and advanced simulation of the Greenland ice sheet surface mass balance in the model, which should give better consistency between forcing and response, and a high number of simulations. So said responses the robustness of them can be addressed. So in response to this Arctic sea ice loss and SST increase, in winter, there's this pan-Arctic increase of near surface temperatures. of up to 16 degrees in the Barents Sea, for example. And it in the zonal mean, you can see it is quite extensive and all the way down to 40 degrees north. On the other hand, in summer, you also have increases of near surface temperature, not as extensive and not as strong as in the winter. And I would like to add that these dotted areas are the non-significant areas, while non-dotted areas are significant responses at the 95% level. Also, you can see that during summer, the warming is really more confined to the high altitudes and mostly in a band between 60 to 80 degrees north. So the impact this has on the surface mass balance of Greenland is that it increases the surface mass balance. This is really great. Losing Arctic sea ice adds mass to the ice sheet in winter, and then particularly in the southeast, although almost over the entire ice sheet. And this is mainly attributable to increased precipitation. So if I split this precipitation into the convective precipitation and large-scale precipitation, then we can see that while there is an increase in convective precipitation in response to the sea ice loss, there is almost zero that actually falls on the ice sheet. So most of this precipitation increase is because of more large-scale precipitation. So then I was curious whether this was because more precipitable water, or if there was also something dynamic. However, there is quite some more precipitable water in the atmosphere, but for example, the frequency of cyclones, while it increases in the Arctic and decreases in the North Atlantic, there does not seem to be much of an influence in the high accumulation area of the Greenland ice sheet. So moving over to the summer surface mass balance response, then we can see in blue here that this mass balance decreases, particularly around the margins. And this is mainly because of more surface melt at coastal locations. There's also a redistribution of mass through precipitation changes where you get more precipitation in the northwest and less precipitation in the southwest. However, the precipitation response is not significant, so therefore it is not in bold here. So if I contrast it to the winter response, then you can see that in the winter, it increases with 23 gigatons per year in surface mass balance. And in the summer, it loses 33 gigatons per year. So the net result is a it's a slight negative impact on the surface mass balance. So then I was curious about where the energy for this increased melt comes from. So particularly in the western part of the ice sheet, you can see that there is an increased sensible and latent heat fluxes there that provides more energy for melt. Interestingly, the incoming shortwave responses are not significant. However, there are significant responses in increased shortwave net at the surface for providing energy for melt. And that is really because of an albedo decrease. So when I looked more into detail, then it looks like it is that the sensible and latent heat fluxes from advection of warm and moist air over where you have sea ice loss is advected over the ice sheet, and it triggers melting conditions, which then again decreases the albedo, and you get a higher contribution from net shortwave. It's also looking into some circulation changes, because as I showed, you have increased precipitation here and lower precipitation there. Also, you have very high sensible heat fluxes on the western side of the ice sheet. So we see that in response to the sea ice loss, you get a regional enhancement of the geopotential heights, which is very deep. So here is a meridional here's a meridional mean from 60 to 80 degrees north. And here is a cutoff at the 500 hectopascal geopotential height. So this is quite interesting because this type of circulation regime has really gotten a lot of attention as they have done some attribution studies where they see that 50% of the current mass loss trend of the Greenland ice sheet is because of this anomalous circulation. However, these responses here suggest that this response we see here is accounting for about 16% of the current observed regional enhancement. So it looks like sea ice loss is contributing to this regional enhancement, but cannot explain everything of what we can see in observation. So one thing I was wondering about was why this location, because this is not really where we have the strongest sea ice loss. It's not where you have the strongest surface forcing. So again, I have a meridional mean with height in hectopascal, 60 degrees to 80 degrees north, and also plotted in the surface contours. We can see that here with Greenland, you get a quite deep warming compared to other locations. And it seems that this is because you have these westerlies that flows. And then Greenland is like an obstacle to these westerlies. So they have to either turn around to the south or you get lifted air masses. So this seems to advect the temperature and heat upwards into the atmosphere. And many studies have shown that the deep heating really is what the circulation responses are very sensitive to. So it seems like because of Greenland is a very high elevation area, there seems to be like a positive feedback between making itself melt more through this mechanism. So a summary is that the sea ice loss together with increased SSTs warm the Arctic surface and atmosphere in summer and winter, and that the Arctic warming by sea ice loss enhances the hydrological cycle over the Greenland ice sheet by having more precipitation in winter and more meltwater production in summer. And you have regional enhancement of geopotential heights in summer. So.
Great, thank you. So if we have time, if we have one quick question, and if not, perhaps we'll do it in the chat because we are kind of short on time. All right, so not hearing any quick question, why don't we move on to the next talk, and please ask Raymond questions in the chat. I see there's actually one there already. So that can be going on in the chat. So our next talk is from Jinghua Ding from UC Santa Barbara. I'm talking about some nudged wind simulations in the Arctic, trying to understand the changes occurring in the Arctic system. So Jinghua.
Yes, thanks. So can you see my slides?
Yes.
Okay. Yes, great. So yeah, I really appreciate this opportunity. And the first, I'd like to thank the contribution from my collaborator, Ian Baxter, Axel Schwager from UW, and Ed Blanchard, and Yi Huang from NASA. And so the goal here is pretty simple, just to put the ERA5, the newly available real analysis wind to the CESM1 model to see how the CS respond to the observed wind over the 40 years. So this is the plot I just got yesterday from this online publication on Journal Climate. And this paper test just to look at this, let me remove this bar. Just to look at this, the CS trend in September, CS extend over 36 years from 1979 to 2014. So you can see this blue, this green one is for observation, and this dashed line one is from CIMP 5 and the CIMP 6. And it seems like over this 36 years, and the model example from 2 phases of this CMIP6 model still lower than observation. So this somehow suggests maybe there's so many way to understand this discrepancy. One is that probably model is some model has some lower sensitivity, or as a group has a lower sensitivity, or maybe something in this green line include not only the false response, but also maybe internal response. And in the observation, we see a minus 0.9 per decade, and the model give us like the 0.6, 0.7. So CMIP6 a little bit higher than, stronger than this CMIP5. And so I think probably we should consider 2 things. One thing is the internal variability is important, but that only work for like a short period, like decades. That's a long segment. But if we look at long term, like if we have 100 years data, probably that is the primarily driven by this anthropogenic faulting. So we need to understand both. But right now we only have 40 years of data, so we have to consider both. But we want to quantify the contribution from each factor. So this is the goal of this study. So this is my framework. So I think people are really familiar with this box. There's so many feedback. Favor is the AA amplification effect, but this feedback or this amplification collective effect could be triggered by not only anthropogenic faulting, like a CO2 faulting, but also internal variability. Like Raymond said, there's a high pressure there in the observation summer. So I think the part of this, the high pressure in summertime in the Arctic over the last decade, some of them probably driven internally. Some part of them probably relate to some tropical SST faulting. So this is the plot. I can show you the result directly. So this is the observation again. So up to 2020, just last summer. And so you can see this a little bit, I saw different versions. So if you look at extend, it's a little bit different from this. So this is CS area. The 2020 is almost like the second lowest in record over the 40 years record. But if you look at the area, the monthly September, like monthly average is still like a tie with the other year as like either like a second lowest or the third lowest. And this one is the model. I just using like a CSM1 and I put ERA5 wind, daily wind, 6-hour wind in the Arctic and the dry wind and 3 times. So I'm running more members, but now just to show you like a 3 members average. And the goal is that to try to quantify how wind contribute or simulate this purple line. And so the approach is using this nudging method I got from with help of E and Ed Blanchard, and put this model. And I only add a wind, zonal and meridional wind, U and V every 6 hours. I got it from ERA5 and put in this model. And this is our sighting. So we have a really long spin up before it's nudging wrong. So this is a long spin up. I firstly get it from lens, CSM1 lens. Then I still run this some initial condition from lens and for another 17 years. Then I using some like the end result to restart this 3 nudging wrong. And in this nudging round, the nudging domain like this large, 60 to 90, and from surface to the TOA, and the full nudging. So it's like 100% nudging. Just a false model, just replay observe wind in this CSM1. And the constant CO2 and no, I don't have any other information from like a CI thickness, ocean heat content, everything determined by model and or the spin up. I only let the model know how wind evolve over the 40 years. And I run 3 times. And so I like to see if you see observation from a ERA5 over this period, the trend in JJA. This is a jet potential high at upper level. You can see there's a high pressure there. Like the Raymond side, his model can only capture like a 16% over this area. But if you look at the whole structure, like a global, like the Pan-Arctic pattern, it seems like there's a high pressure here and can extend even into the interior of the Arctic. And this is a wind associated with this. This is a trend. Okay, this is a trend of this wind and the jet potential high. And this is the wind pattern associated with the circulation, the trend. And this is the CSM1, a large ensemble 40-member average over the same period. I just attach historical run with the RCP 8.5. together, and so this is a false response. So I use the same scaling for scaling for its wind. So you can see CO2 doesn't generate any wind pattern because we know there's no pressure gradient because CO2 is quite uniform, warm everywhere, same intensity, so it doesn't generate any wind pattern. But in observation, we see really strong wind pattern. So this is how so after we nudge wind there, so it's natural to see everything like pretty similar to observation. But if you look at vertical structure, so this is a zonal mean average of a potential high in contour and in black contour, and the shading is temperature. And this red contour and blue one is the vertical motion, omega. So you can see over the past 40 years, there's really strong subsidence because the positive red one means like the upward, like downward motion, right? Downward motion, omega. And so if we nudge the wind into the model can somehow capture this feature. So if you look at the observation, it seems like a mixture of the two components, one from CO2 forced component like this part, and plus something like this. But a model doesn't generate any wind, but a model still can generate the CS melting. So we do some like the quantification. So this is each line. I put it together. Purple line, CICE September CS area total from observation, and the red one is a 3-member average. This is a long nudging run over this 40 years, and the black one is a length 40 false run. So you can see basically if I add a black and the red together, it's a green one. The green one is add them two together. Somehow I can capture part of this one, especially from 2000 to 2012, like this acceleration of the CS melting. And over this period, it's a strong melting observation, probably due to this aerosol effect, because we don't have aerosol effect like a volcano eruption effect or cooling effect due to aerosol, like a more injection due to a Pinatubo eruption in the model. So you can see it's stronger than observation. But basically, if you look at each month, I do this one each month. The green bar indicates the trend for each month, CICE declining, and each month, and the color one means from each model. So it seems like the model, and for winter time, if add the two together, like a purple line, cannot fully explain the observed CS decline. But for the summertime, for warm season, it seems like we need the two components added together to fully explain observed feature, especially in like August, September, and October. And if you compare blue one and the red one, it seems like the wind effect explain like the 40% or something of the observation. So we also looked at radiation. So we looked at TOA, net, flux, short wave, minus long wave, and in four data source. So ERA5 is a purple, EBAF is a blue one, and our nudging run and the lens run in black. So you can see basically with wind active in the model can do a much better job than like the only force by CO2 to capture the radiation budget, like a TOA. So this is only for summertime for like a Antarctic. So it's matched with this blue one, that's EBAF very well. And if you look at the horizontal plot for this 13 years with a really fast CS melting in the Arctic, for summertime JJA, you can see the lens give us like at the top of the atmosphere, the atmosphere whole air column gain more heat. But if you look at observation, it looks like it's not very uniform. Have the maximum value over this area and some part over there. So with a wind nudging to the model can do a better job to capture this regionality of the energy imbalance at the top of the atmosphere. And if we look at the surface, so the same thing with a model, with a wind nudging to the model can still do a better job than only forced by CO2 capture the imbalance of a surface flux budget. So this is a net surface heat net flux, just a short wave minus a long wave. You still can find basically it's a more like an albedo effect, right? The albedo effect, more CS melting and the more open water and take much more heat. And this imbalance translate to the top of atmosphere. So this is how I understand that it's a comparison of the two plot. So the message I want to see from this plot is that if we don't add a wind into the model, so if model doesn't know anything from like a wind. Model just do like this, like a black curve. So it's quite uniform and have a really strong like a trend then observe the curves. So we also looked at, because this model can generate the CS melting and from each component and the advection and the CS mass transport. So I also focused on this for 13 years and see how it's still a trend. So see how this melting contribute to this the total melt. It seems like in June, July, August, a lot of melt occur in the basin due to this top melt. This is the trend. And from July to September, most of the melt is the basal melt. And the lateral melt is the in color in the bottom panel, but doesn't show any significant value. And this the purple one is the ice mass transport. It seems like this anticyclone wind doesn't favor a lot of ice, flashing ice out of basin. Most of the ice just relocate from one small area to other area, but still melt local within the basin. That means that most of the ice melting occur within the basin locally due to either top melt or due to the basal melt, rather than just flashing out and melt outside of the Arctic. So lastly, I'd like to briefly see this, the 2020, last year. So last year, if you looked at this anomalies, just using this year minus the other, like the previous 39 years, you can see there's a high pressure again. And if you look at the vertical structure, there's like the bullseye shape, like the high pressure top, and the temperature like this is really warm in the bottom and really strong subsidence. And if you look at the global map, it seems like a high, low. So it's probably connected to the like a La Nina phase, because we know if over like a 40 years data, if we do this a simple correlation between September sea ice with like the JJA Z200 global scale, you can find some signal just maybe originated from like a tropics. So when there's a cooling, low, high, may favor some high pressure in the Arctic. So it shows some similarity as the last summer. So I think I used up my time. So basically, this is the flow chart of my the mechanism. So this is a plot from in Baxter. So the idea is the tropical cooling may generate some wave train and a favor subsidence, and this long wave emission, but eventually warm the CS, melt CS through this albedo feedback. Just through this the changes albedo and ocean take a lot of short wave radiation. So this is my take-home message. I want to just leave here. Yeah, that's all I have. Thanks for your listening my talk.
Great, thank you. Yeah, it's really great to see these nudged wind runs have been really valuable, I think. So it's great.
Yeah, I like to share with but when I have a more member, I like to share with our group.
Great. So I'm trying to keep track of time, and I know there's actually quite a few questions in the chat for you. So
yeah,
why don't you answer them there? Answer them in the chat, and just to keep so that we can try to keep on time.
Okay.
So yeah. Okay. So next up is Yuchao Liang from Lamont Doherty, talking about Arctic amplification from ozone depleting substances.
Okay, thank you, Marinka and Hansi. So can you see my screen?
Yes.
Well, okay.
It's not in present yet. There we go.
Okay, my name is Yuchao Liang. I'm a postdoc working with Lorenzo at Lamont, and this work is also contributed from many of my colleagues, and I appreciate their contributions. So in this study, we want to understand the effect of ozone depleting substances on the Arctic amplification and compare its effect from carbon dioxide. So to begin with, we quickly look at the radiative forcing related to ODS and carbon dioxide. As we can see, during 1955 to 2005, carbon dioxide contributed to a significant amount of radiative forcings. And during this period, ODS also contributed to some of the radiative forcing, as you can see in the cyan line here. And overall, ODS, the strength of the radiative forcing from ODS is about 1/3 to the carbon dioxide. So ODS is also important greenhouse gases. And we especially want to highlight that in 1987, when Montreal Protocol was signed and enacted, the ODS started to phase out a little bit. So you can see the ODS radiative forcing becomes more flat. But overall, during this period, ODS contributed to global warming substantially. So during this period, the Arctic amplification signature also started to emerge. So as you can see on the left panels, I'm showing you the surface air temperature in the zonal mean sense at each latitude. And you can see in the first couple of years, there's less Arctic amplification signature, but as time evolves, this Arctic amplification becomes more apparent. So we wonder that during this period, in addition to contribution from carbon dioxide, is the ODS can also contribute to the Arctic amplification. So the scientific questions we want to address in this study is first, what is the role of ODS in affecting Arctic climate? While most of the previous study focusing on Southern Hemisphere, because ODS related to the ozone hole formation and the recovery, but the last study has been focused on the ODS impact on Arctic climate. So Lorenzo and all 2020 have addressed that ODS can have substantial impacts on Arctic warming trend and the Arctic sea ice loss. I found that about half of the Arctic warming trend and Arctic sea ice loss can be attributed from the warming effect of ODS. And Mark England's AGU presentation also showed that by phase out ODS, we can delay an ice-free Arctic by decade. And we further, in this study, we further want to understand the effect of the ODS on Arctic amplification, and especially compared to the Arctic amplification from carbon dioxide quantitatively. So this has not been documented in previous study. And further, we want to dig in further to understanding the underlying mechanisms which allow ODS to produce Arctic amplification. So to answer these questions, in this study, we conducted 3 sets of large ensemble simulation. In the first set of experiment, we run the O-forcing run, and we 10 members were sampled from CSM large ensemble simulations. And in the second set of experiment, we fixed the CO2 level at 9055 levels, but we keep outer forcing exactly the same as in O-forcing. And similarly, in the third experiment, we fix ODS level at its 9055 levels. And by using 1 and 2, for example, we can single out the effect of carbon dioxide, for example, by 1 minus 2. And in the following presentation, I'll just call it CO2. And similarly, we can also single out the ODS effect by considering the difference between 1 and 3. So we first look at the surface air temperature trend. As we can see in O-forcing, there's a large warming trend in Pacific sector and the Atlantic sector. And the CO2 produces similar warming trend patterns. In contrast, the ODS just produced the largest warming trend in the Pacific sector, including laptop C. And we also conduct the other set of experiments, try to single out the effect of stratospheric ozone, but in general, its effect is very limited and very small. So we won't talk about much about that. So correspondingly, large of the Arctic sea ice loss in the Pacific sector and in the Atlantic sector in O and the CO2, while most of the Arctic sea ice loss in the Pacific sector related to ODS. So to further quantify this trend effect, we calculate the Arctic average surface air temperature trend in Whisker plot and in the distribution with 10,000 resampling. So we can see that larger of the all warming comes from carbon dioxide, but ODS also contributed to some of the warming. It's about like 0.15 Kelvin per decade. So you can see some of the spread reflect the internal variability. But overall, this CO2 and ODS, they can they are separable statistically, indicating the effect of internal variability cannot overwhelm this forced signal. And this feature can also be clearly seen in the distribution from 10,000 resampling. As we can see, they are separated, and the CO2 and O-forcing overlap something. So CO2 explains the large of the warming. So correspondingly, we also see similar statistical feature in September sea ice extent. So next, we want to focus on the Arctic amplification. So we first investigate the Arctic warming trend in y-axis, and we plotted against the global warming trend in the x-axis. So we see that almost all the individual member or ensemble member are sitting above 1-to-1 slope line, indicating the Arctic amplification signature response. And overall, in Arctic warming and global warming, CO2 has larger warming compared to ODS, but we want to more focus on its slope because its slope is more reflect the Arctic warming against the global warming. So we found that actually the slope for ODS is about like 3.57, which is larger than the CO2 slope, about it's only 2.74. So this indicated the ODS may contribute a stronger Arctic amplification signal. So to further quantify this, we calculate the Arctic amplification factor by the Arctic surface air temperature trend divided by global surface air temperature trend. And as you can see on this whisker plot, CO2 is, the ensemble mean of the CO2 is about 2.6 for the Arctic amplification factor. But for ODS, it's about 3.8. So the ODS contributed is 1.4 stronger than carbon dioxide did in producing Arctic amplification. So although again you see larger spread in the ODS indicating the internal variability, but overall these two they can separate it statistically across 10 members. So indicating again the internal variability cannot overwhelm this forced signal. So this result clearly show that ODS may possibly more efficient global warming agent in producing Arctic amplification compared to CO2. So we finally want to understand the underlying mechanisms. So we perform standard radiative feedback kernel analysis, and to single out to decompose each component of the feedback. So in the y-axis, I plotted out the feedback parameters for ODS, and the x-axis is for CO2. So everything sitting above this 1-to-1 slope line indicating ODS get stronger feedback. So two feedback stands out. One is Lebesgue feedback and the albedo feedback. So there are these two feedbacks that will work together to amplify the Arctic warming in the ODS scenario. And we also checked the spatial distribution of these two feedback parameters, and we actually found their spatial distribution is very similar to the Arctic warming and Arctic CICE loss. So indicating these two feedbacks are closely coupled with the local warming and the local CICE retreat. And they are working together to amplify the Arctic warming, give rise to stronger Arctic amplification. So to quick summarize, ODS can serve as important greenhouse gases for recent Arctic warming and Arctic CICE loss. And in this study, we quantified that ODS are about 1.4 times stronger than CO2 in producing Arctic amplification. This stronger Arctic amplification from ODS than from CO2 is mainly caused by Lebesgue and albedo feedback, both of which are coupled to local warming and Arctic CICE loss. And one important indication for this study is that in the absence of the Montreal Protocol, present or near future Arctic amplification would be much stronger than we observed today. Okay, so I'll stop here. I'm willing to take any questions. Thank you.
Thanks. So we do have a couple minutes for questions. So people can either just jump in or raise your hand. Yeah, Ray?
Hey, thanks for your talk. I have a question. You showed that if you look at Arctic amplification as the ratio between Arctic and the rest of the world, ODS has a larger impact than CO2. What about the difference? If we want to talk about temperature, difference between the Arctic and the rest of the world, if we want to talk about regional temperature gradient effect of Arctic amplification, if I read correctly, your plot, it's actually CO2 is more important than ODS if we look at the temperature difference rather than the ratio?
Yeah, I haven't checked that, but that's a good point. Yeah, but I guess if you use that matrix, probably we'll get a similar result. Yeah, because they are relatively, because now the stronger amplification just reflect the relative warming produced by ODS is stronger than CO2. So I guess in that matrix it would be quite similar. Yeah, but that's my guess. Yeah, I definitely will check. Yeah, thank you.
Any other questions?
I saw that Belly has some questions. So it looks like a lot of scalar and some big outliers on a few of your plots. You know what is going on there. So because we fixed, for example, the ODS wrong, we fixed ODS at the 1955 levels. But when we calculate the warming trend, we calculate its difference from historical wrong, right? So the ODS contribution could be, so the all forcing wrong minus ODS wrong in terms of the global warming could be small. So if you put in the denominator when you calculate the Arctic amplification, you amplify the spread. Yeah. So yeah. So we deal with this issue using two methods. One is using the resampling to try to test the robustness of the result, and we get the robust result. And the second, I also mentioned that we do the statistical test to try to separate two 10 members from the CO2 and the ODS, and they are statistically separable. So I guess the result, I mean, the forced response is quite robust in our analysis. So I guess, yeah, probably the outliers is just because due to some unreasonable, very small global warming signal. Yeah.
Great. Okay, well, if you have more questions for Yu-Chao, please put them in the chat. It seems like there's a lively chat going on. And so we're going to move to the next talk before break. So Mark England, so he actually sent a pre-recorded talk because his internet is a little bit flaky, but he is here to answer questions. So Dave's going to play his talk, and then we'll take questions for Mark. Dave, you're muted, so.
Sorry about that. Too many knobs to figure out here.
Hello, everyone. Today, I'll be talking to you about our work on the recent emergence of Arctic amplification. And this is work done with Ian Eisenman, Nick Lutzko at Scripps, and Till Wagner at UNCW. And I'm recording this video because our internet connection hasn't been good recently, so I didn't want you to miss out. And this work, I'm currently in the process of writing it up. So I think all of you will know that Arctic amplification is a robust phenomenon which is found across a wide range of climate model simulations. So on the first panel here, I'm showing the quadrupled CO2 CMIP-5 experiments, which show enhanced warming in the Arctic. And this is projected to occur over the next century under RCP 8.5 in CMIP-5, as I'm showing in the middle here. And this phenomenon has even been found in past climates. So on the right here is from reconstructions and PMIP-2 experiments. But in our study, we investigate the extent to which and why Arctic amplification occurred over the last century. And many studies have really investigated the causes and the effects of Arctic amplification in climate model studies, but relatively little attention has been paid to the observational record over the last century. And so we investigate this question using a range of observational and reanalysis products. And we also use this CSM large ensemble and the single forcing ensembles to understand the contributions of aerosols, greenhouse gases, and internal variability to the observed trends. So here I'm going to talk about global and Arctic averages, and Arctic I'm going to referred to as 60 to 90 north. We're looking at 50-year linear trends in near surface air temperature, and Arctic amplification occurs when the Arctic trend divided by the global trend is greater than 1. So we look at 5 observational and reanalysis data sets: GISTEMP version 4, HAD group 5, the Cow-Tannenway update to HAD group 4, ERA 20th century, and ERA 5. And we're going to mostly show you results from GISTEMP version 4, but all the results are really robust across the different data sets. So if we just look at the time series of the Arctic on the left and the global in the right, and the surface temperature time series, you can really clearly see that Arctic amplification did not occur through much of the mid-20th century. And this is robust in all 5 data sets. So I've picked out a 50-year period here, which is 1935 to 1984, where the Arctic was cooling at a rate of 0.15 Celsius per decade. And in contrast, the globe was warming by a moderate amount of 0.03 Celsius per decade. So this is a period of Arctic cooling during global warming. So this is not Arctic amplification. If we look at all possible 50-year trends over the last century, and on the left, I'm showing all the different data sets, and you can see that they are very consistent with each other. In the blue is the Arctic trends, and in the red is the 50-year trends in global mean surface temperature. And so what I'm shading in blue here is 50-year trends which feature Arctic cooling concurrent with global warming. And so you can see that this occurred for quite a substantial portion of the observed record before transitioning into this red shaded area. And this red shaded area is periods of Arctic amplification. So this is where the observed Arctic trends are above the observed global trends. And you can see that roughly about the same amount of time has been spent in periods of Arctic amplification as it has in terms of Arctic cooling under global warming. So one question you can ask is, how robust is this to the different observational uncertainties? Because we know that the data coverage in the Arctic was much less in the beginning of the 20th century. And so for that, we turn to the HAD group 5 observational data set, which has 200 ensemble members to account for this observational uncertainty. And you can see here that the behavior and the results are really robust considering this observational uncertainty. So one question we wanted to ask is, can the CSM large ensemble reproduce the observed trends? On the left here, I'm showing you the observed trends just for GISTEMP for clarity. And in the middle here, I'm showing you 2 members, member 33 in crosses and member 31 in circles. And so we show that there are some members, such as member 33 in crosses, which capture the characteristics of the observed trends well. You get a period of Arctic cooling under global warming and then transition to a rapid Arctic warming. Whereas there are other members, such as member 31 in circles, where you have Arctic amplification throughout the last century because you have continued Arctic warming over every 50-year period. And so this, the difference between these 2 members indicates a potentially important role for internal variability. And if we look at all 40 members of the CSM large ensemble, which I'm showing here in the right panel, where the dots are the individual members and the line is the trend for the ensemble mean, we can see that the ensemble mean response here features a mild Arctic cooling in the mid-20th century. We can also see that if we compare the first and the last panel, that the observed Arctic cooling trends are really at the edge of what is simulated by the CSM large ensemble. But you can also see from about 1975, these are the mid-year of the trends, that there is really unambiguous Arctic amplification here. The Arctic trends and the global trends are very well separated. So within the second half of the 20th century, that is a very unambiguous Arctic amplification. And just to note that 31 out of 40 members of the CSM large ensemble show some periods of Arctic cooling under global warming. So we then go on to investigate what has contributed to the lack of Arctic amplification for much of the last century. And we look at industrial aerosols, greenhouse gases, and internal variability. And we do that using the 40 members of a large ensemble and two 20-member single forcing ensembles where aerosols are fixed at 1920 values, and then greenhouse gases are fixed at 1920 values. And those are documented in Desser et al. 2020. So if we look at what is happening in the global and Arctic trends in these two single forcing ensembles, the left shows the fixed aerosol runs. This shows that without the increase in aerosols, Arctic cooling would not have occurred. The Arctic would have warmed throughout the last century. And this is Arctic amplification. If we look at the fixed greenhouse gas ensemble, without the increase in greenhouse gases, global warming would not have occurred. We'd have had global cooling, according to this model, throughout the last century. And so in both ensembles, the Arctic amplification is actually pervasive throughout the last century. This suggests that this specific combination of aerosols and greenhouse gases basically countering each other, creating a setting where Arctic amplification may not occur. So we then move on to looking quantitatively at the contributions to the 1935 to 1984 trends. So first I'll show you for the Arctic. So over this period, as I said before, there was an Arctic cooling of minus 0.15 Celsius per decade. And then we can look at the effects of aerosols and greenhouse gases. You get a cooling from aerosols and you get a warming from greenhouse gases here. And this leads to a net anthropogenic impact of minus 0.7 Celsius per decade. And so you need a residual here of negative 0.08 to account for the observed trend. And this is within the bounds of what the internal variability simulated by CSM. Here's the plus or minus 2 sigma bounds. And so that we are attributing this residual here to internal variability according to the model. Something important to note is that this suggests that a different configuration of internal variability could have overcome the net anthropogenic cooling and resulted in Arctic warming, which suggests that the lack of Arctic amplification was not inevitable. We can do the same exercise for the global trend. The global trend was plus 0.03 Celsius per decade over this time period. And we find that there's near total cancellation in response to aerosols and greenhouse gases. And so internal variability is going to contribute to the residual, which is 0.03. And this is right at the edge of what is simulated in the internal variability in CSM. So this also suggests that a different configuration of internal variability could have resulted in global cooling at the same time as the Arctic cooling, which again suggests that the lack of Arctic amplification was not inevitable. So the conclusions here, we investigate the extent to which Arctic amplification occurred over the last century. And we found that if we look at 50-year trends, Arctic amplification only began to occur in the 1970s. And prior to this, the Arctic was cooling under weak global warming. And so we asked why, and all these results are, according to CSM. In the absence of the emission of aerosols or greenhouse gases, Arctic amplification would have occurred. And it's the combination of these aerosols and greenhouse gas forcings which has created the conditions for Arctic amplification not to occur over the mid-20th century. And lastly, we show the internal variability has also played an important role. And with that, I'll thank you very much and answer any questions you may have.
Great, thanks. So if there are questions for Mark, I think he is able to hear and see us. I see him. So actually, it looks like there is one in the chat. So I'll just read it from Laura Landrum. Really nice talk. She has a couple questions. Observations of surface temperature in Arctic are very limited, particularly in winter over the Arctic Ocean until the latter part of the 20th century. Are the estimates of Arctic amplification primarily from land surface air temperatures? And how might this impact the estimate of Arctic amplification from observations?
Yeah. Can you hear me? Hopefully.
Yes.
Yeah. Okay. Yeah, I think this is a very good point that especially earlier in the 20th century, that they do primarily come from land. But we looked into this using the HADCRUT 5 200 member ensemble, and we did this looking just over land and just over ocean, because they produce this ensemble spread, which is meant to account for the different infillings they use in areas where they lack coverage. And all the results are very consistent with this. So it doesn't seem to be having such a huge impact on what we say for Arctic amplification. And there's a second question. Early 20, yeah. So there was some warming between it was enormously warm in the Arctic in the 20s and 30s. And I think that definitely the transition to this period of Arctic cooling probably wouldn't have happened without this anomalously warm period in the 1920s and 30s. Yeah, that's definitely part of the story. But I think part of our motivation for the study was we were kind of shocked by this lack of Arctic amplification for so much of the observed record, and trying to understand that. And I think that cooling from the 1920s period onward, 30s period onwards, is definitely part of the story. And then Dave has a question about the changes of reanalysis. So we tried to look at lots of the observational. Maybe Dave, can you clarify what
well, mainly it just there were things that happened before the satellites, after the satellites, and I worry about that. And there was even that sort of signal, I think, in Qinghua's presentation, where there's all of a sudden there's this really big jump that you see in some of the reanalysis products, and so I just wondered if that might have an influence.
Yeah, and that does correspond with the fact that the Arctic, the trend, or what we think is the trend, has been so rapid after the 80s or so. It's a good question. So I think it also happens in the ERA 20th century. They're all very consistent with each other. There's a good point for me to think about. As much as the observational data sets and reanalysis, they're all very consistent with each other for these longer time period trends. And all the, I've tried to use the most updated observation. So HADCRUT 5 only came out earlier in January, I think. So this is the best observational data sets we've got, and this is what they're suggesting.
Yeah.
Great.
Thanks.
Okay, if you have more questions for Mark, please put them in the chat. And I would, unfortunately, if we were all together, we would have a great coffee break now where we could discuss some of the questions we didn't get to during the talks to try and keep on time. So we're going to take a break now. We'll reconvene at 15 past the hour. But I would encourage people to talk on the Zoom meeting. If you have questions for each other or want to respond to questions that were put in the chat, but do that verbally, please use this to do that. For those of you that need to get up and grab a cup of tea or use the facilities, now's your time. So we will come back in 15 minutes. And thanks for a really great set of talks. So yeah. And also I'll just mention, there are still questions in the chat, so please answer things there as well. Thanks.
Hi, Mark, are you still there? Sorry, this is the coffee break question. Sorry, everyone should go do their thing. I don't want you to feel like you have to stay. I was just curious. I just have a question for you about sort of thinking about like Arctic amplification, and okay, like one thing that I would maybe say or wonder is like, when we think about natural variability, like when you think about natural variability in like global mean surface temperatures in like, say, a long pre-industrial control run, like, would you expect to see Arctic amplification there? Like if I calculated,
yeah, so
like,
I've actually looked at this. And,
yeah, what does it say? I'm
yeah.
so excited. Yeah.
So that, yeah, there is Arctic amplification. So I think it's a bit
so it's
hard
like a mode. It's like it's like a mode that gets excited even with internal variability.
Yeah, it's within just a long control run. And actually, there was a paper, it was on sea ice loss, but I think you can kind of think about it in terms of Arctic amplification as well, but saying that in the control run, the sensitivity is actually higher than it is to in the forced response, as in the Arctic amplification factor of internal variability they found in this long control run. I think this was a CMIP-3 class model, was actually higher and it was a kind of conundrum of why this was in the control run. But yeah, Arctic amplification will occur in the control run, and it obviously depends what kind of time scale you're looking at. You know, maybe I think it will be there in like 30, 50-year trends, but maybe if you go longer, everything's going to go to zero. So you're going to have some problems with the denominator.
Right. Yeah, I was just kind of wondering in terms of that sort of weirdness of the 1930 to 1980 time period. Yeah, like what is going on there in terms of maybe like what we would expect from sort of like the behavior in internal variability per se.
Yeah, so I think that, I mean, there are members in which there is no Arctic amplification, but like the majority will have, in terms of internal variability, the majority will have, just in terms of internal variability. Yeah.
Right. So basically the fact that we did not have Arctic amplification, it could be potentially due to internal variability, but it might be more likely due to the forcings.
Well, so I think you need the specific combination of the forcings to kind of cancel out in the global mean sense, but we know that aerosols are slightly more Arctic amplifying because of over this time period, because of where they were being emitted, which is primarily Northern Europe and North America.
Right.
And so that in the ensemble mean, there is basically there's very weak global warming and very weak Arctic cooling. And then at least according to a CSM, you need some sort of internal variability to get to the observed trends. Yeah.
Okay. Yeah.
I think the point is that you can't explain, unless the model is like way off, you can't explain it all with the force trend.
Okay. Yeah, that makes sense.
And I think what we kind of show is it's very, Arctic amplification is a very pervasive thing, and it only doesn't occur in like very specific circumstances, right? It occurs if you fix aerosols, it occurs if you fix greenhouse gases, but during this period where you have increases in both, they kind of cancel out, and then you might not get it.
Right. Okay. Yeah, thanks for that discussion. I was super curious about that. Yeah.
Like following on from that, maybe I missed part of this discussion, but I mean, one of the problems we've had in the CSM2, as Patricia's talked about and so forth, is that the forcing is a lot more strong in the CSM2 runs. And so, we still have the same sort of things going on where the aerosols are counteracting the global warming, but it seems like the aerosols are not as effective at it and we get more warming. So how much have you looked at the new large ensemble? I know that it's not public totally.
Yeah, we haven't actually looked at that at all, but it would be a good thing to look at. We looked at a lot of the multiple large ensembles, the kind of CMIP-5 class ones. And some of them can get this kind of behavior, some of them can't. But so we focused on CSM because it was A, the best, and B, it had the single forcing ensembles, which allowed us to do this.
Right.
This kind of thing. But yeah, the CSM was kind of better than all the other ones at capturing this behavior.
I like to hear that.
Yeah.
Yeah, well, Patricia's going to give a talk at 2:30 at 1/2 the hour. So she'll talk a little bit about some of these forcing issues with the CMIP-6 forcing.
Right.
Xinghua, are you there? Because I had a question about your talk. Maybe he's not. Yeah, I really wish we were actually all together at the Mesa Lab. That'd be nice to see all of you in person.
Who knows when that will happen? So many variants jumping around everywhere, faster than you can design vaccines.
Yeah.
It's insane. Yeah.
Maybe in a year, maybe
Dang.
for our next winter working group meeting.
So Mark, that recording, sorry about the mute.
Oh, I was going to say thank you very much for playing it.
But it did come across quite well, I think. So
Yeah, thanks. Yeah, I gave a talk last week in which it was only like a 10-minute talk, but no one could hear anything I said. So I was trying to avoid that that disaster.
yeah. So your internet seems pretty reliable now out on your patio.
Yeah, I'm using my wife's phone, which was a big improvement.
Mark, are you staying at a cabin or something?
Yeah, we're in the middle of it's called La Honda in the Bay Area, but the internet is very up and down. Some days great, some days can't do any work.
It looks beautiful.
Yeah, it's
Beautiful trees behind you. Warm enough to be outside.
yeah, it's also out of necessity because my wife's in a meeting and we have one room.
Yep.
Yeah, it'd be a little cold here right now for us to be outside, I think. So.
Yeah, I saw the pictures of the snow and ice.
Actually, we don't have any snow in Colorado, really, at least along the Front Range. But we're catching a little bit of the polar front that's coming through right now.
Yeah, we've been getting quite a bit of snow in the mountains, but Boulder hasn't had any at all. It's really quite sad. But the mountains have had a foot or more in the last week, so that's good. Good for skiing.
And hopefully better for fires this summer, fall. So. taking notes the old-fashioned way. I can write better, faster than I can actually type, I think. So.
Well, I have an interesting piece of news. We just got our permanent residency to Canada. So yeah, because we're parked here for a while.
Congratulations, I guess. That's great.
Yeah, yeah. I'm just so glad that like we're done, right? Because it's just all bureaucracy, right? Like immigration bureaucracy. Holy moly. And yeah, Canadians will just totally deluge you with paperwork when they can. So doing lots of paperwork. So anyway, done with the paperwork. So
good.
Don't think Americans do anything differently, Hansi.
Oh, I know they don't. I know they don't. And it's probably worse, right? Because they probably like, I don't know, you end up getting like some crazy immigration officer that like, yeah, I don't know. You're right. You're completely right. At least in Canada, they're always like by the book and they're doing everything like, a lot of things, but like very methodically.
Yeah.
So.
I just applied for a passport for my son, a Canadian passport for my son, because he's considering going to school in Canada. And yeah, it was actually a harder form than the US passport form. And the Canadian picture specifications are very different and particular. And yeah, it's
yeah, and you got to find like the right person to take them and everything. And, you can't just go to a regular place. You have to go to a special place that, yeah, I know. At least here, it's like very easy to get like US passport pictures. Like everybody knows what they are, right? Yeah. So anyway.
All right, well, I think we should get started on the post-break session. So first up, we have Yi Huang from NASA Langley, who's going to be talking with us about summertime low clouds and their impacts on Arctic sea ice. So Yi, if you can share your screen.
Thank you, Marika.
Yeah.
Okay, can you see my slides?
Yes.
Okay, thank you. So today I'm going to talk about the role of low clouds or linking large-scale circulation in the Arctic sea ice. So my talk would be a little bit similar to the Chenhua's talk earlier, but I would mainly focus on some physical mechanism. So first time, why low clouds? Because the Arctic low clouds are an important climate feature of the boundary layer, especially during the summer in the Arctic Ocean. The Arctic low clouds are close to the sea ice and can strongly influence the amount of the solar and infrared radiation. So it's gonna highly impact the melting rate of the sea ice. So let's first take a look at the long-term trend. So the blue line here is just September CS trend during 2000 to 2016. And the red line here is geopotential height at 200 millibar in JJA. So you can see these two time series has strong negative correlations with each other. And if we take a closer look at their spatial distribution, we can find the Z200 has been rising over the northeastern Canada and Greenland, which is accompanied by the rapid Arctic sea ice decline in the early 21st century. And then with this increasing Z200 trend, we can find the increasing trend for the low-level clouds, especially over the Bafford and the Chukchi Sea. And due to the increasing low-level clouds, we can also find the increase in the downward long-wave cloud radiative effect. So then we try to identify the relationships between the summertime low-level clouds and September CS concentration variations. So we first apply the maximum covariance analysis between the Z200 and the low cloud. And then we plot the leading mode of these two time series. So the leading mode accounts for about like 50% of the covariance between the JJA Z200 and the Arctic low-level clouds. And then we take the time series for this blue line, it's low clouds, and then calculate the correlations between the low clouds and September CS concentration, and we get a spatial pattern like this. So we can see the large portion of the Arctic Ocean showing the strong negative correlations. So that means the increase in JJ low-level clouds can affect the subsequent CS decline because of enhanced long-wave cloud radiation effect. But also we see like part of Arctic Ocean showing the strong positive correlation. That because when we have the more low-level clouds, it also reduces the short-wave cloud radiation effect and cool the surface. And then we're trying to provide a hypothesis that how the large-scale circulation can affect the low-level clouds. So we first take the average for the temperature and the humidity profile over the area of focus, which is marked by this green box. So that is a region we have the substantial increase in trend for low-level clouds. So first we can see there's both temperature and specific humidity inversion existed below 900 millibar. And for the relative humidity, it just decreased with height. And in the meantime, if we just focus on the linear trend of the vertical velocity at 500 millibar, we can find the stronger downward motion occurred in this region as well. So we believe that the both temperature and humidity inversion, and as well as a stronger downward motion can serve as a moisture source to form and maintain the low-level clouds in this region. This can be confirmed by the linear trend of the relative humidity in the AOF, which is represented by this blue line. You can see the relative humidity mainly increased at a low level, which is below 900 millibar. And for the cloud fraction, actually it mainly increased at around 975 millibar. So it is closely matched with the largest increasing trend of the relative humidity. So those analyses are mainly based on the reanalysis and the observations. And then we trying to take a look at the CESM larger ensemble data sets to see whether the CESM can capture the similar relationships. So here we focus on the CESM pre-industrial simulations. So note that this is from the CESM version 1. So here we have 1,800 simulations in total. And then what we did here is we try to partition this 1,800-year simulation to 780 non-overlapping 20-year episodes. And then we try to calculate the pattern correlations for the Z200 between each 20-year episodes with the reanalysis. And then we selected one member showing the highest pattern correlation with the reanalysis and to analyze the pattern in the vertical velocity radiation and the CICE. So here we can see that the Z200 pattern is quite similar to the reanalysis, but with a smaller magnitude. And we also see the strong temperature and humidity inversion, especially over the Chukchi and Bedford Sea region. And we also see the increasing trend in the relative humidity and also the low cloud fraction. So here we can also find the increasing trend for the downward long-wave flux. And more importantly, we found the strong CS decline, especially over this region. And due to the decreased CS concentration and the sea surface albedo, and we have the increase. So we have the increase in absorbed solar radiation at the surface. And here we can also see a little bit like CS growth in this region. That is because in the Z200 pattern, it is affected by the low pressure in this region as well. So we think the CESM generally can capture those relationships between the large-scale circulation, cloud and radiation, as well as the sea ice concentration variations. But one thing we find, so we didn't find the stronger downward motion in this pre-industrial realm. So we think the CESM can somehow capture those relationships, but maybe capture them with the wrong mechanism. So that's why we go further to run those CESM nudging simulations. So here we also run the fully coupled simulation with all modules active. And here we also use the year 2000 emission scenario. That means during our simulations, the greenhouse gas emissions remain constant. And we also nudge the U and V to the reanalysis only in the Arctic, which is a 60-degree northward. But here we only partially nudge the model wind fields to the reanalysis, which is 50%. So here we conduct the 8 simulations in total with very diverse initial conditions. So most of them are obtained from the large ensemble run, and some of them have a high CS volume, and some of them have thick or thin ice. So they have a very diverse initial conditions. And note that we only nudge the winds above the 860 millibar above. So except the experiment 2, that is because we would like to give the model some freedom in the low level of atmosphere, because that is the level we find the substantial increasing trend in the low level clouds. So we would like to see the response in that level. So here's the results from our CESM nudging experiments. So note that these results are average from all 8 members. So here, the Z200 and the Omega at 500 millibar are similar to what we see from the reanalysis, because we just nudge the dynamic fields to the reanalysis. And then we can see the response in the relative humidity, and as well as the low level clouds. So, and more importantly, we see the increasing trend in the downward long wave flux. So their magnitude actually is comparable with what we see in the observations. And more importantly, we see such a substantial sea ice decline in the Arctic Ocean. And also we see the increase in the absorbed solar radiation at the surface, and their magnitude are also comparable with the observations. So here I also show you in all 8 members, actually we do see the sea ice decline in September. So recall that the greenhouse gas emissions remain constant in our simulations. So we do believe that the large-scale circulation is a really important driver for the low cloud variability and the changes in the radiation budget, as well as the CS variations. So with that, I would like to take any questions. And our paper has been accepted, and I think it's going to be released online soon. So you can go to check it out if you're interested. Thank you.
Thanks, Yi. So we have time for some questions. So dive right in or raise hands. So I had a question if there's no one else. So it looked to me like your omega trends are quite localized, but your long wave down trends are much broader. So do you think that it's really kind of the substance acting on the temperature gradient that is really important for the long wave, trends more generally, or is that a really kind of local feature?
So I think, so we do see the the linear trend of omega is localized, just specified in this region. So that is because the omega is not only, so this stronger downward motion is not only affected by the subsidence, it's also going to affected by the surface roughness as well. So we won't see a like stronger downward motion in a large portion of the Arctic Ocean. And also back to that long wave downtrend. So I think this subsidence just amplify this warming effect, thus increase the long wave downflux. But also, we think the greenhouse gas emission definitely gonna play a role in the like increase in the downward long wave flux.
Yeah, because I was thinking specifically at your the nudged wind runs.
Mm-hmm.
Where? Okay, thanks.
Yeah.
All right, if people have additional questions, please put them in the chat for Yi. And we'll move on to the next talk, which is Patricia Duray-Pignet, who's going to be telling us about the impact of biomass burning emissions on Arctic sea ice. So Patricia, if you can share your screen.
Yeah, hopefully this is working.
It looks, yep, looks good.
Okay, great. So as Marika said, I will be talking about the impact of biomass burning emissions on Arctic sea ice loss. This work has been done in collaboration with several people from the University of Colorado Boulder, NCAR, and NSIDC as listed here. And we are also planning to submit the results from this work shortly. So I want to jump right in and start by showing you the evolution of the Arctic September sea ice area anomaly in the CSM2. What you can see here is an acceleration in the sea ice decline starting around the 1990s, which is then followed by a recovery up to about the year 2020. This might actually look similar to what a figure that Jen showed this morning in the CSM2 large ensemble. So these results are consistent in the CSM2 large ensemble as well. And this feature of the CSM2 CMIP6 was not present in the CSM large ensemble, which is the previous version of the CSM model that uses CMIP5 forcing instead of CMIP6. And we found that one important difference between CMIP5 and CMIP6 that could potentially explain this odd behavior in the sea ice in the CSM2 CMIP6 has to do with biomass burning emissions, which we'll abbreviate to BB emissions in the text throughout the talk. So biomass burning emissions are emissions of gases and particulates from the burning of live or dead vegetation, including human-initiated burning and natural lightning-induced burning. So in CMIP6, the biomass burning emissions were updated to include the Global Fire Emissions Database, or GFED, which is available from 1997 to present day, but was used until the end of the historical period in 2014 for CMIP6, and is indicated by the two vertical lines on these plots and the following plots as well. So GFED uses data from a variety of sources, including satellite observations, and the goal is to provide a more realistic picture of biomass burning emissions. However, as you can see in the time series of black carbon emissions in the Northern Hemisphere mid-latitudes on the right, it results in this unrealistic increase in the interannual variability of biomass burning emissions compared to pre and post GFED years. And in comparison, in CMIP5, there was no interannual variability in biomass burning emissions, with the mean increasing over the historical period until 2005, and then staying at a constant value for the future scenarios. We also found that some other CMIP6 models seem to exhibit kind of a similar behavior to the CSM2, although not all of them. So in the figure on the left, we separated 12 CMIP6 models with at least 3 ensemble members into 2 categories, sensitive and non-sensitive. For a model to be considered sensitive, by which we mean showing similar behavior as the CSM2, it needed to simulate an acceleration in sea ice decline of at least 100% over the years 1997 to 2009, which is indicated by the dark gray shaded region on the plot. compared to the trend over the reference period from 1978 to 1990, which is the light gray shaded region on the plot. When choosing these two periods, which are quite frankly very arbitrary, we decided to make them the same length and to exclude the years 1991 to 1996 because of the Pinatubo volcanic eruption and its effect on global climate. And so based on this criteria, we found that 4 of the 12 CMIP6 models analyzed here fall in a sensitive category, and the other 8 fall in a non-sensitive category. And so the lines on the plot show the multimodal average of these two categories. So another way to look at this that might make it a little easier to understand is to look at the trend in sea ice area, as shown on the right, as 20-year linear trends with the end year of that 20-year period indicated on the x-axis. So the sensitive models in purple show increasingly larger trend, meaning more negative over the acceleration period compared to the reference period. On the other hand, the non-sensitive models show a slowly increasing negative trend over the whole period on this plot. You'll also note that the sensitive models tend to show a recovery following the acceleration period, but not the non-sensitive models. Interestingly, the non-sensitive models do not really simulate a reduced rate of sea ice decline following the Pinatubo volcanic eruption in 1991 and the global cooling that followed for a few years, which could indicate that these models are not sensitive enough to aerosol emissions and may explain why they also show little sensitivity to biomass burning emissions. However, even though we found some CMIP6 models that exhibit a similar behavior as the CSM2, none of them simulate a sea ice decline and recovery of the same magnitude as the CSM2, even when looking at each model individually. As can be shown, you can see the trend for the CSM2 in black on the right plot. And so to investigate the impact of the increased interannual variability in biomass burning emissions over the GFED era on Arctic sea ice, we conducted sensitivity experiments, which we'll refer to as CSM2BB, in which we averaged the biomass burning emissions over the GFED period and used a fixed annual cycle to remove the interannual variability. So this is represented by the green line on the plot, with the emissions pre and post GFED being the same as in CMIP6. And as a result, our sensitivity experiments has prescribed biomass burning emissions that are similar to CMIP5 over the GFED period. So before I move into the results, I want to introduce a different model experiments that we'll be using to compare to our sensitivity experiment, just to make sure that everybody's on the same page. So first we have the CSM large ensemble, which uses the CSM1 version of the model and CMIP5 forcing with 40 ensemble members. We also use the CSM2 CMIP5, which uses the CSM2 model with CMIP5 forcing. So comparing it with the large ensemble highlights changes due to model physics only. And then the CSM2 CMIP6 uses the CSM2 model with CMIP6 forcing, and comparing it to the CSM2 CMIP5 highlights changes due to CMIP forcing only. And then finally, our sensitivity experiment in CSM2BB is the same as the CSM2 CMIP6, except for the biomass burning emissions from 1997 to 2014, which are more similar to CMIP5 as I showed on the previous slide. So moving into the results, on the left, I show the Arctic temperature anomaly, and on the right, the September sea ice area anomaly, starting with the CSM large ensemble only. When we add the CSM2 CMIP5, which again represents a change in model physics only, we see kind of a similar time evolution, although the cooling following the Pinatubo eruption in 1991 is larger in the CSM2 model compared to the CSM1, which is likely due to changes in cloud aerosol interactions from CSM1 to CSM2. The CSM2 CMIP6, on the other hand, simulates large Arctic warming over the first part of the GFED period, as shown on the left, and consequently, the sea ice declines at a faster rate compared to the other two CMIP5 force experiments, as shown on the right plot here. And then finally, in our sensitivity experiment, we found that removing the variability in biomass burning emissions over the GFED period leads to a reduced Arctic warming from 1997 to about 2010, making it more similar to what we see in the CMIP-5 forced experiment. And in addition, the rate of sea ice decline is also reduced and also is more similar to the CMIP-5 forced experiment. So this implies that the increased interannual variability in biomass burning emissions over the GFED period is causing enhanced Arctic warming and sea ice decline since the late 1990s in the CSM2 CMIP-6. In terms of sea ice sensitivity to CO2 on the left and global mean surface temperature on the right, the sea ice sensitivity is similar for the CSM large ensemble and the CSM2 CMIP-5. But then that CI sensitivity increases, meaning more negative, for the CSM2 CMIP-6. In addition, the CI sensitivity in the CSM2BB falls about halfway between the CI sensitivity of the CSM2 with CMIP-5 and CMIP-6 forcing. And so this suggests that based on these results using the CSM model, the increased CI sensitivity to CO2 and global mean surface temperature from CMIP-5 to CMIP-6 that was reported by the SI-MIP community in their paper published in 2020 is likely due to changes in historical forcing, not improvements in model physics. So I want to finish up this presentation by making a link to the observed sea ice decline and ask whether there is a force signal in the recent reduced rate of Arctic sea ice loss. So as can be seen on this plot showing, again, 20-year linear trends in September sea ice area, the sea ice loss, acceleration, and recovery also seems to be present in the observations, with the timing of the maximum negative trend only shifted by a few years compared to the CSM2 CMIP-6. Excuse me. However, the sea ice recovery is also present in our sensitivity experiment CSM2BB, with no interannual variability in biomass burning emissions, although the magnitude of it is much reduced compared to the CSM2 CMIP-6. As such, our conclusion is that there must be other forcings at play here, at least in addition to the biomass burning forcing. And therefore, although we can say with confidence that the increased interannual variability in biomass burning emissions is causing enhanced sea ice loss from 1997 to about 2010, we cannot say that it is responsible for the sea ice recovery that follows, although it may contribute to it together with some other forcing that is currently unknown. And so in summary, I showed that the CSM2 CMIP-6, as well as a few other CMIP-6 models, simulate an acceleration in sea ice decline that coincides with the start of the GFED era, followed by a recovery until the start of the 2020s. We conducted a sensitivity experiment in which we removed the interannual variability in biomass burning emissions over the GFED period. And those sensitivity runs showed reduced Arctic warming and sea ice decline compared to the CSM2 CMIP-6. We also found that half of the increase in sea ice sensitivity from CMIP-5 to CMIP-6 in the CSM2 could be attributed to the increased variability in biomass burning emissions during the GFED era. And there seems to be an indication of a force signal in the recent reduced rate of Arctic sea ice loss, although biomass burning emissions alone cannot explain it. So I want to thank you for your attention, and I'm happy to take any questions now or later on in the chat or via email. Thank you.
Thanks, Patricia. So are there any questions?
Okay, I was struggling to find the Zoom window, but I found it.
I have a question sort of inspired by this. So in one of the plots you showed, you have the I guess the biomass burning, the predictions in the model are very, very smooth. And what do you think the models would show if you had more realistic sort of bouncing up and down biomass burning?
Yeah, we actually tested that out a little bit. So we ran a few future experiments, so starting in 2015, I think until about like 2040. And we kind of like created these random, variations in biomass burning emissions based on the GFED period. And we didn't really see a difference in the recovery of the sea ice, which was surprising to us. We thought that, these kind of sharp transition from no variability to variability to no variability were going to explain the recovery. But it doesn't seem to be the case it seems to be able to explain the decline, but not the recovery. But I agree with you that in a perfect world, now that we know that there's a lot of variability in these emissions, we should probably include that in the future scenarios as well. I guess it's just kind of hard to predict how those emissions are going to change in the future. Yeah.
I have a question, if that's okay.
Yeah.
Yeah. So I was wondering, the CSM2 in particular seems particularly sensitive to those super sort of high frequency variations in that biomass forcing. And it is even like, you're saying that it might be more sensitive to Pinatubo just because of its various new aerosol type parameterizations. But I guess one thing that I wonder is that, like, if a model is super sensitive to these like short time scale fluctuations, like is the mixed layer like really shallow or something like that? Like, I just wonder if there's sort of some elements like perhaps biases or whatever you want to call them in the model that compared to these other CMIP6 style models that make it particularly sensitive, which would be interesting. I mean, we were finding some interesting things also in the Antarctic. Like the Antarctic, for example, it is like much warmer at depth in the CESM2 than in the CSM1, for example, even though at the surface there's more ice. So, or not more ice, there's less ice and it is thinner, but like it was just quite surprising how warm it was underneath. So I just wonder if there's like some weird things like that going on in terms of sort of ocean characteristics that might render greater sensitivity to high frequency variations.
Yeah, that's a good question. I haven't looked much at ocean fields. We've been mostly focused on atmospheric fields because we know that biomass burning occurs over land in the northern hemisphere, especially in North America and Siberia, and then that heat kind of gets transported to the Arctic, and then you see the results of that. That's a good question from the ocean side. I don't have a strong intuition about if there are some changes compared to the previous version that could explain that.
All right, I think we'll move on to the next talk. It looks like there are some questions in the chat for you, Patricia, and please put other ones there as well. So our next speaker is Dave Bonin from Caltech, and he's going to be talking about explaining and constraining the spread and projections of Arctic sea ice.
All right, thanks, Marika. Yeah, so I didn't do any specific experiments with CSM, but I hope you guys find this still interesting. It's work that I've been doing mainly with Tapio Schneider and Ian Eisenman, and then Marika Holland, Flavio Lehner, and then Rob Wills at the University of Washington. And it's really trying to both explain and constrain what I think we need to do in the spread of projections of Arctic sea ice. So if we look at the Arctic sea ice just over the historical record or the observational record, we know that there's like pretty large changes going on over the seasonal cycle. So what I plotted here is just the seasonal cycle of Arctic sea ice extent, color-coded by each decade, where black is just the year 2020. And we experienced the second lowest sea ice extent on record in September here. And I think it's pretty striking to note that the decline in the summer is just a lot more than in the winter, which is a bit more muted. But then there's also been substantial thinning of sea ice across the seasonal cycle of in the Arctic as well, as noted here by Arctic sea ice volume. And so if we just look at uncertainty and projections of Arctic sea ice, I think we're all very vaguely know of kind of the Hawkins and Sutton framework of this, of where you have model uncertainty due to model structure, uncertainty due to internal variability, and then uncertainty due to emission scenarios. So what you're looking at here is just September Arctic sea ice extent with all the available CMIP5 models going forward under RCP 8.5 forcing. And then here is just the MPI grand ensemble labeled in red for the RCP 8.5, and then here are the different emission scenario. And you can kind of see that there's about, say, a 6 million square kilometer spread to begin with that remains so going forward in the 21st century. And then internal variability can add an additional, say, 2 million square kilometer spread to that as well. And then by the end of the century, there's this pretty large emission scenario uncertainty. And so what I want to argue is I think that with the release of the multi-model large ensemble archive, we have a kind of a unique advantage here to really understand uncertainty both at different spatial scales and temporal scales as well. And so what I'm plotting here is just September Arctic sea ice extent again under these RCP 8.5 scenarios, where now each line represents the multi-model or the different large ensemble, and each line is the multi-model or ensemble mean of the large ensembles. And then this is the spread as well. And I think what's interesting to note here is if you just plot that available CMEP5 spread, you can see that this multi-model large ensemble archive really captures the spread in the CMEP models as well. So it really tells us that we can, apply some framework here to really understand and parse uncertainty and projections of Arctic sea ice extent. And so what I'm going to do is I'm going to just say the total uncertainty is the sum due to model structure, uncertainty due to internal variability, and then uncertainty due to that emission scenario as well. And so to really do this, we can take the ensemble means of these large ensembles, which is that forced response. And that's what I plotted here, just in an arbitrary reference metric of percent of remaining sea ice. So this is 100% of sea ice remaining. This is when sea ice is all gone. And if you take the variance across these ensemble means, that's the model structure. You can then look at each individual model's internal variability and take the variance across just the model's ensemble members. And then you can also do this for different RCP scenarios. And I should note that for these RCP scenarios, we turn to the CMEP5 archive just to accurately represent of what the different scenarios do, just because these large ensembles only have RCP 8.5 forcing. And when we do this, we kind of get the canonical image of, I think, uncertainty that people are aware of. And so this is looking at how uncertainty unfolds both in time for September Arctic sea ice extent going forward in the future. And I think you can see that internal variability matters a lot. Initially, about 40% of the uncertainty is due to internal variability. That quickly diminishes, and then model structure really matters towards the middle of the century. By the end of the century, scenario uncertainty really matters. And so this is kind of a nice breakdown of what's going on. But I think what's really unique about the multi-model large ensemble archive is we can start to understand intermodal differences in the representation of internal variability here in sea ice. And so the shading here actually represents either the lowest amount of contribution to internal variability or the highest amount. And so it's saying that some models, primarily the CICE model, is suggesting that only 20% of the uncertainty going forward in the future is due to internal variability, whereas some of the other models are saying upwards of 60% can be due to internal variability. And so I think that these, the understanding the intermodal differences in this internal variability is kind of an interesting question going forward. But what's also unique is we can do this for other months as well. So now on the right, you're looking at how uncertainty unfolds for March sea ice extent. And this is the fractional contribution of model structure, internal variability, and scenario again. And I think you can note that internal variability matters a lot more than, say, in summertime, and it actually persists much longer into the 21st century than it does in the summer. And then really towards the end of the century, you start to see model structure dominates with little representation of scenario uncertainty, but I think that this is sensitive towards the representation of these large ensembles with respect to the CMEP 5 archive as well. So don't read into that too much yet. But what's also unique is then we can go towards a more regional focus. So I've kind of broken these up into domains of Arctic sea ice in July, August, and September, but for the central Arctic, what I'm calling the Siberian marginal seas, which is just over here off the coast of Russia, and then the North American marginal seas as well. And I think that what you start to see is that if you contrast this with what's going on in September for total sea ice extent, you see there's a quite large role for internal variability that becomes a lot more important as you go towards these more regional domains. But again, there's this generic picture of where model uncertainty peaks by mid-century and then reduces towards by the end of the century. What's interesting, if you focus on wintertime sea ice, so January, February, and March in these kind of more peripheral Arctic Ocean domains, you start to see a different picture. So in the Baffin and Hudson Bay, upwards of 70% of that uncertainty is due to internal variability in the next few decades. And in particular, I want to focus on the Jin and Barents Sea, in which you see that internal variability really dominates projection uncertainty for the next 20 or 30 years. You're seeing that upwards of 60 to 80% of the uncertainty is just due to those internal variations. And I think that understanding how this relates to ocean heat transport is also an interesting question going forward. But kind of what I'm walking through this really quickly because I really want to understand how can we reduce this model uncertainty. And I think that there's kind of a fun framework that people have been pushing lately that I'm trying to add on to. And so what I want to focus on is we have a kind of a simple expression that I think relates future Arctic sea ice area or extent to past sea ice area and extent. So what this equation is, just future sea ice area is a function of your mean sea ice area times some plus some sensitivity of sea ice to Arctic temperature changes or to CO2 changes, like what Patricia was showing earlier, and then times that amount of warming. And so what I'm plotting here on the left is just annual Arctic sea ice extent in black. And then on the right is Arctic sea ice area as a function of, or scatter plot of Arctic temperatures. And so what you can do is through total least squares regression, get some kind of gamma or some sensitivity parameter, at least for the local Arctic temperatures. And then if we take the average Arctic sea ice extent and temperatures over the past 40 years, we can reconstruct Arctic sea ice fairly well. And so we're explaining over 60% of the detrended variability here. You're also capturing those interannual variations and that long-term trend. And what's unique about using kind of the local sea ice sensitivity rather than the global is you get a really good picture of what's going on at monthly timescales as well. So over here on the left is just observations over the past 40 years of sea ice extent. Here's January through December. And then if I estimate the sensitivity parameter at each month and apply this same kind of framework, we can reconstruct both the decline of sea ice extent, those interannual variations, and really this more muted decline of wintertime sea ice extent. And so I think what you can start to ask is, well, how well does this allow us to understand what climate models are doing too, or what the CMET models are doing? And so if you take this equation and I just say, let's calculate the average sea ice area over the past 40 years, and then the sensitivity over the entire length of the simulation, and then calculate the amount of warming relative to that reference period, I can reconstruct sea ice extent. So plotted here on the left is just September sea ice area over the historical and SSP 5 8.5 scenario, where this is the ensemble or multi-model mean, and there's just each individual model. And then on the right is equation 1, which is just representing what these models are doing. And I think broadly you see that both the multi-model mean match well, and that spread is kind of captured as well. And so we can kind of do this a little bit more quantitatively, as you can say, what's the proportion of variance that this equation can explain in the CMET models as a function of month? That was just September I was showing you. And so on the x-axis here is just 2020 to 2100. On the y-axis is January through December. And you're seeing across all months, you're explaining upwards of 70 to 95 to 100% of the variance, basically. And I would say that arguably you're explaining most of the variance. 70 is a low estimate here. And so I think what's unique about this is we can start to play a game and say, well, what's causing the intermodal spread and projections of Arctic sea ice extent? How does each of these terms contribute to this? And then it allows you to start to answer questions. If mean state biases were reduced in GCMs, how much more certain is the date of an ice-free Arctic? Or I think that kind of the more interesting one is that if there was an emergent constraint on Arctic warming, how does this impact this expression? How can we relate that to sea ice changes going forward in the future? And so to kind of parse this, if we look at the contributing factors of this spread of each term, we can say, let's apply the multi-model spread of one of the terms, but hold the other two terms as the multi-model mean, and just ask how much variance does that explain relative to this proportion of variance squared. And what you see is that most of the spread results from mean state biases that really persist throughout much of the 21st century. Matters more for wintertime projections where there's less sea ice decline, but really just those mean state biases cause the spread. But then if you apply the other two terms, you see that that sensitivity parameter doesn't really explain much of the variance. It kind of contributes more towards the end of the century when that trajectory matters. But the amount of warming is really what's determining the spread of sea ice extent towards the end of the 21st century. And so I think that this framework now kind of allows us to say, well, how does this impact the probability of an ice-free Arctic, which I think a lot of us care about. And so what I'm plotting here is just a probability distribution or cumulative density function of the first year when each model crosses this 1 million square kilometer threshold. And then I've just assumed some Gaussian distribution, and then this is the cumulative sum of that distribution. And so this is equation 1. I should note that equation 1 looks similar to what the CMET model's raw output suggests as well. And it says that, say, the 50% probability of an ice-free Arctic occurs by 2050. And so now if we take these same models, but add in the mean state of the observed record and reduce the mean state of all these, or remove the mean state of all these models, you decrease the likelihood of seeing ice-free conditions going forward in the next few decades, but you increase it much more quickly after that. And so this moves that date up by 4 years, and you increase the very likely date of an ice-free Arctic upwards of 15 years. And we can do the same thing of if we increase the observed local ice sensitivity rather than each model's sea ice sensitivity, you move that 50% probability up by 2 years, you decrease the likelihood a little bit more, and then you increase the very likely date of an ice-free Arctic by another additional 5 years. And then what I should note here is that we can also understand what this gamma parameter, this sensitivity, is doing in observations and how it evolves towards the future. And so I've constrained this with model guidance of how the sensitivity evolves in the future. I'm happy to talk about this more later. And that adds in an additional 4 years. And so you're seeing that with this kind of constraint here, we've reduced the probability of seeing an ice-free Arctic, or increased the probability of seeing an ice-free Arctic by upwards of 30 years by this very likely date, just through this kind of simple equation. And then I should note that this is the CSM large ensemble. We can get kind of a probability distribution of just due to internal variability. And that's what this red line here. So it's saying that the Arctic has a likely date of seeing an ice-free Arctic anywhere between, say, 2040 and 2048, just due to internal variability. And I think, I don't know time, but you can do this for each SSP scenario. So I've broken this up into now July, August, September, and October, which I think is kind of remains a less understood part of seeing ice-free conditions, is just the seasonality of this. And then you can also do this for each SSP scenario. So in black is the raw output, basically, and then red is the constrained projection. And so I think, interestingly, in July, across all probability you're seeing, or values, you're seeing a reduction of about 30 years in these constraints. It's less so for September and August, but remains, I think, a more constrained picture of what we see the Arctic is going to be going forward in the future. And so I kind of jumped in through a lot there, but I think what I really wanted to emphasize is that model uncertainty dominates these projections of Arctic sea ice, which I think we all know. But internal variability could contribute up to 60% of the uncertainty in the first few decades, and really impacts uncertainty at longer lead times in the wintertime. And then the influence of internal variability is very seasonally and regionally dependent. So in the Jin and Barents Seas, for instance, it matters much more in the wintertime, whereas in the North American marginal seas, for instance, it's a little bit less and doesn't persist as long into the 21st century. And then we've used this kind of simple linear expression to kind of emulate the future evolution of Arctic sea ice extent. And we've related that to present day biases, the amount of Arctic warming, and the sensitivity of sea ice as well. And so using that, we can kind of constrain the 50% probability, or these different likelihoods of seeing an ice-free Arctic. And it's suggesting the 50% probability is anywhere between 2037 and 2044 going forward in the future. And we can also do this for different summer months as well. So this work's been written up in a paper with Marika and Flavia that was just published a few weeks ago, and one that's about to be submitted in a few weeks. So thank you.
Thanks. So we have time maybe for a quick question. All right, well, I guess please put questions in the chat for Dave then. I have some questions, but they're a little longer questions. So, and we're gonna move on now to Chris Wyburn-Powell, who's gonna be sharing with us some work on the realism of simulated internal variability in Arctic sea ice. All right, and Chris, we can see your slides. But we can't hear you, so I think you're still muted.
Right, you can hear me now, right?
Yes, now we can hear
Great. You. Okay, yeah, thank you for the introduction. So today I'll be talking about the realism of simulated internal variability in Arctic sea ice. And this is work I've done with Alex Yarn and Mark England. So as Dave Bone was just talking about, we have a large proportion of projection uncertainty, which is due to internal variability. So we have this question of how do we assess the validity of internal variability in models when we only have one realization of reality from observations. So today I'll be talking about using a resampling technique, which will allow us to directly compare the metric of internal variability between observations and models. So the data I've used is the NSIDC Sea Ice Index for observations and 5 models from the CLIVAR Multi-Model Large Ensemble archive. And the parentheses show the number of large ensemble members. The time periods we'll be using are 1979 to 2020, and that allows us to compare an equivalent forcing. We'll also compare a 42-year period where the mean state of sea ice is equal to observations. So for example, in September, CSM in blue has an equivalent mean state to observations in the period 1989 to 2030. So resampling methodology has the assumption that the forced response causes a linear trend, and therefore any deviations from that linear trend is due to internal variability. So this plot on the bottom here for the September sea ice area, we can take the anomalies from that in this bar graph here, and then we can resample those 1,000 times. So once we've done that, we can compute 1,000 equally possible scenarios which could have happened due to different internal variability. And then we can take the gradient of each of those 1,000 resamplings and then use that to compare different time series from models and observations. So using the standard deviation and the mean from the NSIDC observations, we can build up this PDF, which shows how the internal variability has some uncertainty in the observed trend. We can also resample each of the time series for the 40 CSM members as shown in these faint lines. And we can take the average of these 40 members as shown in this dark blue line. And what we can see here is that the PDF of the average CSM member is wider than observations, suggesting that this resampling methodology picks up more of the variability, internal variability, than observations. Another metric which is usually used for assessing internal variability is the standard deviation between members in a large ensemble. And here this is shown in gray for CSM. And the large ensemble standard deviation is approximately 1.8 times the size of the average resampled member. So now, if we look at the 5 models and for all months, not just September for CSM, then we find that there's quite a variety between the 5 models, where we have CANISM in pink, for example, which has a similar amount of internal variability by this resampling metric if you look at the large ensemble or you look at the individual resampled member. And so in contrast, the ESM2M model has up to 3 times larger standard deviation across the members than if we were to resample an individual member. And so this is for the period 1979 to 2020. And we get very similar results if we look at the equivalent mean states for different time periods. Now, if we compare more like for like with an individual member versus observations, and we resample both of those, we find that model members are typically around 10 to 50% larger in this metric of standard deviation than observations. So now if we look at the trend spatially between 1979 and 2020, we find that for September, the largest trends are distributed in the marginal seas. And then for March, we have the largest trends in the Barents Sea and Greenland Sea. So if we consider each of these grid cells as having a time series, like we're talking about with the Pan-Arctic, then we can resample each of these 1,000 times, compute the trends, and then find the standard deviation within those 1,000 resamplings. And so the plots in the middle here are showing the amount of variation between these trends. And what is noticeable is the fact that in September, the area with the largest variability by this metric is in the East Siberian Sea, which is not actually where the largest trends are for the 1979 to 2020 period. Similarly, in March, we have the strongest, the largest variations in the Labrador Sea and the Bering Sea, which aren't the locations where there is the strongest trend. So to put these standard deviations into context, if we were to start in 1979, the sea ice concentrations in that year, and we were to go 41 years into the future, using a plus or minus 2 standard deviations from the observed trend, we would find that the some areas in September have up to 10% sea ice concentration difference due to this internal variability picked up by this resampling methodology. So now we're going to focus in on the standard deviation for each of the models. And again, we have the observations, just like the previous slide, on the far left. So what's immediately apparent is that the variations in standard deviation in March are very similar across the models, and there are only a few patterns which are dissimilar. So for example, CSM, there's, CAN-ESM, there's less variability in the Bering Sea than observations, and we have in CSM less variation in the Labrador Sea. For September, we find that CSM and GFDL ESM2M have relatively good representations of the variability in the marginal seas. CAN-ESM and CICE are not very well represented in the internal variability here, and that's mainly due to their mean state issues. So now if we move on to the time period equivalent to the mean state of observations, then we find that March is practically unchanged. We haven't noticed much of a difference between this and the 1979 to 2020 period. In September, we find that now we have MPI as well to look at, and that has much higher variability than observations in the Central Arctic. And in fact, all of the models seem to have a higher variability in the Central Arctic than observations, with the ESM2M model being the most realistic. So another way of looking at whether the simulated internal variability is realistic is whether there is an overlap between any of the members and observations. So here I've shaded in black any regions which have over 97% climatology for sea ice concentration, because these regions have very low variability and it's difficult to compare models and observations here. What we find in March is that the ice edge is a big determination on whether the models are too high or too low in their variability compared with observations. In September, we find that for CSM and ESM2M, that most of the marginal seas are relatively well represented in their variability. So at least one member overlaps with observations, and that's shaded in white. We look at MPI ESM1. Most of the marginal seas here have too low variability in the model, and so there are no members which overlap with observations. So now to conclude, the resampling technique does not capture all of internal variability, typically approximately half to a third that of the full large ensemble. So we're measuring only a portion of the internal variability. We've also found that there is a large variation in internal variability realism between models in September, with some models being better than others, especially CSM and GFDL ESM2M. But there is agreement between most models in March. And when using a resampling technique, the internal variability for most regions and models is not inconsistent with observations. And with that, I'll take any questions. Thank you.
Thanks. So we have time for a couple questions.
So I have one. Hansi and I are kind of going back and forth about CAN-ESM. So it's funny that, you know, both you and Patricia have kind of highlighted CAN-ESM as this really interesting outlier in some ways. And I mean, are there any hints anywhere why that CAN-ESM might be different there? Or
Dave, I just want to point out that in my analysis it was CAN-ESM 5, and for Chris it was CAN-ESM 2.
Oh, okay.
Yeah.
Yeah. I can't say that there's anything that is immediately apparent, but yeah, I'd have to look into that because it's definitely wrong for for maybe the right reasons or wrong for the wrong reasons, and I'd have to drill into that further.
Thanks.
Other questions?
I put this into the chat, but and I might have just missed this in your talk, but I was wondering, in your resampling technique, how do you account for potential sort of auto-regression?
Yeah, so we used a 2-year bootstrap sampling size for our resamplings because that's where we found that autocorrelations dropped off between 1 and 2 years, 2-year lags. So that's a compromise, but the smaller bootstrap size you use for resampling, the greater variability you'll have. But we found that 2 years was a compromise between including enough of the autocorrelated data and still retaining enough variation.
Okay, so I think we should move on to the last talk before our discussion session. So Steve Vavris is going to be from University of Wisconsin-Madison, is going to talk to us about interactions among Arctic cyclones, atmospheric rivers, and sea ice. So Steve.
All right. Is that coming through?
Yep, looks good.
Okay, great. So as the last speaker of the day, you're going to love that I'm going to keep this mercifully light. This talk is actually just a preview, so no real results to speak of yet. And this project is I'm part of, along with my co-conspirators from NCAR here, who are probably all on the call. And we're taking a bit of a systems approach to address the question of sea ice and its feedbacks among Arctic cyclones, wind, atmospheric rivers in a warming climate. And part of the motivation, societal motivation for this, has to do with coastal erosion, which most of you know is a real problem in the Arctic, and it's becoming worse. And so an open question is whether atmospheric changes involving winds and cyclones and such as the sea ice retreats, whether it's exacerbating this problem. So this project is brand spanking new. We just got official approval of it last week. And so we had a virtual celebration with imaginary rounds of beer. And hopefully someday we'll be able to turn that into a real celebration with real beer. So just a general picture, just a climatology of part of our hypothesis here. If you look at the present day distribution of sea level pressure and surface winds in the Arctic, this happens to be the multi-model mean from CMIP5, but it matches observations very well. And you look at the sea level pressure pattern on the left, you'll see well-known high pressure over sea ice, over the colder ice pack in the annual mean, and then these well-known strong subpolar lows on either side over the ocean. And you'd see over looking at wind speed, you see an even more striking pattern. And that is that over land, the winds are light. Over the open ocean, the winds are strong. And over the sea ice, the winds are light, but not quite as light as over the land. So it's really a simple picture in the observations. In reality, sea ice cover goes along with high pressure and light winds, and open ocean goes with low pressure and strong winds. So if you didn't know anything else, you might speculate that as the sea ice retreats, we're going to have more of this open ocean environment with more cyclones, lower pressure, stronger winds. And that's part of our conjecture for this project. But it is just conjecture, it's pretty simple. So is there any observational support for that? And the answer is yes. This is based on some results of work that I've been leading that's very related to our new project. In review right now. If you look at the CMIP-5 multi-model mean of annual sea ice area, the trends up here in the upper left, we get a huge decrease, 50 to 60% in many places. This is with the RCP 8.5. And if you look at the corresponding surface wind field, it's a dramatic match. It matches almost 1-to-1, where sea ice retreats in red, winds increase in red over the open ocean, not over land. And yet over areas that presently have no sea ice, it's the opposite pattern. You see somewhat of a decrease in wind speed. And if we look at sea level pressure, we do get the expected decrease in pressure just based on present day observations. It spills over actually over onto land, unlike the wind changes, but the center of it is indeed over the areas of Arctic Ocean and sea ice. And again, this is in the annual mean, but certain seasons have an even stronger pattern. So for instance, if you look at winter, the well-known strengthening of the Aleutian low with greenhouse warming really comes through here. Just to put these changes in perspective, these wind trends are of the order of 10 to 12% in the annual mean. In certain seasons like autumn and winter, they are stronger, maybe 20, 25%. So pretty intriguing, I think. And it leads us to our conceptual framework for this project. So the first step is to consider changes in sea ice, specifically reductions as observed and projected for the future. And that, based on past work, corresponds to windier surface conditions. We're not talking aloft, but at least at the surface, as well as a more cyclonic circulation in the boundary layer. The interesting part, though, is what does that entail in terms of, before I jumped ahead, it's known already that cyclonic change is basically a thermal low, so a baroclinic response that's been shown in various other studies with sea ice reductions. The transition toward a windier climate with less sea ice is not as obvious. So there are probably three candidates. One is that the geostrophic winds might get stronger, so a tighter pressure gradient, but based on past research, the answer is generally no, except in areas like around the Aleutian low. Another candidate is reduced atmospheric stability as the surface heats up more than aloft, and that creates more vertical mixing of momentum to strengthen the surface winds. That's a maybe even a probably. But perhaps the strongest candidate, we think, is that a smoother surface as you go from jagged, rough sea ice to open ocean is probably the leading candidate for why you get stronger winds. And we'll address this point later at the end of the talk. So as I was saying before, the interesting part about this is the feedback part. And so for instance, if you get these direct effects of sea ice with a windier, more cyclonic atmospheric circulation pattern, what does it entail for ocean feedbacks? For example, you'd expect windier conditions to strengthen the surface momentum flux, leading to more ocean mixing and more ice transport. At the same time, a more cyclonic circulation favors Ekman divergence and associated ocean upwelling and impacts on sea ice in that respect. And then when you add the atmospheric feedbacks on top of this, you get this interesting feedback loop that we're proposing. Windier surface conditions imply stronger evaporation, more long wave radiation and precipitation, probably clouds, and that'll have some impact on the sea ice. You might expect it to be a positive feedback, lead to even more sea ice reductions. But interestingly, depending on things like the timing of enhanced snowfall, if it happens in the spring, it might actually suppress sea ice melt during the summer. With cyclonic circulation changes, tied in with those are atmospheric rivers and more broadly with moisture intrusion events, which have been increasing in the Arctic. If those increase, we would expect, again, more long wave radiation and precipitation, perhaps even rainfall, which will have some bearing on sea ice coverage and thickness. So our hypothesis is that this is generally a positive feedback loop, but some exceptions are likely. And this leads us to our key research questions. One is, how do extratropical cyclones and ARs and Arctic winds affect sea ice through these different momentum fluxes? So that's in this picture, in this conceptual diagram, that's the arrows pointing to the sea ice changes and those feedbacks. And then the other direction, how does sea ice changes, how do those affect the cyclones and rivers and Arctic winds? So that's the black arrows emanating from the sea ice loss. And then maybe the most interesting question of all is, how will a changing climate affect these feedback processes and their relative importance? So for example, if you get a windier climate and you have a thin and mobile ice pack like we're increasingly getting, that ought to mean that your ocean mixing and ice transport is felt more and has a more appreciable impact on the sea ice changes than if those exact same wind increases had happened in year 1800, for example. Our tools for this work are proposed to be threefold. One is the CESM and CESM2 large ensembles. As the newer ones become available, we'll lean more on CESM2. We don't want to put all our eggs in one basket, and so we're going to also be looking at the CMIP5 and CMIP6 output, increasingly at the newer CMIP6. And then PAMEP, the Arctic Model Intercomparison Project, has some useful experiments for us too, especially the prescribed sea ice experiments that'll help tease out the separation between the direct sea ice effects on the circulation and then the resulting feedbacks. And then finally, we're also proposing 2 new modeling experiments with CESM2, at least one of which will use Polar Climate Working Group resources. And that's being this first one of the smoothed sea ice experiment, in which we'll reduce the surface roughness of sea ice to match that of open water. And so that addresses this question of why, when you get sea ice reductions, why do models typically produce stronger winds? And so if in this experiment with the smoother sea ice, we find that that largely explains the standard simulation, that would point to the smoothing surface as the culprit. But if we don't get a windier climate, then that implies another factor, probably reduced atmospheric stability and more turbulent vertical mixing as the cause. And then the last experiment, at least that we proposed, is a suppressed atmospheric circulation change. We've been hearing about nudging being used in various ways today, and that's what we're proposing here. And that would be a way to try to short circuit some of these feedback loops. And so we would, for instance, if we wanted to reduce the impact that winds have, the feedbacks of winds on sea ice changes, we could do that with the nudge sea ice experiments by preventing these wind changes in the first place to suppress these feedbacks involving evaporation and surface momentum flux. And similarly, if we wanted to reduce the direction of the wind changes and the cyclonic flow, that would have a reduction in the Ekman divergence and the moisture import, presumably. So this is what we're proposing. Like all projects, I'm sure it'll evolve. But anyway, this gives you a preview of what we're planning, and hopefully at next year's Polar Climate Working Group meeting, we'll actually have some results to show. So with that, I will stop and be happy to take any questions.
Thanks, Steve. Are there any questions?
Very good, CICE. I've got a question.
Yep.
Steve, this is really nice. With respect to your smooth sea ice experiment, are you planning to scale that as a function of the wind speed? Because I mean, for the ocean, you know, the drag coefficient is going to be dependent on the wave height and wave steepness. So there is a wind dependence to that. Are there plans to do something similar with the ice?
Yeah, that's a good question, Heis. We haven't figured out all the details of this, and there is that nonlinearity that you describe. So we may have to tinker with this to see what works best. And it's possible, as you're suggesting, that the transition from sea ice to open water may not actually lead to a smoother surface. If you have really strong winds and a really rough ocean surface, conceivably, the roughness could actually increase. And so there are places and the potential for that to happen. So I think that makes it an interesting experiment, but the details need to be worked out because, as you described, there may be some complexities we haven't thought of.
Thank you.
I had a kind of dumb question. So, I mean, you're talking about increase in windiness. I mean, this is in terms of speed. Are you going to look at sort of breaking that down into the zonal, the meridional component, which is changing, you know, and you know, I guess getting more at your question of more cyclonic activity. So, you know, can you be able to suss that out from this?
Yeah, absolutely. And so the focus has been on the windier conditions, but in the net. But you're right that the breakdown between zonal and meridional flow is very relevant. There was a recent paper that came out that showed that there's a tendency for more of a southerly flow to occur with the reduction in sea ice in the observed record. So up to present. And so the suggestion was that could act as a positive feedback with the import of more heat and moisture from lower latitudes into the Arctic. So I agree, that would be an interesting thing to look at, and we certainly will. Although for the proposed work, the focus was primarily on the wind, the total wind speed, and its impacts and suggestive on things like coastal erosion and wave height.
Okay, well, so thanks so much, Steve, and thanks to all the speakers. There was a really nice set of science talks throughout the day, so that's been great. So now we have a discussion session, and we just decided on the fly, as we do at these kind of polar climate working group meetings, that maybe we should try to do this as in breakout groups so that more voices can be heard. But I want to, before we attempt that, because I've never actually set up breakout groups on Zoom before, I wanted to first see if people want to participate in the discussion before we force you into a breakout group. And so I'm not quite sure how best to do this. Maybe if people could raise their hand in the, or now I can see most of you. And I see Heis put his hand up. So yeah, if people can go and raise their hands, that would be great. I can't remember how to raise my hand. Under reactions, I guess. Okay, I see.
Yep.
Yeah, you can do it under reactions.
Oh man.
Lindsay's laughing at me.
No, I'm laughing at myself. I can't find it. Yeah, so it's ridiculous.
It's under reactions at the bottom. There's a hand raise feature, or you can do a clap or a smiley face if you're just really excited about joining a breakout room.
Right. I think the clap and the smiley face goes away.
Oh, well, that complicates it.
Yeah. So, or just sit there like this.
So I see 13 people that have raised their hands, but I don't know if that means we're, you know, some people may have had to step away to get a cup of coffee, something like that. And I guess the thing is I can put people randomly in breakout rooms, and then if you come back and you're in a breakout room and you don't want to be there, you can just leave. So, okay. I'll give people one more minute to see if they want to try to join a breakout room. Because the idea was that if there's enough interest, we might try and do 4 breakout rooms. And Hansi, myself, Dave, and Alice have all agreed that we would lead or kind of be the discussion leaders. Alice, I believe you agreed to that. Yeah, okay. Because this was a conversation between Hansi and Alice that I wasn't involved in, so good to confirm that. But it would just be a way for us to, more people to actually participate in the discussion. And I did send a slide, kind of a discussion slide to everybody, all of those 4 leaders. And what I would say is just, you don't have to go through all the questions on there. I would say pick the one that is of interest to your group and just focus on that. And then if you need more questions, you can shift to another topic as well. So I think we're going to go ahead and try this. Like I said, I haven't done this before. And so if it doesn't work, we'll only try it for a couple minutes. I mean, if I can't figure it out, I'm just going to make us all come back and discuss in this room. And hopefully I won't disconnect everyone.
I think
so I'm going to.
Todd can also help us with the breakout rooms too. He's had a fair bit of experience.
Yeah, I messaged Todd, and I expect he might be off.
Okay.
Paying attention to something.
Hey,
else.
I'm here.
Oh, you are here. Oh, okay.
Yeah, I'm trying to reach out to Ryan about the co-hosting.
Okay. Well, I have so Todd, have you done breakout rooms in the past, and would you?
I have not.
Okay. So I have a breakout room button on my Zoom call. So I'm going to push it and see what happens.
Go for it.
It says I can create 4 breakout rooms. So I'm going to do that. I'm going to, let's see, it will assign automatically, but I'm not sure how to do that and put an organizer in each room. So I can assign manually too. So I'm going to try and do that so that I can make sure that
you might
Alice
be able to just move people around afterwards if you don't have a host in each.
Oh, you can?
I think usually. Depends how the settings are.
Okay, I'm going to just assign automatically. And
yeah, do it.
If
an experiment.
2 of the discussion leaders are in one room, discuss amongst yourself and try and leave and join another one.
I think you can move them yourself. I think if you do the random assignment and then you can move people to where you want them to be, I think.
Okay. I'll assign automatically and we'll see how this works. And if you have no discussion leader in your group, feel free to just chat and we'll it'll be good for you to just talk with each other. Okay, so I'm gonna create this now. Oh, I see how it works. Okay, so Dave Bailey is in room 1, so that's good. Hansi is in room 2. Alice is in room 3. And I don't see where I am.
I think you can choose which one you go to
Okay.
if you're like the direct host.
Okay, I'm gonna try this. Okay, here we go. Hansi? Huh, I have no idea how I join a room. Todd, do you have any idea how I join a room? You're muted.
I'm just looking at breakout rooms myself.
I probably should have had you create the breakout rooms and then I would have been
Can I assign you to one? Which one would you like to go in?
to number 4.
All right, let's see.
Yeah, I got it. Okay.
Okay, great.
think we're the only ones who came back early because I didn't know what they were going to do. Todd, are you there?
Yes.
Did Marika have, or Marika or Hansi say when people were supposed to come back? Are we reconvening together or?
She didn't.
Okay.
But it must be soon. What time is it now? Almost 4 o'clock, so I'm sure they're coming back soon. And I can also broadcast a message if that helps.
Sure. Maybe give people like a 1-minute warning.
Sure.
Thanks for being cooperative with this experiment.
Yeah, and sorry I didn't have other functionality with the hosting, because as I'm a co-host and not a full
Yeah,
host.
no, that's okay. Don't worry.
Todd, thank you for your help this morning. I'm sorry I seemed like a drag on the system. It was a very strange issue I had. It wasn't breaking, but it wasn't working. So it looked to me like I had a connectivity problem.
Well, I'm glad it got cleared up. It wasn't a drag at all. All right, let me just send this message out. Okay, here they come.
All right, so I think rooms 3 and 4 are back, looks like. We'll give the others maybe a minute to I think we might all be back except for room 1.
I agree with that.
Yeah, I'm looking at my breakout room list. So maybe give them a minute. I don't know. So this was Alice's idea. I just want to give her credit for it because actually I think it worked amazingly well. Like I thought our breakout room was really good and it meant, you know, you could have much easier conversations than with all of us together. So Alice, you're awesome. Thank you for the idea. Even though my implementation of it was a little, but
it was very short notice. When I have to do something like that, especially because it seems like Zoom changes, like when they changed where the raise hand button went, I got confused for weeks. So.
Yeah. But I think it was it's hard to have a discussion with this many people.
Yeah.
And especially on Zoom. So that was, yeah.
We can just close the room. Should we do that?
Oh yeah, I guess I can close all rooms. All right, I hate to cut them off.
I think it gives them a warning. But
or yeah, can't you put like a timer and after like 30 seconds the room just closes automatically? I don't know.
Oh, I just did it. Sorry, it'll be a minute. It's telling them.
Okay.
As all breakout rooms will close and it's counting down.
Yeah.
So what did you guys talk about? So we talked about how to enhance collaboration and some discussion of kind of what research priorities or what things might be missing that we don't often discuss at the meetings that we should come back to.
So we had this one great suggestion modeled after what the Land Ice Working Group does is a monthly Zoom call where we could just have like, you know, folks that have something interesting to share, little 5-minute updates, you know, that they want to contribute. And then at that time, we can also say, oh, these new data sets are available. This is where they are, or this is the progress on this and this. Y'all folks need to be running your runs because it's your turn, you know, that kind of thing. So we could try to do that. If folks are interested in those kinds of like regular meetups, I think that that could be a way for us to stay connected and therefore more aware of what different folks in our group are doing.
Yeah, I think that's great. We also did have a kind of call for more communication, but through things like Slack, where you can have more sort of informal running conversations. And I love Slack, so no. But I think it would be a good idea. It's like room 1 got kicked out, so yeah.
We talked a lot about kind of what big changes were coming for CESM. We didn't talk about any specific parameterizations to add, but just like making sure that testing with MOM and with MPAS or SEMA or whatever it's called now, all actually, we do thorough analysis of the polar regions because people in our group felt like, you know, what's most important to them, and I know this isn't true of everyone, is that the model has a decent Arctic and Antarctic mean ice state. And if it doesn't, then they feel like it's not usable. Like it was mentioned, they're not sure if they should even use CESM 2. Maybe just stick with CESM 1. And so that was kind of one of the things we talked about. And we also talked a lot about more communication between observational groups and modeling groups, and like how we mostly had modelers in our group, but just how modelers might use specifically like the Mosaic data set, because people weren't really sure immediately about how they would and what the appropriate ways to do so would be.
Yeah. So we had this very kind of a very general discussion about particularly whether it would be possible to find some optimal parameter values for various CICE parameters through the observations, and perhaps in the context of that, use machine learning, though I don't think we got much more specific than that. But that was one way that we thought that perhaps machine learning could be useful.
Yeah, and I know there is several machine learning things that are kind of starting. I mean, Hannah, director, gave, you know, a talk about one thing, and she's, you know, very actively working on that, but only has been for several months. So it's early days, but.
I have a question to everybody, and you could raise your hand or not, but you know, in this new world, we're all doing Zoom meetings all the time. Would you prefer that in the future, like the winter working group meetings, would you be likely to attend if they were in person, or would that make you less likely to attend if you're not situated here in Boulder already?
I feel like, I don't know, I feel like in the past, the Polar Climate Working Group has been really nice, you know, in the way of like accommodating people that couldn't come and like having virtual talks as well as people being in person. And so I think keeping that flexibility of people being able to present and attend over Zoom, but then maybe still for people who can be in Boulder to be able to meet and, you know, see each other in 3D would probably be nice.
Yeah, it looks like Heist put something similar in the chat. So yeah, I think we can do that. And we have done that reasonably well in the past, I'd say. Okay, well, I'm also cognizant of the time and that a lot of you have been on all day. And so anyway, I think this has been really great. I miss seeing all of you in person. I'd love it if we could go out and get some pizza and a beer right now, but unfortunately, maybe in a year. So anyway, I mean, I think there's so much exciting work going on. I think we'll follow up on some of these ideas that came out about how to enhance collaboration, and we'll probably be sending some emails to set things up. But yeah, so look for more on that. I don't know, Hansi, Dave, Alice, is there anything else you guys wanted to bring up before we end the meeting? Okay.
Thank you all so much for hanging on until the bitter end here. So it's great to see all you. So hopefully in person someday.
Yeah. And use your computer resources if you have some. And if you don't, let us know if you want some. We might be able to help out.
That came up briefly in our discussion too, that, you know, feel free to contact any of Marika, myself, or Hansi, and we should be able to fix you up, because there's really not many people running with polar climate resources right now, aside from me. So so I think, you know, definitely contact me, and especially those of you who do have highlighted projects in the Polar Climate Working Group proposal. You know, we're going to need you to start getting on that soon.
Okay. Well, thank you so much, everyone. Enjoy the rest of your day.
Thank you.
Thanks.
Thank you so much.
Thank you.
Thanks, everyone.
Bye.
Marika, did you want us to stick around or anything, or no? Okay.
We could debrief really quickly on Andrew, I should mention to you that, have you, sorry, just because Andrew, you're still.
That's right, I was trying to get off. And it's
You're stuck.
No, go ahead. It's actually good. If I'd like to ask you a question, actually. I didn't want to ask that in front of everybody, but go ahead.
Okay, well, before you, yeah. So in our work, in our breakout group, I mentioned this interest in having a mosaic forcing data set because CICE was in my breakout.
Oh, yeah. Yeah.
And he said, oh, that's a great idea. You know, Matt and I should talk about that. And I was like, well, this is really.
Wasn't he on that call?
Well, yeah, but I think it was kind of because the focus was more on